Hey guys, good morning and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having the good time. So dear students, quickly let me know in the chats if all of you can hear me, if I am perfectly audible and visible to everyone. Quickly let me know in the chats. Quickly let me know in the chats if all of you can hear me, if I am perfectly audible and visible to everyone. Welcome back guys, welcome back. Vanakkam. So as you all must be knowing, from today we are starting this mega marathon series, right? So basically we'll be completing your whole syllabus in the form of marathons now. And today it's going to be our first marathon in which we shall be doing the complete physical chemistry in one shot. Okay? So dear students, you tell me, do you want to start from class 11th physical chemistry or class 12th? Do you want to start from your class 11th or class 12th physical chemistry? Tell me once in the chats quickly. As I told you, this channel belongs to you, right? So whatever you tell me, I'm going to start with that. Quickly, everyone. Do you want me to start with class 11th or class 12th physical chemistry? Quickly. Quickly, everyone. Anyways, I'm going to complete the whole physical chemistry. You don't worry about that, right? So, okay. So, majority is saying class 11th. Is that? Oh, class 12th. Class 11th. So, let's do one thing. Let's follow the sequence then. Okay, let's follow the sequence of NCERT. Right? Let's just follow the sequence of NCERT. Let's start with the first chapter of your class 11th physical chemistry then. Right? I thought to start with the class 12th physical chemistry, but now you are saying class 11th. So let's start with class 11th only, yeah? Cool? Yeah, I can see like there are more than 1600 people watching live and the like count is just 1K. Like, what is that? You have to match it, right? So I'm giving you 30 seconds of time to make the like count from 1K to 1.7K. Quickly. Quickly, quickly. Quickly. Yes? Perfect. I can see people are saying start with class 12th physical chemistry. So let's start with 12th only then, right? Cool. Because otherwise I have to change the slides and so on. Yeah, I don't want to do that. It'll take a lot of time then. Perfect. You be relaxed. Everything will be done and dusted. Just be relaxed. Okay. And I'll be exactly starting from the basics itself. Cool. All right, guys. Yes, exactly. Everything will be done and dusted from the basics. So first of all, the ones who have just joined in, the ones who have not subscribed to the channel, please and please do subscribe to the channel. Do share this video to everyone whosoever is preparing for NEET 2023. This particular session is for everyone, right? Let everyone get benefited out of these sessions, right? So please and please do share this video to everyone and at the same time do subscribe to the channel as well right now. Right now, I want everyone to subscribe to this particular channel so that you remain notified about all the sessions which we take live on this particular channel. Okay? Perfect, guys. So are you guys ready with your pen and paper? Anyways, you are going to get the PDF also at the end of the session. Well, this is the list of the chapters which we are going to do. Let's start with the solid state. After solid state, let's cover the electrochemistry, then kinetics, mole, redox, chemical equilibrium, ionic equilibrium, states of matter, thermodynamics, solution, and atomic structure. This is going to be the sequence which I'll be following with all of you. Yes? This is going to be the sequence which I'll be following with all of you. At the end of the session, I'll be sharing the PDF of this particular session as well. You be relaxed. Okay? Right? So let's get going. Let's get started with the first chapter, that is your solid state. Okay? Solid state. As I told you, I'll be exactly starting from the basics. I'll assume that as if you have never studied solid state before. In the same way, I'm going to teach you. Just be relaxed. Every single point will be covered in detail with all the questions, with all the theory. So Let's get going then. Let's get started. My dear students, as you all must be knowing, whenever we talk about solids, solids are basically made up of constituent particles, right? Solids are made up of the constituent particles. Now, based on the arrangement of constituent particles inside the solid, we classify solids into two types, right? Let me write it over here. So, based on what? Based on arrangement. Based on arrangement of constituent particles inside the solid, we classify solids into two types. Number one. First type is going to be called as the crystalline solids. And one more type, that's called as amorphous solids. Now the point is, what are crystalline solids and what are amorphous solids? Let's have a look on that in detail. And in this particular chapter, let me tell you, we have to deal with the crystalline solids in detail. In this particular chapter, we have to deal with only the crystalline solids, okay? So first of all, your solids are basically made up of the constituent particles, and based on the arrangement of constituent particles inside the solid, we classify solids into two types. One is crystalline and one is amorphous, yeah? Now, what are crystalline solids? The first point which I would want you guys to remember. In case of crystalline solids, what you'll find a regular arrangement of constituent particles. You'll find regular arrangement of constituent particles. What does that mean? You'll get the idea in some time. And in case of amorphous solids, you will find the irregular arrangement of constituent particles. Irregular arrangement of constituent particles. Let me show one scenario over here. Understand properly what I'm going to say. Yes, it's a live session. Understand. See guys, for example, I'm making one small arrangement of constituent particles here like this. Just understand exactly what I'm doing. Just understand what exactly I'm doing. I'm making two arrangements so that you can understand it properly. As you asked to start from the basics, I have exactly started from the basics. Let's cover everything in detail. Alright guys, so let's have a look over here. Let's say I have got a solid in which there are two types of constituent particles. One is A and one is B. Okay, let's say I have got a solid in which there are two types of constituent particles. One is A, one is B, right? Let's say I'm keeping the A particle here, then I'm keeping B. This is A, this is B, this is A, this is B. Similarly, this is A, this is B, A, B, this is again A, this is again B. I'm continuing in the same manner. Right? Over here in the next scenario, I'm not worried about the arrangement. I'm just keeping randomly the particles. Randomly here. Not worried at all about the arrangement. Now look at these two arrangements, my dear students. Look at these two arrangements carefully. In the first arrangement, we have got a solid which is made up of two constituent particles, A and B. In this particular arrangement, do you see the regular arrangement of constituent particles? Do you see after every A, B is getting repeated, after every B, A is getting repeated, after every A, B is getting repeated, after every B, A is getting repeated? So can I say over here in this particular scenario, we have got the regular arrangement of constituent particles. Whenever you see such kind of the solid, in which there is regular arrangement of constituent particles, we call that particular solid as the crystalline solid. Whereas, if you look at this particular scenario, do you find any such arrangement like this? There is no such arrangement. You can see 3A particles here, then 3B particles, then B, then AAA, BB. There is no such arrangement as well. I must say it is the random arrangement over here. It is the irregular arrangement over here. And whenever you see such kind of a solid in which there will be irregular arrangement of constituent particles, that solid I'll be calling as the amorphous solid, right? Very simple and basic. Perfect. Now there are few things which you need to remember about the crystalline and amorphous solids in detail. Okay, let me tell you the first point here, students. When I talk about the crystalline solids, they have got the sharp melting points. They have got the sharp melting points. Whereas if I talk about the amorphous solids, they melt over a wide range of temperatures. They melt over a wide range of temperatures. What is meant by that? What is meant by that? Have a look. If you look at the crystalline solid, there is particle A here, then you have B, right? Then you have B. So over here between A and B, there will be some force of attraction. Between B and A, there will be some force of attraction. Force of attraction, force of attraction. Everywhere, from every side, you will see the force of attraction. Now, which kind of force of attraction do you see in this solid? See, this is AB, this is BA, right? So there is only one type of attraction which I am representing over here, and it is AB attraction. Perfect. There is only one type of attraction in the first case. Look at the second case. Over here, there is an attraction between A and A. Right here, there is attraction between B and B. Right here, there is attraction between A and B. So I can see in this particular scenario, there are three types of attractions which I can see over here. AA attraction, BB attraction, and AB attraction. Perfect. Now, dear students, let's assume in order to break AB force of attraction, let's say I have to raise the temperature till 100 degrees centigrade. Let's assume in order to break AA force of attraction, I have to keep the temperature 70 degree. Let's say over here, I have to keep the temperature 80 degree. To break this attraction, I have to keep the temperature 100 degree. Let's assume that. Let's assume that. Now, if I want you guys to melt this solid, what you guys are going to do? You'll start heating it up. You'll start raising its temperature. When you start raising its temperature, what is going to happen when the temperature reaches 100 degree? When the temperature reaches 100 degree, all the attractions, since there is only one type of attraction here, all the attractions will be broken down at one particular temperature. When you start increasing the temperature and when the temperature reaches 100 degree, all the attractions here will get broken down at a particular temperature. And whenever you see such kind of a solid in which all the attractions gets broken down at a particular temperature, we say that solid has got the sharp melting point. Whereas, look at this particular scenario. First, you'll start increasing the temperature. When the temperature reaches 70 degree, all the AA interactions will be broken down. When the temperature reaches 80 degree, all the BB interactions will be broken down. When the temperature reaches 100 degree, all the AB interactions will be broken down. So can I say this particular solid, it's melting over a wide range of temperatures? Absolutely. When you talk about the amorphous solids, they melt over a wide range of temperatures. Okay. Now at the same time, if I talk about the third point, related to the crystalline solids. Well, dear students, we say crystalline solids, they are anisotropic in nature. Whereas, when you talk about the amorphous solids, they are isotropic in nature. Now, what is meant by this? Have a look. Dear students. Look at the first scenario over here. This is a solid. In which the arrangement of constituent particles is represented here. Okay. Let's say I want to measure some physical property of this solid. Let's say I want to measure some physical property about this particular solid. Right. Let's say I want to measure the refractive index of this solid. Okay. What I'll do? I'll choose certain directions. First, let me measure the refractive index of this particular solid in this direction, right? Then I'll change the direction. I'll measure the refractive index of this solid in this particular direction. Then I'll again change the direction. I'll measure the refractive index in this direction. What you will find out in the crystalline solids? In case of crystalline solids, what happens when we try to measure any physical property like refractive index? The value of the physical property, it will change on changing the direction. On changing the direction, the value of physical property changes, right? And dear students, any such solid in which the value of physical property changes on changing the direction, we say that that solid is anisotropic in nature. So it is basically your crystalline solid which is anisotropic in nature, in which the value of physical property changes on changing the direction. Whereas when we talk about the amorphous solids, you choose any direction, and measure the physical property. The value of physical property due to the random arrangement will come out to be same in all the directions, right? And any such solid in which the value of physical property does not change on changing the direction, we say that particular solid is isotropic in nature. I hope this is clear to everyone. At the same time, when we talk about the crystalline solids, these crystalline solids, they show clean cut. And these amorphous solids, they do not show clean cut, they show irregular cut. What is meant by that? They show irregular cut. What is meant by that? Assume that, imagine that, let's say this is the marker, right? Imagine it is the crystalline solid. Okay? When I cut this marker into two pieces with the help of a knife, right? Perfect. Can I say two new surfaces will be getting exposed? Right? And the exposed surfaces, if it is a crystalline solid, the exposed surfaces, they'll be smooth, they'll be polished. That's why we always say when a crystalline solid is cut with the knife, the new surfaces that get exposed, they are smooth, they are polished. That's why we always say they show the clean cut. Whereas when we talk about the amorphous solids, when you cut the amorphous solids, the new surfaces which get exposed, they are always irregular, they are always rough. Okay, that's why they show the irregular cut, right? One more thing, my dear students. In case of your crystalline solids, let me tell you one more thing. Crystalline solids, they are called as true solids, and your amorphous solids, they are called as pseudo solids. Or they are called as supercooled liquids. Let me write it over here. They are called as supercooled liquids. Why is that? Let's have a look on this as well. This is complete basics which I'm teaching you. Once you understand the basics, then we can slowly increase the level. Okay. So dear students, first of all, why crystalline solids are called as true solids? Why amorphous solids are called as pseudo solids? There is a reason for that. Have a look. See, if I'm sure that you would have seen some old buildings, right? Perfect. Let's say the room in which you guys are sitting in, there will be a glass window basically. When you see that glass window after 15 years, after 20 years, you'll observe one strange thing. The room in which you guys are sitting currently, right? The glass window of that particular room, when you see that glass window after like 15 years, 20 years, you'll observe one thing which will be very strange. You'll find the thickness of the glass at the bottom would have got increased, and the thickness of the glass in the middle, that would have got decreased. Imagine and understand why. The glass which you have in the room, right? The thickness of the glass at the bottom has increased. In the middle, it has decreased. What can we conclude from here? We can conclude some of the constituent particles from the middle, they have moved towards bottom and settled down at the bottom, due to which the thickness at the bottom has increased, right? Any such solid in which the constituent particles have got the tendency to move, any such solid in which the constituent particles show the tendency of movement, we call that particular solid as pseudo-solid, or we call it as the supercooled liquid, right? Perfect. Do remember this. Whereas if you talk about your crystalline solids, they are true solids, their particles, their constituent particles, they do not show any movement at all. Okay? Perfect. One more last thing about the crystalline and amorphous solids. Do remember, your crystalline solids, they show the regular geometry. or you can say they have got regular shapes. They have got regular shapes, or you can say regular geometric shapes, right? Whereas your amorphous solids, they have got irregular shapes. They have got irregular shapes. They do not have any regular geometric shapes at all. This was all about the basics, right, of your solids. On the basis of arrangement, we classify solids into two types. I hope you got it properly, okay? Now, dear students, these crystalline solids basically we have to discuss in detail, right? So let me mark the heading over here as crystalline solids. We have to understand, we have to do it in detail. So let me start with a simple statement. Let me start with a simple statement. Crystalline solids forms a crystal lattice. Crystalline solids, they form a crystal lattice. What is meant by that? What is meant by that? Crystalline solids, what do? They form the crystal lattice. Now, what is a crystal lattice? From here, you have to imagine things. What is a crystal lattice? How do you define the crystal lattice? See guys, when I talk about the crystal lattice is basically the regular arrangement. It is the regular arrangement of constituent particles in three-dimensional space, inside the solid. What is meant by that? You know, when I talk about the crystalline solids, in case of crystalline solids, the constituent particles inside the crystalline solid, they will have some regular arrangement, right? That regular arrangement of constituent particles inside the crystalline solid in 3 dimension, that's something which you call as crystal lattice. What is meant by that? Have a look. Let's understand it. For example, I'm making one cube over here. Let's say I'm making one cube over here. This is the cube which I'm drawing, right? Let's say at every corner I'm keeping a constituent particle. At every corner I'm keeping a constituent particle. Let's imagine we have got a solid which is made up of constituent particles, right? Perfect. Which solid I'm talking about? Crystalline solid. Inside the crystalline solid, what you'll observe? You'll observe a regular arrangement of constituent particles. Let's imagine one regular arrangement of constituent particles inside the crystalline solid is like this. See, let's say these are the constituent particles which are present inside the crystalline solid and having this kind of the arrangement. If you look at this particular arrangement, can I say the distance from here to here is same as that of distance from here to here? Absolutely. Which is same as that of distance from here to here. Can I say this particular arrangement which I'm showing you over here, this is a regular arrangement of constituent particles in 3-dimensional space inside the crystalline solid? Absolutely. Whenever you say a regular arrangement of constituent particles in 3-dimensional space inside the crystalline solid, you call this particular regular arrangement as the crystal lattice. Now, it's not important that your crystal lattice will always look like this. The arrangement is always going to be the same. It's not like that. The arrangement can be like this as well. This can be the arrangement as well. This can be the arrangement as well. I'm showing you one random arrangement over here so that you can understand it properly. Right? Look at this particular structure. Should I be calling this as the regular arrangement of constituent particles or irregular? You tell me in the chats. You tell me in the chats quickly. Should I be calling this particular structure, should I be calling this particular arrangement as the regular arrangement or irregular arrangement? What do you think? Should I be calling this as regular or irregular arrangement? It's again the regular arrangement of constituent particles. It's again the regular arrangement of constituent particles inside the crystalline solid. And any regular arrangement of constituent particles in 3-dimensional space inside the crystal, that's something which you call as crystal lattice. So this is one type of crystal lattice. This is one more type of crystal lattice. Okay. So what is a crystal lattice? Crystal lattice is nothing. It is just the regular arrangement of constituent particles in three-dimensional space inside the solid. That's all. The arrangement can be of different types. Two arrangements I have shown you over here. Perfect. Now, dear students, when I talk about the crystal lattice, when I talk about the crystal lattice is basically made up of what? It is made up of unit cells. Crystal lattice is made up of what? It's made up of unit cells. Now, from here, we are going to start the chapter actually. Till now, whatever I was teaching you, that was complete basics. From here now, we are going to start the chapter. Crystal lattice, it's formed of what? It's formed of unit cells. Now, what is a unit cell? What's a unit cell? Unit cell is defined as the basic structural unit. It is the basic structural unit which upon repeating along all the axes generates the complete crystal lattice. Understand what the unit cell is all about. The basic structural unit which upon repeating along all the axes generates the entire crystal lattice. What is meant by this? Dear students, it's very simple. Just imagine the room in which you guys are sitting right now. Okay? Imagine the room in which you guys are sitting right now. Some people are saying, sir, speed up, slow down. You don't worry about that. I know when to speed up, when to slow down. Okay? Don't focus on that. Focus on something which I'm teaching right now. Don't tell me speed up or something. Understand what I'm saying. See, when I talk about the unit cell, how you can understand this unit cell first of all? My dear students, imagine the room in which you guys are sitting right now. Okay? Imagine that room is cubical in shape. Imagine that room is cubical in shape. Okay? Now, if I say, can I say the room is basically made up of bricks, right? As simple as that. The room in which you guys are sitting in right now, that room is cubical in shape. That's something which I'm imagining, right? And dear students, room is made up of what? It's made up of bricks. Can I simply say one thing? On repeating one particular brick along x-axis, along y-axis, along z-axis. If I repeat a brick along x-axis, y-axis and z-axis, can I say I'll get the entire room? Can I say I'll get the entire room? The room in which you guys are sitting right now, let's imagine that's cubical in shape, right? That room is made up of bricks. On repeating one particular brick along x-axis, y-axis and z-axis, I generated the entire room. So that brick is basically the basic structural unit, which upon repeating in all the directions, generates the entire room. That brick I'll be calling as the unit cell. So imagine the room in which you guys are sitting right now. Imagine the room is the crystal lattice and the bricks are what? Bricks are the unit cells, right? Bricks are the unit cells. I hope you got it. Let's make it a little more clear. So over here, I'm making one diagram. From this particular diagram, you'll understand it properly. I'm damn sure about that. So understand it, what I'm exactly going to say. Have a look, have a proper eye on this particular diagram. Have a proper eye on this particular diagram. What do you see? Do you see one bigger sized cube? Yes, you can see one bigger sized cube. This whole cube, this bigger sized cube which I mentioned over here, let's call this bigger sized cube as the crystal lattice. Let's call this as crystal lattice. Do you see this bigger sized cube is actually made up of small cubes, right? Let's imagine from here to here, it's your ground floor. From here to here, it's your ground floor. And from here to here, let's imagine it's the first floor. From here to here, let's imagine it's the ground floor. From here to here, let's imagine it's the first floor. In the ground floor, how many small cubes do we have? In the ground floor, how many small cubes we have? Imagine one small cube like this. Imagine one very small cube like this. This is one small cube which I'm representing over here. Look at this particular small cube, right? Can I say on the side of the small cube, there is one more small cube like this? Just behind it, there is one more small cube. So in the ground floor, how many small cubes do you see? In the ground floor, I can see 4 small cubes. 4 small cubes in the ground floor. Similarly, in the first floor, how many small cubes do you see? You will see again 4 small cubes, right? So can I say this bigger cube, this crystal lattice, it is basically made up of 8 small cubes? Yes, it's made up of 8 small cubes, right? Can I say something like this? Can I say something like this? Your crystal lattice, this crystal lattice, it's right now made up of 8 small cubes. I can simply say one thing. On repeating this small cube, along x-axis, along y-axis, along z-axis, the whole crystal lattice got generated. Can I say something like that? Absolutely. On repeating one small cube along x-axis, along y-axis, along z-axis, the whole crystal lattice got generated. So I'll be calling this very small cube over here as the unit cell. So this is my unit cell. So what is a unit cell? Now you can understand it. Unit cell, it is the basic structural unit which upon repeating along all the axes generates the entire crystal lattice. That's all, right? Yes? Perfect. Now, dear students, these unit cells we have to analyze in detail. So first of all, I'll give you the idea about the different types of unit cells. Right? Some basic idea I would want to give you about the unit cells. Then we'll discuss about these unit cells in detail. Okay? So let me give you first of all the basic idea about the different types of unit cells which we have to study. Types of unit cells. The first type of unit cell which we have to discuss, that's what you call a simple cubic unit cell, SCC, or you call it as the primitive unit cell as well. The first type of unit cell, simple cubic unit cell, primitive unit cell. Second one is what we call as body-centered cubic unit cell. This is one more unit cell which we have to discuss, body-centered cubic unit cell. One more unit cell which we'll be discussing, that is going to be your face-centered cubic unit cell. Face-centered cubic unit cell. Okay. There are a few basic things which I would want you guys to remember about these unit cells, right? And then we can talk about these unit cells in detail. First point. In case of simple cubic unit cell, the first point, what you'll observe the constituent particles. They'll be only present at the corners of the cube. First point about the simple cubic unit cells. The constituent particles, you'll find that these constituent particles will be only present at the corners of the cube. Point number 1. Point number 2. The contribution of the corner particle towards the unit cell is always 1/8. The contribution of the corner particle towards the unit cell, that will be always 1/8 towards the cubic unit cell I'm talking about. Okay. What does it mean? You'll get the idea in some time. At the same time, in case of simple cubic unit cell, the adjacent corner particles touch each other. Now, what is meant by all these things? Let's have a look. See, first of all, how this simple cubic unit cell looks like. So, first of all, I'm drawing a cube over here. This is your cube, right? This is a cube. And in this particular cube, what I'm going to do exactly, I'll keep the constituent particles exactly at the corners. Let's say I'm keeping the constituent particles where? I'm keeping the constituent particles exactly at the corners of the cube. Perfect. My dear students, in this particular unit cell, do you see the constituent particles are only present at the corners? Absolutely. Whenever you see such kind of the unit cell in which the constituent particles are only present at the corners, you will be calling this particular unit cell as the simple cubic unit cell. That's point number 1, right? That's point number 1. Yes, perfect. Now, point number 2. The contribution of the corner particle towards the unit cell, that's 1/8. What does that mean? If you talk about this particular corner particle, this corner particle it won't be completely inside this cube. Only 1/8 part of this corner particle you'll find inside the cube. Only 1/8 part of this corner particle you'll find inside the cube. Only 1/8 part of this corner particle you'll find inside the cube, right? You take any corner particle, the whole corner particle won't be inside the cube. Only 1/8 part of the corner particle will be inside the cube. That's all. And at the same time, one more thing, adjacent corner particles touch. Which particles do I call as adjacent corners here? Which particles do I call as adjacent corners here? If you look at this particular particle and this particular particle, I'll be calling them as adjacent corner particles. For example, if I talk about this one and this one, again they are adjacent corner particles. And in case of your simple cubic unit cell, the adjacent corner particles touch each other. Okay? So this one and this one, they'll be touching each other like this. Let's say this is one corner particle and this one I'm representing like this. So this is one more corner particle, so they'll be touching each other. So do remember, in case of simple cubic unit cell, just remember 3 or 4 things. 1. Constituent particles present only at the corners, number 1. Number 2, the contribution of corner particle towards the unit cell, 1/8. Adjacent corner particles touch, and this is how the unit cell looks like. That's all. This is just the basics which I'm teaching you. We are going to analyze it in detail in some time. Let me once in the chats if it is clear. Give me some thumbs ups in the chats, people, everyone. Give me some thumbs ups in the chats if it is clear to everyone. Let's talk about the body-centered cubic unit cell now. In case of body-centered cubic unit cell, what you'll find the constituent particles. They'll be present at the corners of the cube and at the center of the cube. Corners of the cube and at the center of the cube, right? Number 1. Number 2, in case of body-centered cubic unit cell, do remember body diagonal particles. They touch each other. Now, what is meant by all this? Have a look properly. This again very simple. So, for example, I'm drawing a cube over here. This is the cube which I'm drawing. Okay, this is the cube. Now, first of all, I'm going to keep the constituent particles at every corner. I'm keeping the constituent particles at every corner of the cube. Apart from the corners, I'm going to keep one particle at the center of the cube. Whenever you see this kind of the unit cell, in which the constituent particles will be present at the corners, and apart from the corners, one particle will be present at the center of the cube, you'll be calling this particular unit cell as the body-centered unit cell, right? Body-centered cubic unit cell. Perfect. Point number 1. You know the contribution of corner particle. How much is that? That's 1/8. That means 1/8 of the corner particle will be inside the cube, right? What about this particular particle? This particular particle is wholly and solely completely inside the cube only. So if I ask you about its contribution towards the cubic unit cell, that's 1, right? Now, dear students, I have written something over here. Body diagonal particles touch. So for that, you have to understand it like this. See, first of all, if I talk about this particular front face, let me talk about this particular front face and select this particular corner. Right? So I took the front face. Now, opposite to front face, we have got the back face. This is the back face. Let me select this corner of the back face. If I join these two particular corners, this line which I am drawing over here, this is something which you call as body diagonal. Right? This is something which you call as body diagonal. And when I talk about BCC, in case of BCC, all the particles lying along body diagonal, they'll be always touching each other. Now, if I talk about this particular body diagonal, which all particles lie along this particular body diagonal, I must say this particle, and this particle, they lie along the same body diagonal, right? The body diagonal crosses through them, right? So these 3 particles, they'll be touching each other always, right? And how exactly you're going to represent it? This particle you're going to represent like this. The one at the middle, like this. The one here, like this. So these 3 particles, they'll be touching each other in case of BCC. Let me know once in the chats, everyone, if everything is super clear till here. Let me know in the chats quickly. with the thumbs ups. With the thumbs ups. And I want this live like count to reach 2.5k right now. And the ones who have not subscribed to the channel yet, do subscribe to the channel right now. Right now means right now. Yeah? Perfect? Done? Done quickly. Wonderful. Now similarly, there are a few more things which you need to know about the FCC as well. In case of face-centered cubic unit cell, the constituent particles, they are present at the corners of the cube. Apart from the corners, they are present at the face centers as well. They are present at the face centers as well. Point number one. Point number two, face diagonal particles touch each other. Face diagonal particles, they touch. They touch. How exactly I'm going to show this? Understand. For example, I'm going to make one more cube like this. Right? And what exactly I'll be doing? I'll keep the constituent particles at every corner. I'm keeping the constituent particles at every corner. And apart from the corners, I'm keeping the constituent particles at the face centers as well. Look at the top face, center of the top face, center of the bottom face, center of the side face, center of the side face, center of the front face, somewhere here, center of the back face, somewhere here. My dear students, whenever you see this kind of the structure, in which the constituent particles are present at the corners, apart from the corners, they'll be present at the center of each face, you'll be calling this particular unit cell as the face-centered cubic unit cell. Right? This is something which you call as FCC, face-centered cubic unit cell. Number one. This is your FCC. Particles are present at corners and face centers. Now, the contribution of corner particle towards the unit cell, that's 1/8. And contribution of face-centered particle towards the unit cell, that's 1/2. That's half. Right? Contribution of the face-centered particle towards the unit cell, that's 1/2. Perfect. Now, dear students, one more thing. I have mentioned something over here. Face diagonal particles, they touch each other. Face diagonal particles, they touch each other. Face diagonal, let's have a look. If you talk about the top face, right? If I talk about this particular top face, if I join these particular centers, if I join these particular particles, I'll be calling this particular line over here, which I'm representing with green color, I'll be calling it as the face diagonal. All the particles lying along the face diagonal, they touch each other, right? So, if this is the face diagonal, which all particles lie along this face diagonal? I would say this one, and this one. They lie along the face diagonal, so they will be touching each other. So, my dear students, I must say this particular particle, the one here and the one here, they'll be touching each other. So, this was complete basics related to the 3 different unit cells which we have to discuss in detail, right? I want you guys to remember and understand everything over here. Perfect. And guys, just focus on the session. No more talks, yeah? Okay? Focus on the session. Is everything super clear till here? Quickly let me know in the chats with the thumbs ups. Then I can move on. Let me know quickly in the chats if every single thing is clear. Quickly. Yes or no, quickly with the thumbs ups, yaar. Quickly. Perfectly done. I want everyone to say it. The chat box has to continuously move today. Right? The chat box has to continuously go up. Perfecto. Perfecto, guys. Wonderful. All right. So this was about the quick basics about the unit cells. Now, it's going to be analysis of the unit cells. And whatever point I'm going to write on the screen from now on, that's going to be a question basically. That's going to be a question. Analysis of unit cells. Analysis of unit cells. Whatever things I'll be mentioning on the screen from now on, that everything is going to be a question. So first of all, we are going to analyze simple cubic unit cell in detail. Let's try to analyze the simple cubic unit cell in detail. Few points about simple cubic unit cell that you already know, right? The constituent particles, they'll be present only at the corners. So let me draw the simple cubic unit cell first. I've drawn a cube, right? And I'm keeping the constituent particles at all the corners. At all the corners, as you can see. So this particular unit cell, I'll be calling as the simple cubic unit cell. As simple as that, right? This is the simple cubic unit cell. Now, dear students, the distance from here to here, I'm calling this particular distance as the edge length. I'm calling this particular distance as the edge length. And edge length, I'm representing by A. Edge length, I'm representing by A, number one. Number two, let's assume that the radius of each constituent particle. Let's imagine that the radius of each constituent particle is R. R represents the radius of each constituent particle. Okay. Now people, the first point, which I'm going to share with you. What is that? The first point about simple cubic unit cell. That's what you call as effective number of particles. That's what you call as effective number of particles. Effective number of particles, or you call it as the rank of the unit cell as well. You call it as the rank of the unit cell as well. And this effective number of particles or rank of the unit cell, I'm representing with Z. Now, first of all, how do we calculate this Z? How do we get the value of Z? How do we get the value of Z? Have a look, understand. In case of your simple cubic unit cell, as you all must be knowing, the constituent particles, they're only present at the corners of the cube, right? If I ask you, what is the contribution of the corner particle? You'll say 1/8. How many corner particles in total we have? We have 8 corner particles. So multiplied it with 8. The value comes out to be 1. So I'll say 1 particle per unit cell. 1 particle per unit cell. Perfect. So effectively, in the simple cubic unit cell, you'll find only 1 particle. Because I told you, if you talk about any corner particle, the whole corner particle won't be inside the cube. Only its 1/8 part will be inside the cube. Only its 1/8 part will be inside the cube. Only its 1/8 part will be inside the cube. So effectively, there will be only 1 particle forming this particular unit cell. As simple as that. So Z value for SCC, that's 1. Point number 1. Point number 2. Point number 2 is basically the relation between edge length A and radius of the constituent particle. Edge length A and the radius of the constituent particle, right? Now, what is this? What is the relation between A and R in case of simple cubic unit cell? You guys are going to tell me. Few minutes back, I told you, in case of SCC, the adjacent corner particles, they touch each other. Well, dear students, if you talk about this particle and this particle, they are adjacent corner particles. So absolutely, they'll be touching each other. And how exactly these two particles will be touching? How exactly these two particles will be touching? Or if I show you like this particular particle and this particular particle, again, they are adjacent corner particles. So they will be touching each other. So let me show it here. So this is one particle. Similarly, this is one more particle. They'll be touching each other. Perfect. Now, you know the distance from here to here, it's A. Can I say this A is actually R plus R? A is equal to R plus R. That means A is equal to 2R. So a quick simple relation between A and R in case of SCC. So A is equal to 2R. One more point which I would want you guys to remember. One is effective number of particles. One, relation between A and R. A is equal to 2R. Perfect. Now at the same time, dear students, one more thing. The third point, that is really important. The third point, that's really important. What is the third point? The third point is something which you call as packing efficiency. Which you call as packing efficiency. So first of all, I'll show you how to calculate packing efficiency. Then I'll make you understand what this packing efficiency is all about. Right? Okay? Packing efficiency. Packing efficiency is calculated in this manner. Volume of constituent particles inside the unit cell divided by volume of the unit cell multiplied by 100. What is meant by this? Let's try to understand. First of all, I'm making a simple cubic unit cell again. In which the particles are only present at the corners. Perfect. Let's say the edge length of this particular cube is A. Okay. Now, what do I need to calculate? I need to calculate the packing efficiency. Let's try to calculate it, then let's try to understand it. Okay. Now, people see volume of constituent particles inside the unit cell. Let's say I have this constituent particle here. Let's assume the radius of this constituent particle is R. Okay. If I ask you what is the volume of this whole constituent particle, volume of this whole constituent particle will be 4 by 3 pi r cube, right? If I write something like this, 4 by 3 pi r cube, what is this 4 by 3 pi r cube? This is the volume of whole constituent particle, this particular constituent particle. But if I ask you whether this particle is completely inside the cube, no. This particle is not completely inside the cube. Only its 1/8 part is inside the cube, right? So, if I multiply it with 1/8, what do I get? What is this term all about? I would say this term, it is basically that volume of the corner particle which lies inside the cube. It is basically that volume of the corner particle that lies inside the cube. And similarly, how many such particles we have? We have 8 particles like that. So if I ask you now, what about this whole term? I would say this whole term, it gives me that volume of all the constituent particles which lies inside the cube. And I'm going to divide it with what? I'm going to divide it with the volume of the unit cell. Since unit cell is cubical in shape and volume of cube, that is side cube, so A cube multiplied by 100. Few minutes back only I told you A is equal to 2R. A is equal to 2R in SCC. So it's going to be 2R ka cube. It's going to be 2R ka cube. Perfect. So dear students, R cube gets cancelled out. When you put the exact value of pi and everything, you'll be getting 0.524 multiplied by 100. Something like this. Okay. When you solve it, the value comes out to be 52.4%. So this 52.4%, what do I call it as? We call it as the packing efficiency. And this 0.524, this is something which you call as packing fraction. Now the point is, what is meant by this? What is meant by this? 52.4%, this is something which we call as packing efficiency. It means out of the total volume of the cube, 52.4% volume is covered by the constituent particles, right? Out of the total volume of the cube, 52.4% volume is covered by the constituent particles. What about the rest of the volume? The rest of the volume will be empty. And that empty space is something which you call as voids. So, if I ask you, what about the percentage of voids? What about the percentage of voids? It's going to be 100 minus 52.4, right? 100 minus 52.4, which comes out to be 47.6%. So, I would say out of the total volume of the cube, 47.6% volume is going to remain empty. And that empty space is what you call as voids. Perfect. Done and dusted. Let me know quickly in the chats. Let me know quickly in the chats if everything seems clear. Everyone. Everyone, guys. Everyone. Everyone. I'll be teaching you SCC in detail. All the other FCC and BCC, right? I'm just going to give you the data which you are going to remember. This is something which I'm teaching in detail. Okay, so that you can understand it, how we get the values. Quickly guys, give me some thumbs ups in the chats. And what is this? I can see the likes only 2.4k and subscribers have not increased yet. That's not done guys. I'm giving you 30 seconds to increase the subscriber count. Quickly. Quickly. You need to do that. Yeah? Alright. Moving on to the fourth point. This is again important and please keep an eye on this. Fourth point. What is that? That's coordination number. That is coordination number. Coordination number in case of simple cubic unit cell. How do we define the coordination number first of all? Coordination number is a simple term It is defined as the number of immediate neighbors. The number of immediate, or I must say, the number of nearest neighbors. The number of nearest neighbors which a particle has. Which a particle has, comma, equidistant from it. Equidistant from it. So what is meant by the coordination number? Let's understand it first of all. See guys, for example, I'm taking one scenario like this. Let's say I've got Na positive here. Let's say this Na positive, okay? I'm drawing a circle. Let me keep one Cl negative here and one Cl negative here, one here and one here. Can you tell me how many neighbors this Na positive has right now? Can you tell me how many neighbors this Na positive has right now? It has 4 neighbors right now, correct? All these 4 neighbors, are these equidistant from it? Yes, they are equidistant from it. All these 4 neighbors, are these the nearest neighbors of Na positive? Yes, they are the nearest neighbors. The number of nearest neighbors which a particle has equidistant from it, that defines its coordination number. So I must say the coordination number of Na positive in this particular scenario, that's 4, right? Now, in the same scenario, I'm drawing one more circle. Let me keep one Cl negative here, one Cl negative here. Now tell me how many neighbors Na positive has. No doubt, Na positive now has 6 neighbors. Na positive now has 6 neighbors. But out of 6, how many are the nearest neighbors? How many are the nearest neighbors? I must say there are 2 which are the nearest neighbors. 2 are the nearest neighbors now in this particular scenario. Perfect. The number of nearest neighbors which a particle has equidistant from it, that's coordination number. So coordination number in this particular scenario now is equal to 2. So I hope you just got the concept of what is coordination number. I hope you got the concept of what is coordination number. So dear students, let's have a look exactly how coordination number in case of SCC is calculated. Have a look. Have a look guys. First of all, this is one cube which I'm drawing. I'm drawing a simple cubic unit cell. Understand properly, please. Please take a note of it properly. This is something which is very important. So, this is a simple cubic unit cell over here, in which the particles are only present at the corners, right? Now, for example, let me underline this particular particle. Let me underline this particular particle. I need to find its coordination number. I need to find its coordination number. That means I need to see the number of nearest neighbors which this particle has, right? And we know in case of simple cubic unit cell, the adjacent corner particles touch each other, right? The adjacent corner particles touch each other. So my dear students, I would say this particle and this particle, they'll be touching each other. And the particles touching, they are the closest ones. They are the closest ones, right? So basically, if I need to find the coordination number of this particular particle, I have to calculate all the adjacent corner particles which must be touching this particular one. Okay? So, this particular particle and this one, they'll be touching, right? They'll be touching each other. Perfect. Similarly, on side of it, there'll be one more cube whose top face will be like this, right? There'll be one more cube on the side of it whose top face will be like this. And over here, you can find one more particle. And I must say this one and this one, they'll be also touching each other, right? Adjacent corners only. Perfect. Now, similarly, if you talk about this particular edge, I would say this particular particle and this one, they are again the adjacent corner particles. Now, behind this particular cube, you'll find one more cube whose top surface will be this one, right? And this is one more adjacent corner particle of it, which will be touching. Perfect. Now, similarly, if you talk about this particular edge, this is the particle, which is the adjacent corner particle. Now, similarly, on the top, there'll be few more, right? Here you will find one more particle, this one and this one. They'll be touching each other. They're all adjacent corners. Now, people, if I ask you, how many particles are touching this particular particle simultaneously? 6 particles are touching this particular particle simultaneously, so its coordination number is 6. Got it? Perfect. Let me know once in the chats if everything seems clear. Let me know everything in the chats. Quickly, everyone. Everyone quickly in the chats here. So, I hope you got to know how I got all these things, right? Perfect. All right. Now, all the other unit cells, we are not going to discuss them in detail. I'm just going to give you the values. Like we discussed about SCC. The value of Z, a relation between A and R, packing efficiency, voids, and coordination number. All these points directly I'm going to give you now about all the other unit cells, which you just need to remember. Anything can be asked out of them. Okay, so let me give it to you. See guys, the second is BCC, body centered cubic unit cell. The first point related to body centered cubic unit cell, the value of Z, effective number of particles. If I talk about the effective number of particles, Z value for BCC, that's 1. Point number 1. Relation between A and R. R is equal to root 3A divided by 4. Second point. Packing efficiency. Packing efficiency will be 68%. Voids percentage. Percentage of voids will be 32%. Coordination number will be 8. That's all. The way we did for SCC, in the similar way I'm doing it for BCC. And in the similar way, I'm going to write it for FCC as well. In the similar way, I'm going to write it for FCC as well. Yeah? I'm going to write it for FCC as well. For FCC, the value of Z is 4. R is equal to A divided by 2 root 2. What is A? A is the edge length. Packing efficiency is equal to 74%. Void percentage. Percentage of voids will be 26, right? Coordination number over here will be simply 12. Perfect. These are the 3 unit cells and their parameters which I would want you guys to remember. By the way, I'm sorry, this is not Z is equal to 1, this Z is equal to 2. Okay? Oh, got it. My bad. Perfect, guys? All cool? And for SCC, which we already discussed, for SCC, Z value is 1. R is equal to A divided by 2, right? Packing efficiency is equal to 52.4. Percentage of voids is equal to 47.6. And coordination number is equal to 6. Now, I'm just going to ask you one question. Tell me the order of packing efficiency. Tell me where do you find the efficient packing? Tell me where do you find the efficient packing? Tell me where do you find the efficient packing? In case of FCC, the packing efficiency is maximum. So efficiently packing has happened in FCC, followed by what? Followed by your BCC, followed by your SCC. Done and dusted? Done and dusted quickly? Okay. Perfect, guys. Perfect. So, let's try to do few basic questions so that you can understand how all these concepts are applied in the questions, okay? Let's try to frame certain questions and you guys are going to solve them, okay? Before solving the questions, there is something which I would want to mention. When I talk about the corner particle, the contribution of the corner particle towards the unit cell, that's 1/8. And how many corner particles are there in the cube? 8 corner particles. If I talk about face center from now onwards, contribution is 1/2. And in total, there are 6 face-centered particles. When I talk about body-centered particle from now onwards, contribution is 1, and there is only 1 body-centered particle. As simple as that. Similarly, if I talk about the edge-centered particle, the contribution is 1/4, and there are in total 12 edge-centered particles. So these 4 things I would want you guys to remember. Okay? So the first question, for example, I'm giving you the simplest among all. Let's say you have got a solid which has got 3 types of constituent particles in it. You have got a solid which has got 3 types of constituent particles, A, B and C. Let's imagine A particles are present at the corners of the cube, B particles are present at the face centers, C particles are present at the body centers. I'm asking you, what should be the empirical formula of this solid? What should be the empirical formula of this particular solid? How to solve these sort of questions? They are frequently asked in your examination. And it's simple. See, A particles are present at the corners. Contribution of corner particle is 1/8. In total, there are 8 corner particles. So multiplied it with 8. Done, understood. B particles are present at face centers. Contribution of face centered particle 1/2. In total, there are 6 face centered particles. Body centered. Contribution is 1. There is only one body centered particle. When you solve it, the value comes out to be 1 here. It comes out to be 3. This value comes out to be 1. So the formula has to be A1, B3, C1. Simplest of all the questions. Yes. Now let me change the question a bit. Let me see if you can do it or not. I'm going to change the question. The question is like this. You have got a solid A. You have got a solid in which there are 4 types of constituent particles. Let's say A particles are present at the corners of the cube. B particles again at face centers. C particles are present at the edge centers. And D particle is present at the body center. I'm asking you about the formula. What do you think? What do you think about the formula for this? Empirical formula, quickly. It's simple again. A particles are present at the corners. Contribution of corner is 1/8. In total, there are 8 corner particles. Face-centered particle, its contribution 1/2. In total, there are 6 face-centered particles, right? Edge center, contribution is 1/4. In total, there are 12 edge-centered particles. Body center, contribution is 1. In total, there is 1 body-centered particle. Now solve it. The question is done and dusted. Solve it. This is 1 here. This is 3. This will be 3. And this will be 1. So what should be the formula? The formula should be A1, B3, C3 and D1. You can do these sort of questions. Say yes or no in the chats quickly. Then only I can increase the level of the questions. Say yes or no in the chats quickly. If you can solve these sort of questions from now on. Let me know in the chats with the thumbs ups. With the thumbs ups. With the thumbs ups. Yeah? Perfect. Now guys, solve this one. A particles are present at 50% of the corners. B particles are present at 25% of the face centers, edge centers, body centers. How you are going to do it? Let's see. Let's see guys. First thing, as you know, 50% means 50 by 100, matlab 1/2, half. 25% means 25 by 100, 1/4. 75% means 75 divided by 100, 3/4. Something which you all know. Yeah? Now how to solve these questions? Have a look. A particles are present at 50%. 50% means half. 50% means half. 50% of what? Corners. Corner contribution is 1/8. In total, there are 8 corner particles. Done and dusted. Khatam. 25%. 25% means 1/4. Face center contribution 1/2. In total, 6 face centered particles. Done and dusted. Edge center. Edge center. Contribution 1/4. How many edge centered particles? 12 edge centered particles. Body center. Contribution 1. How many? Only 1. Yeah? Now kill it. This is going to be 8. It cancelled. The value is 1/2. This is going to be 3 divided by 4 when you solve it. 2, 1, 2, 3. 3 by 4. This value is going to be 4, 1, 4, 3. And this is 1. Now as per this, the formula has to be A 1/2, B 3/4. But have you seen any formula in the fraction? No. No formula will be there in the fraction. So look at the denominators of all these. Look at the denominators. What do you see? The denominators are 2 and 4. The denominators are 2 and 4. So take the LCM of 2 and 4. So what is the LCM of 2 and 4? That's 4, right? LCM of 2 and 4 is 4. So I'm multiplying everyone with the LCM. Multiplying everyone with the LCM. This value comes out to be 2. This value comes out to be 3. This value will be 12. This value will be 4. So the formula has to be A2, B3, C12 and D4. Right? This has to be the formula of the compound. As simple as that. Quickly let me know in the chats if everything seems clear. Yes? Okay. The similar type of question, one more similar type of question I'm giving you, and then we'll move on to one more topic. Okay? One similar question. One similar question. The question is like this. You have got a solid in which you have got 3 types of constituent particles, A, B and C. Okay? I'm keeping A particles at the corners of the cube. B particles I'm keeping at the face centers. C particles I'm keeping at the edge centers. Now the question says, if two corner particles, comma 3 face centered particles and 2 edge centered particles are removed, what will be the formula of the compound? Can you give it a try? Can you give it a try? Guys, just be patient. We'll complete everything, okay? Just be patient. We'll complete everything. Just understand the things. This is something which you cannot do on your own. So just focus on stuff. Quickly, everyone. How do we exactly solve this one? How do we solve this one? First of all, A particles are present at the corners. What is the contribution of the corner particle? That's 1/8. Right? That's the contribution. How many corner particles do we have? How many corner particles do we have in total? 8. Out of 8, 2 corner particles are removed. So I'll be only left with 6. So multiply with 6. The left out particles. Similarly, dear students, B particles are present at face centers. Contribution of face centered particle is 1/2. Right? How many face centered particles we have in total? 6. Out of 6, how many face centered particles are removed? Out of 6, 3 are removed. So I'm left with only 3. Okay. Edge centers. Edge center contribution is 1/4. How many edge centered particles we have in total? 12. Out of 12 edge centered particles, we have removed 2. So I'll be left with 10. So multiplied with 10. So this value when you solve, this is 3/4. This is 3/2. This is 5/2. Correct? If I take the LCM of the denominator, LCM of the denominators, that comes out to be 4. So multiply this with 4, this with 4, and this with 4. So this 4 got cancelled. This value is 3. This is 6. This is 10. So the formula of this particular compound is going to be A3, B6, C10. Is this clear to everyone? Are you like 100% sure you can solve these sort of questions from now on? Say in the chats quickly. Say in the chats quickly. Everyone. Say in the chats. Everyone. Quickly in the chats. Yes? Done. Wonderful. Now, let's talk about something called as close packing. Let's talk about something called as close packing. This is again important from which question comes. Okay. My dear students, now what we are going to do exactly is we are going to arrange the constituent particles in such a way that the empty spaces between them, they should get minimized. One thing that should strike our mind, whenever from now onwards we are going to hear the term packing, hear the term close packing, that means we have to arrange the constituent particles in such a way that there should be minimum vacant spaces left between the particles. That's all you have to remember. That's all you have to remember. Yes? Have a look now. In case of close packing, only thing which we have to take into consideration, that the empty spaces between the particles, empty spaces should get minimized. Should get minimized. Empty spaces should get minimized. Yeah? Okay. So first of all, I'm talking about the close packing in 1D. This is the first type of packing, close packing in 1D. In close packing in one dimension, we are going to arrange the constituent particles along one of the axes. So as you can see, I've arranged the constituent particles along x-axis only. I could have done it along y-axis, I could have done it along z-axis as well, right? So dear students, in case of your close packing in 1D, the constituent particles are to be arranged along one of the axes in such a way that the empty spaces should get minimized. That's all. So, do you see, my dear students, in this particular packing, we have arranged the constituent particles along one axis, number one. Number two, the empty spaces between the constituent particles, they got minimized. Absolutely. So, this particular packing is something which I'll be calling as the close packing in one day, right? Now, if I select one particle here, tell me how many other particles are touching this particular particle simultaneously? How many other particles are touching this one simultaneously? 2. So, I must say its coordination number is 2. That's all. That's all you have to remember. That's all you have to remember, nothing else. Okay. Now, our actual thing, that is close packing in 2D and close packing in 3D, that's important. Okay. 1D is like, it's very simple. Yeah. Right. So, close packing in 2D and 3D is important. So, let's talk about the close packing in 2D. In case of close packing in 2D, we are going to arrange the constituent particles along two of the axes. Along two of the axes, or you can say along a plane. Along a plane. What is meant by that? Have a look. Understand. In case of close packing in 2D, your close packing in 2D, it's actually divided in two types. Say, over here, I arrange the constituent particles along one axis, right? And now, in case of close packing in 2D, I have to arrange the constituent particles along two axes, or along a plane. Now, there are two ways by means of which we can do it. First way is going to be called as AAA packing in 2D. Second one, that's going to be called as ABAB packing in 2D. Let's try to discuss them one by one. Let's have a look first of all on AAA packing in 2D. In case of AAA packing in 2D, the arrangement is simple. Let's say these are the constituent particles which I'm keeping here. I'm keeping the constituent particles in the first row. This is the first row of particles. Let me call this row of particles as row A, right? The first row of particles is called as row A. The second row of particles is also called as row A. That means the second row and first row, they are supposed to be identical. First row and second row, they are supposed to be identical. First row and second row, they are supposed to be identical. Now, as you can see, both the rows are identical, one below the other. So, I'll be calling this second row as row A again. So, this is going to be your third row, which is identical to that of first and second. This kind of packing over here, I'm calling as AAA packing in 2D. Whenever you see this sort of arrangement, this is arrangement along two axes, along a plane. So, you'll be calling this particular arrangement as AAA packing in 2D. Number one. Number two, just have a look on one more thing. Very simple and basic stuff I'm going to teach you. Dear students, if I select this particular corner, right? Or let me keep it like this. If I select this particular corner, this one, and this one. If I join these centers, what do I get? I get a square here, right? I got a square here, correct? I got a square here. If I repeat this square along all the sides, along all the axes, can I say the whole crystal gets generated? Absolutely, the whole crystal gets generated. So, can I say this particular square over here, it is a basic structural unit. This square is a basic structural unit, which upon repeating along x-axis and y-axis, which upon repeating along two of the axes generates the entire crystal. So, this basic structural unit I'm calling as, this basic structural unit which you can see over here, which I'm highlighting with the green color, this basic structural unit upon repeating generated the entire crystal. So, this basic structural unit I'll be calling it as unit cell, right? So, the first point which you need to remember, in case of AAA packing in 2D, the unit cell that gets generated is square in shape. The unit cell that gets generated is square in shape, number one, right? That is the reason why we call this particular packing as square close packing in 2D as well, right? That's the reason why we call this particular packing as square close packing in 2D. Perfect. At the same time, if you select any particle here, let's say I'm selecting a particle in the middle, can you let me know exactly how many other particles are touching this particular particle simultaneously? Check this particular particle. How many particles are touching this one simultaneously? 1, 2, 3, 4. 4 particles are touching this particular particle simultaneously, and the number of particles touching a particular particle simultaneously, that defines its coordination number. So coordination number of this particular particle here is 4. That's it. Yes? Clear? Coordination number is 4. And similarly, if you want to calculate the packing efficiency of this two-dimensional unit cell, the packing efficiency of two-dimensional unit cell over here, which we got, do remember it directly, it's going to be 78.54%. I'm not going to derive it, otherwise it's simple, right? It's a very simple concept basically, how to derive the packing efficiency in 2D. It is just instead of volume, we have to use the term area. Okay, so that's least important right now. Just do remember the packing efficiency of this particular unit cell. Clear? Similarly, in two-dimensional packing, we have got one more unit cell. We have got one more two-dimensional packing as well. That's called as AB packing in 2D. AB in 2D. In case of AB in 2D, how exactly you guys are going to visualize it first of all? How exactly you guys are going to visualize it? Let's have a look. Your AB packing in 2D. Let's try to visualize it. See. First of all, these are the constituent particles which I am keeping in the first row. Let me call this row of particles as row A, right? First row is called as row A. Now, second row is termed as row B. Second row is termed as row B. That means first row and second row, they are not supposed to be identical. What I'll be doing? I'll be keeping the second row particles in the depressions caused by the first row. Let's say these are the second row particles. Let's say these are the second row particles. Let me call the second row particles as row B. Let me call the second row particles as row B, because first row and second row, they are not identical, right? Now, dear students, the third row I'm calling again as row A. So, the third row particles will be just below the first row particles. They'll be just aligned with the first row particles, like this. I'm calling this again as row A. Whenever you see this kind of the packing, you call this particular packing over here. You call this particular packing over here as AB packing in 2D. AB packing in 2D, right? Point number 1. Point number 2. For example, I'm taking the center of this particular particle, center of this one, center of this one, center of this one, and this one. Let me join them. So, what is the structure which I got over here? Do you see I got one hexagon? Can I say, on repeating this hexagon along all the sides, can I say on repeating this particular hexagon along all the sides, can I say I'll be generating the entire crystal, right? So I would say this hexagon is the basic structural unit which upon repeating along all the axes generates the entire crystal, right? So I would say the unit cell that got generated in this particular packing, that's hexagonal in shape. Hexagonal unit cell. That's why this particular packing is also called as hexagonal closed packing in 2D. Perfect. At the same time, if I ask you about the coordination number, what about the coordination number of each particle? Just look at it. Look at this particular particle and tell me how many other particles are touching this particular particle simultaneously. 1, 2, 3, 4, 5, 6. 6 particles are touching this particular particle simultaneously. So coordination number over here is going to be 6. And if you ask me about the packing efficiency approximately it is 91%. Approximately it's 91%. Greater than 90, less than 91. Okay, you can remember this data, right? No need to derive it at this particular point of time. Is everything clear related to your two-dimensional packing? Is everything clear, dear students? Quickly. Let me know with the fire symbols. Everyone. All clear till here? All clear till here? Quickly, let me know in the chats. Perfect. Perfect, guys. Good job. Now we have got close packing in 3D as well. Again, close packing in 3D, I'll tell you how to remember it. right? We are not going to the details. We are only going to see those things which are asked basically, in the examination. Now look at it. In case of close packing in 3D, we have got the first step of packing as AAA packing in 3D. AAA packing in 3D. Then we have got AB packing in 3D. AB packing in 3D. Then we have got ABC packing in 3D. These are the three packings which we have to do, right, when we talk about the close packing in 3D. Perfect. There are few points, just few points which you need to remember. Not going into the details. Just remember one thing. When we talk about AAA packing in 3D, the unit cell that gets generated here, that is simple cubic unit cell. The unit cell that gets generated here, that's simple cubic unit cell. The unit cell that gets generated here, that's hexagonal unit cell. That's hexagonal unit cell in 3D. And the unit cell that gets generated here, that's face-centered FCC. So first of all, this can be the question asked. What different kinds of unit cells are generated during the packing? What different kinds of unit cells are generated during the packing? In the first one, it's SCC. In the second one, it's hexagonal unit cell. In the third one, it's FCC, face-centered cubic unit cell. And all the parameters which we discussed till now for SCC, those are actually the parameters for AAA packing in 3D. Do you know that? What do I mean by that? Z value for SCC, that's what. R is equal to A divided by 2. Packing efficiency is 52.4. Wide percentage is 47.6. Coordination number is equal to 6, right? All these parameters are basically the parameters of this particular packing. So if they ask you in the question, what is the packing efficiency in case of AAA packing in 3D? You'll directly say, in AA packing in 3D, the unit cell that gets generated, that's SCC, and in SCC packing efficiency is 52.4%. So the answer is 52.4, right? Yes? Simple? Of course, lunch break will be there, but lunch break will be there at 2, right? At 2, I'm going to give you first break. So till 2, you are going to be with me. First break will be at 2 p.m., the lunch break. Okay, in case of FCC, we have already discussed it. FCC. Tell me the parameters. The value of Z is 4. R is equal to A divided by 2 root 2, right? Packing efficiency is going to be 74%. Wide percentage is going to be 26. And coordination number here, it's going to be 12. Okay. Then in case of your hexagonal unit cell in 3D, do remember its parameters as well. The Z value, it's 6. Z value is equal to 6. Its packing efficiency is again 74%. Coordination number, or let me talk about the wide percentage. Percentage of wides here is going to be 26, right? And coordination number again here it's going to be 12. But this is hexagonal unit cell in 3D. And let me show you how this hexagonal unit cell in 3D looks like. Let me show you just how this hexagonal unit cell in 3D looks like. Let me just show it to you. This is how the hexagonal unit cell in 3D looks like. Okay, this is how your hexagonal unit cell in 3D looks like. Not going into the details, sorry, there's one more particle here. Not going into its details, just these things are sufficient. These things are enough to remember, because questions will be directly from them. Perfect? Now, dear students, now let's talk about something very important. What is that? That is going to be voids. Till now, I did not give you the idea about the voids, right? What are voids? Voids are the empty spaces. Voids are the empty spaces in between, right? Voids are basically the empty spaces. Voids are basically the empty spaces, the vacant spaces. The vacant spaces generated, during the arrangement of constituent particles. Vacant spaces generated during the arrangement of constituent particles. Now there are different types of voids present basically. right? Have a look. The first type of void is called as trigonal void. Trigonal void. The second one, that's what I'll be calling as tetrahedral void. Next one is called as octahedral void. And last one, that's called as cubic void. Octahedral and cubic. Okay. Now, my dear students, understand what I'm going to say exactly. Understand what I'm going to say exactly. This trigonal void, how come it's formed? Just have a look. Let's say this one particle here, one particle here, and one particle here. Do you see a vacant space and empty space got generated in the middle? Yes. Whenever you see this kind of the empty space getting generated in the middle, this empty space is something which you call as trigonal void. This vacant space in the middle is called as trigonal void. Since this void is formed when three particles are touching each other, right? So, do remember the number of particles which will be touching each other and generating the void, that defines the coordination number of the void. So, coordination number of this particular void is 3. Coordination number of this particular void is 3. As simple as that. Yes, number 1. Number 2, in case of your tetrahedral void, this particular void is generated when 4 particles touch each other. When 4 particles touch each other, like this. Let's say this one particle, this is one more here, this is one more here. Do you see a void got generated? Let's say this is the first layer of particles. In the second layer at the top, let's say there is one more particle. In the second layer at the top, there is, let's say, one more particle. So, this particular empty space, it got generated when 4 particles are touching each other. So, do remember the coordination number of this particular void, I'll be directly writing as 4, right? That void which gets generated after 4 particles touch each other, that void I'll be calling as tetrahedral void, and my dear students, its coordination number I'll be taking as 4. Similarly, if you talk about the octahedral void, how do we get it? This is how you get it. This one particle, one more particle, and one more particle, right? So, 3 particles in the first layer. Similarly, in the second layer, 3 more particles. In the second layer, 3 more particles. So, a vacant space and empty space gets generated in the middle, which gets formed when 6 particles touch each other. So, do remember its coordination number is 6. The coordination number of your octahedral void, that's taken to be 6. And similarly, this cubic void, its coordination number is taken to be 8. So, actually we have to discuss this tetrahedral and octahedral void in detail. This is something which is in our syllabus. Rest, we have got nothing to do with other voids, right? Rest, we have got nothing to do with other voids. Just remember, trigonal void is formed when 3 particles touch. Its coordination number is 3. Tetrahedral void, its coordination number 4. Octahedral void, its coordination number 6. And cubic void, its coordination number is going to be, 8. Yeah? Perfect. Now, dear students, there is something which is very important. What is that? Have a look. I'm writing one statement here. One simple statement I'm writing. Number of octahedral voids. Number of octahedral voids in a unit cell. Number of octahedral voids in a unit cell is always equal to the value of Z. Whatever will be the value of Z for the unit cell, same number of octahedral voids will be present in the unit cell. Number 1. Number 2, number of tetrahedral voids in the unit cell. Number of tetrahedral voids in the unit cell, it's always equal to 2 times the Z. So, I can categorically say number of tetrahedral voids present in a unit cell is equal to 2 times the number of octahedral voids. For example, I'm talking about, let's say, simple cubic unit cell. In case of simple cubic unit cell, you know the value of Z is 1. If the value of Z is 1, there will be 1 octahedral void. That means how many tetrahedral voids will be there? 2 tetrahedral voids. So, in total, there will be 2 plus 1, 3 voids in case of simple cubic unit cell. In case of simple cubic unit cell. Right? Yes? Just a second. Someone has started typing when will the session end. Is that? I think you're at the wrong place, yaar. I think you're at the wrong place. You should go have fun, yaar. Enjoy. There are a lot of days left till your NEET examination. Maybe you'll start preparing from 5th of May, yeah? 2 days are enough. Look here now. So first of all, number of octahedral voids in a particular unit cell, that's always Z. Number of tetrahedral voids is 2 times Z. And do remember, number of tetrahedral voids is always equal to 2 times the number of octahedral voids. Point number 1. If I talk about BCC, body-centered cubic unit cell, in case of body-centered cubic unit cell, do remember the value of Z is 2. If the value of Z is 2, that means there will be 2 octahedral voids. That means there will be 4 tetrahedral voids. So in total, there will be 6 voids in total in case of BCC. In case of BCC, right? Similarly, if I talk about FCC, in case of FCC, you know the value of Z is 4. If the value of Z is 4, so in total, you'll find 4 octahedral voids. You'll find 8 tetrahedral voids. So in total, there'll be total 12 voids in case of FCC. And similarly, my dear students, when you talk about the hexagonal unit cell in 3D, when you talk about the hexagonal unit cell in 3D, the value of Z is 6. So octahedral voids will be 6, tetrahedral voids will be 12, total voids will be 12 plus 6, 18. This is for first point which I would want you guys to remember. The first point which I would want you guys to remember. Calculation of total number of voids, total number of octahedral voids, total number of tetrahedral voids in different types of unit cells. Now in our syllabus, we have to discuss the voids in FCC in detail. That can be asked. Voids in FCC in detail. That can be asked. Right? Have a look what exactly I'm going to write. I'm going to write a simple statement, location of tetrahedral voids and octahedral voids in FCC. This is something which you need to know. This is something which you need to know. Let me first of all tell you, octahedral voids in case of FCC, they are present at the edge centers. They are present at the edge centers and at the body center. And at the body center. Similarly, if I talk about tetrahedral voids are present at 1/4 of each body diagonal. 1/4 of each body diagonal. Let's have a look how these voids are formed first of all and where exactly they are. Yes? So first of all, if I make a face-centered cubic unit cell here, I'm making a face-centered cubic unit cell. I'm going to make a face-centered cubic unit cell in which the particles will be present at the corners. Apart from the corners, the particles will be present at the center of each face. Front face, back face, right? Now, my dear students, there is something which is very important. What is that? See, yes, total number of voids means octahedral plus tetrahedral, okay? Now, first of all, I have mentioned one thing here that the octahedral void is present at the edge center and the body center. So, first of all, let's have a look exactly how in case of FCC, the octahedral void is present at the body center. How octahedral void is formed at the body center. My dear students, in the FCC, already I have told you in case of FCC, the face diagonal particles, they touch each other, and apart from that, the adjacent face centered particles also touch each other. What does that mean? If you talk about this particular face centered particle and this particular face centered particle, they'll be touching each other. These two will be touching each other. Similarly, this one and this one, they'll be also touching each other. This one and this one, they'll be touching each other. This one and this one, they'll be touching each other. So, in this particular plane, 4 particles are touching each other. In this particular plane, 4 particles are touching each other. 4 particles, right? And if these 4 particles are touching each other, so there will be a vacant space generated. On the top of that vacant space, you have got this particle. On the bottom of that, you have got this particle, right? So, can I say I got a vacant space generated? Vacant space got generated at the center of the cube. Do you see a vacant space getting generated at the center of the cube? And this vacant space which is getting generated at the center of the cube, how exactly? 4 on one plane, right? One above it, one below it. So this particular void, which got formed when 6 particles are touching each other, this void you are calling as octahedral void. And this octahedral void, where is it getting formed? At the center of the cube. Simple, basic, right? At the center of the cube, octahedral void got formed. Similarly, if you see how exactly octahedral voids are formed at the edge centers, how exactly the octahedral voids are formed at the edge centers. Let's have a look. Let's have a look. If I select this particular edge, that means at its center here somewhere, there should be a void. There should be a void. Which one? Octahedral void. Correct? Now, my dear students, in case of FCC, we know face diagonal particles touch each other. That means if you draw a line from here to here, it's going to be a phase diagonal, right? And all the particles lying along the phase diagonal will be touching. So this one and this one, these two will be touching each other. Similarly, this one and this one, they'll be touching each other because it's one more phase diagonal. Similarly, there'll be one more cube on this side. One more cube on this side. Perfect. There'll be one particle present at the center of this face as well. When you draw a line, it's again going to be a phase diagonal. So these two will be touching. Even these two will be touching. All the particles lying along the phase diagonal, they'll be touching each other. Perfect. So do you see this one touching, this one touching each other, this one touching each other, and this one touching each other. So there'll be one vacant space which would have got generated here. Perfect. Just down the vacant space, there is this particular particle, and above the vacant space, there'll be one more particle somewhere here. Right? So 4 particles are touching in one plane, one above, one below. Can I say again a vacant space got generated? And where this vacant space is being generated exactly? This vacant space is generated at this edge center. That's what I have written over here. In case of FCC, the octahedral voids, they are present at edge centers and body center. Correct? Yes? Is it clear? And at the same time, your tetrahedral voids, they are present at 1/4 of each body diagonal. What is meant by that? What is meant by that? Have a look. If I draw an FCC again, let me just draw a cube so that you can visualize it properly. Let me draw a cube so that you can visualize it properly. So dear students, imagine that this is the FCC. Imagine that this is the FCC, right? Imagine that this is the FCC. Now, if I join this particular corner with this one, I would say it's a body diagonal. It is about body diagonal, right? Now, let's do one thing. Just divide this body diagonal into 4 equal parts. Divide this body diagonal into 4 equal parts. So, this position I'm calling as 1/4 of body diagonal. Even this particular position I'm calling as 1/4 of body diagonal. And do remember, at 1/4 of each body diagonal, what you will find? At 1/4 of each body diagonal, you will find a tetrahedral void. So, on this particular body diagonal, here and here, 2 tetrahedral voids will be present. One here, one here. So, on one body diagonal, you will find 2 tetrahedral voids. And in a cube, how many body diagonals can we draw? In a cube, there are the possibility of 4 body diagonals. On every body diagonal, we can draw, there will be 2 tetrahedral voids. So, how many tetrahedral voids will be there in total? On one body diagonal, 2. So, on 4 body diagonals, 8 tetrahedral voids in total. 8 tetrahedral voids in total. Right? 8 tetrahedral voids in total. Perfect. Now, you must be thinking, since I wrote the total number of octahedral voids in FCC 4, how come we'll be getting the total octahedral voids as 4? See, I told you octahedral voids are present at edge centers. Contribution of edge center is 1/4. In total, there are 12 edge centers, right? And body center contribution is 1 body center. When you solve it, this is 3 plus 1, which comes out to be 4. So, in total, there will be 4 octahedral voids, and in total, there will be 8 tetrahedral voids in case of FCC. Let me know quickly if this is super clear to everyone. Quickly, guys. Quickly. Do remember this. This is very, very, very important, right? There is one more question which can be directly asked. Distance. Calculate the distance between 2 nearest octahedral voids. 2 nearest octahedral voids in case of FCC. This can be one question. Similarly, one more question will be, calculate the distance between 2 nearest tetrahedral voids in FCC. These can be 2 questions which can be asked. They have been asked in your JEE mains, right? So, they can be repeated in your NEET as well because they are very simple. So let's have a look exactly how you are going to tackle these questions here. Let's see exactly how you guys are going to tackle these questions. See guys, it's a very simple thing. Understand and analyze things. First of all, I'm going to draw one FCC. Let's imagine that the cube which I'm drawing here, let's imagine it's FCC. Let's imagine that this particular cube is FCC. Okay. And you know, in FCC, the octahedral voids, they are present at the edge centers and at the body center. So first of all, can I say at this particular edge center, there will be an octahedral void? At this particular edge center also, there will be the octahedral void, because at every edge center, you'll find the octahedral voids. Perfect. Let's call this particular edge length as A. This is A. Now the distance from here to here, it's going to be A by 2. The distance from here to here, it's again going to be A by 2. Now if you join these two, let's call this as point A, point B and point C, right? So I would say I got one right angle triangle. I would say using Pythagoras theorem, AC is going to be equal to under root of AB square plus BC square, right? Perfect. Hypotenuse square is equal to B square plus perpendicular square, nothing else. So it's going to be under root of AB is going to be A by 2, so it's A by 2 ka square plus again A by 2 ka square. So this is going to be under root of A square by 4 plus A square by 4, 2 times A square by 4, right? Which is going to be A square by 2, right? It's going to be under root of A square divided by 2, or you can say it's going to be A divided by root 2. Do remember this particular value directly from now onwards. If you do not want to derive it in the examination, do remember it directly. The distance between two nearest octahedral voids in case of FCC, that's always going to be A divided by root 2. Now similarly, if I ask you the distance between two nearest tetrahedral voids in FCC, you need to imagine it again. Okay? What should be the distance between two nearest tetrahedral voids in case of FCC? So my dear students, let's call this particular length as the edge length, which I'm representing with A. This is the edge length, correct? This is the edge length. Now first of all, let me draw one body diagonal from here to here. It's a body diagonal. Do you see at 1/4 of the body triangle, do you see there will be a tetrahedral void? Yes, here is a tetrahedral void. Perfect. Similarly, let me draw one more body diagonal. One more body diagonal will be from here till here. It will be one more body diagonal. And at 1/4 of the position, you will find one more tetrahedral void. Let me tell you, these two tetrahedral voids which you see over here, these are going to be the nearest tetrahedral voids in case of FCC. So you have to measure the distance between these two tetrahedral voids. These are the nearest tetrahedral voids in case of FCC, right? Now if I ask you, from here to here, it's going to be A by 4. From here to here, again A by 4, again A by 4 and A by 4. So what is going to be the distance between these two nearest tetrahedral voids? I mean this distance I'm asking, from here to here. What is going to be this distance? It's going to be A by 4 plus A by 4. A by 4 plus A by 4 comes out to be what? 2 times A by 4, that means A by 2. So do remember from now onwards, the distance between two nearest tetrahedral voids in case of FCC, that's always equal to what? That's always equal to A divided by 2. Is it clear? Let me know once in the chats with the thumbs ups if everything seems clear. Quickly guys. Quickly, everyone. Everyone, quickly. Quickly guys, everyone. Is it super clear to everyone? With the thumbs ups, yaar. With the thumbs ups. Not like this. With the thumbs ups. With the thumbs ups, yes? Perfect. There are a few more concepts which I would want to discuss with you so that it will be super clear, right? So that you can do the questions properly when it is asked. You are asked a question from the density of the unit cell as well, right? How do we calculate the density? One simple result which I would want to give you, okay, just remember that result, that's all, okay? The result is D is equal to Z multiplied by M divided by NA multiplied by A cube. Multiplied by A cube. So this is the result by means of which you can calculate the density of the unit cell basically. Now here we have got M. What is this M here? M is basically the molar mass. M is basically the molar mass of element forming the unit cell. Molar mass of the species basically forming the unit cell. What is Na? Na represents your Avogadro's number. It represents your Avogadro's number. And A represents what? It represents the edge length. A represents your edge length. Okay? And Z, you know, it is the rank of the unit cell. It is the rank of the unit cell. So this relation, from this particular relation, you directly get a formula-based question. Nothing else. Formula-based direct. It will be mentioned that, for example, carbon is forming FCC. Carbon is forming FCC, in which the density will be given. Density will be given. You will have to calculate the edge length A. Can't you do it? Formula-based question, complete. Let's say you got carbon, whose molar mass you know, that's 12 grams per mole, right? Na is Avogadro's number. Carbon is forming FCC, that means Z value is 4. Density will be given, edge length you will have to calculate. So it's just going to be what? It's just going to be, it is just going to be a formula-based question, which I'm damn sure you can easily solve when it comes, yeah? Perfect? Perfect? Clear to everyone? All right. Perfect, guys. Let's move on then. Let's move on. Let's have a look on few more things and then we'll move on to the next chapter. Right? Whatever were the main points, we have discussed it. So let's do some question practice on the same and then we'll talk about something called as a radius ratio as well. Right? Which you can see here. So let's practice certain questions first, then we'll move on to the radius ratio. This chapter might take like half an hour more, okay? I hope that's comfortable with you. Alright, for example, let's say we have got a question like this. We have got a solid which contains A, B, C and D particles. Let's say this solid is forming CCP. CCP stands for cubic close packing. Cubic close packing, in which A particles are present at the corners, B particles are present at the face centers, C particles are, for example, present at octahedral voids, and D particles, they have occupied the tetrahedral voids. We are supposed to calculate the formula. How exactly you guys are going to do it? Have a look. First thing, CCP means cubic close packed. Cubic close packing. Whenever in a question it will be mentioned, that a solid is forming CCP, cubic close packed. That means a solid is forming FCC. Right? In case of FCC, you know the value of Z is 4. If the value of Z is 4, that means there will be 4 octahedral voids in total. That means there will be 8 tetrahedral voids in total. Right? Understood? Now, A is present at the corners. Contribution of corner is 1/8. In total, there are 8 corner particles. Done? Face center. Contribution of face center is 1/2. In total, there are 6 face centered particles. Done. Octahedral voids in total are 4 and all the octahedral voids are occupied by C. So 4 C particles and 8 D particles. As simple as that. When you solve it, so this is going to be 1, this is going to be 3, this will be 4, this will be 8. So the formula is going to be A1, B3, C4, D8. Right? This was the question. Done and dusted. Simple. Right? I'm sure you can easily solve these sort of questions. Now, for example, one last question which I'm giving you. Let's say you've got a solid in this form, A, B, C, D. A is forming CCP, B is occupying octahedral voids, C is occupying 25% of tetrahedral voids. Now, it's asked to calculate the formula. Can we do it? So, first of all, it's mentioned that A is forming CCP. CCP means FCC. In case of FCC, the Z value is 4. And it's A which is forming CCP. Z is 4. So, directly below this A, you'll write 4. Right? Now, how many octahedral voids will be there? 4. How many tetrahedral voids will be there? 8. So, B is occupying all octahedral voids. So, B is occupying all octahedral voids. C is occupying 25% of tetrahedral voids. 25% means 1/4. Tetrahedral voids means 8. Correct? Now solve it a bit. This is going to be 4, 1. This is 4, 1. This is 4, 2. Correct? So it's going to be 1 is to 1 is to, this is 4, 1, this is 4, 2. 1, 1, 2. Done and dusted, right? Just a second. This is 1 by 4 into 8. So this will be 1 by 4 here only, right? This is 4, 1, 4, 1, 4, 2. So the formula is going to be something like this. Let me write it here. A, you got 1. B, you got 1. And C, you got 2 divided by 4. Correct? 2 by 4 means 1 by 2. 2 by 4 means 1 by 2. Now you can take the LCM of the denominators, which comes out to be 2, and multiply throughout with 2. It's going to be 2, this is going to be 2, this is going to be 1. So the formula is going to be A2, B2, C1. I hope this is clear to everyone. Yes? Let me know once in the chats quickly. Let me know once in the chats quickly if every single thing is clear. Let me know once in the chats quickly if every single thing is clear. Everyone. Everyone, guys, everyone, quickly. Quickly, guys, with the thumbs ups. Don't stop. Perfect, wonderful. Now, moving on to something called as radius ratio. Now, why this concept of radius ratio is needed? First of all, let's see. Let's see why this concept of radius ratio is needed. So, for that purpose, in order to make you understand all this, let's talk about something called as ionic solids. Do you know what are ionic solids? Ionic solids. Typical example is NaCl. Typical example is NaCl, right? So, for example, you have got ionic solid like AB. Let's say AB solid, it's an ionic solid. Let's assume that. If it is an ionic solid, that means there will be cation anion present, A positive, B negative. Cation anion will be present, A positive, B negative. Yes. In general, you know, in the ionic solid, in general, the larger sized ion, among the two, in general, is your anion. And smaller sized ion, in general, is your cation. Smaller sized ion, in general, is your cation. And do remember, in case of ionic solid, the larger sized ion, they always occupy the lattice points. They always occupies the lattice points, and smaller sized ions, they'll be always going into the voids. In case of ionic solids, the larger sized ion, which are generally the anions, they occupy the lattice points, and smaller sized ions, they'll be always going into the voids. Now, in which particular void the smaller sized ion will go? That depends on what? That depends on something called as coordinates. That depends on something called as a radius ratio. Right? So, radius ratio is going to let us know in which particular void the smaller sized ion will go. Whether the smaller sized ion will go into the triangular void, tetrahedral void, octahedral void, whatever void. That's something which the radius ratio is going to let us know. Okay? So, what is the radius ratio now? How do we define the radius ratio? Radius ratio is simply defined as the ratio of radius of cation to that of radius of anion. There is one simple table which I would want you guys to remember. Radius of cation, radius of anion gives you the radius ratio of the ionic solid. Do remember, if the radius ratio value comes out to be greater or equal to 0.155, less than 0.225, at that time, the smaller sized ion will go into the trigonal void. Right? And you know, what is the coordination number of the trigonal void? It's 3. and the smallest sized ion going into the trigonal void, its coordination number will also be 3. Simple and basic. Whenever you'll be having an ionic solid, you have got an ionic solid, you know the radius of cation, you know the radius of anion, for example. You can easily calculate the radius ratio. You can easily calculate the radius ratio. If the radius ratio comes out to be greater or equal to 0.155, less than 0.225, the smaller sized ion will go into the trigonal void, right? The coordination number of the trigonal void is 3. That means the smaller sized ion entering that void, its coordination number will be also 3, right? Perfect. Now, dear students, one more thing. If the radius ratio value comes out to be greater or equal to 0.225, less than 0.414, the smaller sized ion, it will go into the tetrahedral void. And tetrahedral void coordination number is 4. So the coordination number of the smaller sized ion entering the tetrahedral void, it will be also 4. Okay. Now people, if the radius ratio value comes out to be 0.414 to 0.732, the smaller sized ion, it will go into the octahedral void, right? Wherein the coordination number of that void is 6. So the ion occupying, the smaller sized ion occupying that void, its coordination number will be also 6, right? And in the similar way, if the radius ratio, it is 0.732 to 1, the smaller sized ion will go into the cubic void and coordination number here is going to be 8. As simple as that. This is the table which I would want you guys to remember. So this particular table is going to let you know exactly, that whether the smaller sized ion of the ionic solid is going to enter into octahedral void, tetrahedral void, or wherever. Clear to everyone? Let me know in the chats quickly. And these are certain examples. Please and please take a note of all these examples as well, right? Take a note of all these examples as well. Anyways, you are going to get the PDF of this session in the Telegram group at the end, right? But you have to remember these examples as well. Question can be asked out of these examples. Yes? Perfect? All right. Now comes something. The structures of ionic compounds. From this particular topic, again question is asked. Structures of ionic compounds. The question is, what kind of questions are asked? What kind of questions are asked out of this particular topic? Structures of ionic compounds. My dear students, there are few structures of ionic compounds which you need to remember. Out of them, the first important structure is NaCl structure. NaCl structure. First of all, in case of NaCl structure, do remember your Cl negative ions. Your Cl negative ions, they form FCC, and your Na positive ions, they are present at the octahedral voids. They are present at the octahedral voids. This is something which you need to remember first of all. This occupancy is important. Cl negatives, they form FCC. Na positives, they occupy the octahedral voids. Point number 1. Point number 2. In case of FCC, the Z value is 4. If the Z is 4, that means there will be 4 octahedral voids, and all those 4 octahedral voids are occupied by what? All those 4 octahedral voids are occupied by Na positives. All those 4 octahedral voids are occupied by Na positives. In case of NaCl, there will be Na positive and Cl negative. Cl negatives, they form FCC. That means Cl negatives will be present at the corners and the face centers. Na positives will be present at the octahedral voids. For FCC, the value of Z is 4. That means there will be in total 4 Cl negatives, right? There will be 4 Cl negatives and there will be 4 Na positives as well. Perfect. Now, if I ask you, how many formula units of NaCl, how many formula units of NaCl are required to make this NaCl unit cell, to make this structure? How exactly you are going to do that? Simple. Simple. If I have NaCl, let's say I have got NaCl. If I take 4 formula units of NaCl, can I say from 4 formula units of NaCl, you will be getting 4 Na positives and 4 Cl negatives? Absolutely. From 4 formula units of NaCl, you will be getting what? You will be getting 4 Na positives and 4 Cl negatives. And 4 Na positives, 4 Cl negatives. 4 Na positives, 4 Cl negatives are enough to make a structure like this, right? So, if the question is asked, how many formula units of NaCl are enough to make this particular structure, you will say 4 formula units of NaCl are enough to make this particular structure. 4 formula units of NaCl are enough to make this particular structure. If they ask you about the coordination number of Na positive and Cl negative, coordination number of Na positive and Cl negative in this particular structure is 6:6. It is 6:6. It is 6:6. And radius ratio in case of NaCl, it is 0.524. These are the things which can be directly memory based questions, which can be asked basically, right? So please and please do have a look on these questions as well. Occupancy of ions, the number of formula units, the coordination ratio. That's it. That's it. Enough. Nothing else. Okay? Nothing else. Similarly, you have got one more structure which you have to focus on. That is cesium chloride structure. That is cesium chloride structure. CSCl structure. CSCl structure. CSCl structure. In case of CS structure, what do we have? In case of CSCl, what do we have? First of all, you have got CS positive ions. You have got CS positive ions, and at the same time, you have got Cl negative ions as well. And do remember, in case of this cesium chloride structure, Cl negatives, they are present at the corners of cube. Corners of cube, and CS positive, it's present at the center of the cube. Or you can say the CS positive, it occupies the cubic void. It occupies the cubic void. Okay. Now, my dear students, if Cl negative is present at the corners of the cube, the contribution of the corner is 1/8. There are total 8 corners. The value comes out to be 1. Right. Similarly, Cs positive is present at the center of the cube. The contribution is 1, and there is only one center. The value comes out to be 1. So I would say, in order to make cesium chloride structure, you should have one Cs positive and you should have one Cl negative. Now, from where you are going to get one Cs positive and one Cl negative? I would say, if I take one CSCl formula unit, from one CSCl formula unit, I will get one Cs positive, one Cl negative, and it's enough to make one structure, one unit cell of the CSCl. So, if I ask you how many formula units are required, you will say one formula unit of cesium chloride is enough to form this particular structure. This again simple, right? Clear? Is it clear to everyone quickly in the chats? One formula unit. Perfect. Now, similarly, if they ask you about the coordination ratio, it's going to be 8:8. Coordination number of CS positive as well as Cl negative in this particular structure is going to be 8. Okay? Perfect. Now, similarly, these are two very important structures which you have to remember. Rest, I'll show you 2-3 more structures, but those are least important only, right? Then you have got zinc sulfide, ZnS. ZnS. This zinc sulfide, it actually forms two structures. It actually forms two structures. One is called as sphalerite. One is called as wurtzite. One is called as wurtzite. So, two structures are formed by ZnS, sphalerite, wurtzite. In case of sphalerite, do remember S di negative. It forms FCC, and your zinc di-positive ions. Zinc di-positive ions. They are present at alternate tetrahedral voids. Alternate tetrahedral voids. In case of your wurtzite structure, your S di-negatives, they form hexagonal unit cell, and zinc di-positive ions, they are present at again alternate tetrahedral voids. Now, you just have to know one thing in these two structures. One is occupancy, ion occupancy, number one. Number two, what is that? One is ion occupancy. Number two, that is the formula unit. That's it. Nothing else. Number two is the formula unit. So, first of all, if S di-negative is forming FCC, for FCC the value of Z is 4. If the value of Z is 4, there will be 8 tetrahedral voids, out of which alternate are occupied. So, out of 8, 4 are occupied. Out of 8, 4 are occupied. So, in case of sphalerite structure, you should have 4 S di-negatives, 4 zinc di-positives, right? That means I should have 4 ZnS formula units with me, so that I'll get 4 zinc di-positives, 4 S di-negatives, and eventually I can form this kind of a structure, this kind of zinc sulfide structure, right? So, only thing which I would want you guys to remember here, that is the number of formula units. In case of sphalerite, the formula units required to make this kind of a structure, that's 4. That's all. right? Similarly, dear students, your S di-negative, it's hexagonal, right? For the hexagonal structure, the value of Z is 6. So you actually need 6 S di-negatives. Now the point is, how many zinc di-positives? If Z is 6, tetrahedral voids in total will be 12. Out of 12, alternate are occupied. Out of 12, 6 are occupied. 6 are occupied by what? By zinc di-positives. So you need 6 S di-negatives as well as 6 zinc di-positives. Then only you can make this structure, right? So I would say 6 formula units. 6 formula units of zinc sulfide are needed to form this particular wordite structure. Is it clear? These are just few things which I would want you guys to remember. Just, you need not to know the radius ratio values exactly. Radius ratio only you need to know for NaCl. That's all. Rest no one. Quickly let me know in the chats with the thumbs ups if it's clear. Everyone guys, everyone. Everyone. One more structure, that is fluorite. Fluorite structure. CaF2. Fluorite structure. Its example is CaF2, right? Or you can call it as AB2 type as well. First thing, as you all must be knowing, in CaF2 you have got calcium di-positive and F negative. Calcium di-positive and F negative. So in this particular structure, calcium di-positives, they form FCC. They form FCC lattice, right? And your F negatives, they are present, they occupy all the tetrahedral voids. They occupy all the tetrahedral voids. Now, dear students, calcium di-positive is forming FCC. So Z value for FCC is 4. That means there will be 4 calcium di-positives needed, right? F negatives occupy all the tetrahedral voids. How many tetrahedral voids are there in total? Z is equal to 4. So tetrahedral voids will be 8. So I would say all the 8 tetrahedral voids are occupied by F negatives. So in short, I can say 4 calcium di-positives and 8 F negatives are needed to form the structure, right? Perfect. 4 calcium di-positives and 8 F negatives are needed to form this fluorite structure. Now the point is, from where you will be getting 4 Ca di-positives and 8 F negatives. In that case, I'll take 4 CaF2 formula units, which will dissociate into 4 calcium di-positives and 8 F negatives, right? And these many ions, they are enough to form a structure like fluorite. That's it. So how many formula units are required? How many formula units of CF2 are required? I'd say 4 formula units of CF2 are required to form this particular calcium CF2 structure. Clear? And at the same time, do remember this as well. In case of this particular structure, each calcium di-positive is surrounded by 8 F negatives and each F negative is surrounded by 4 calcium di-positive. So each Ca di-positive is surrounded by 8 F negatives. So each Ca di-positive has got the coordination number of 8, right? And each F negative is surrounded by 4 calcium di-positive, right? So you would say calcium di-positive has got the coordination number of 8 here and F negative has got the coordination number of 4 here. So these are few structures which you need to remember, nothing else. Few structures which you need to remember, nothing else, right? Clear? Perfect. Now, dear students, one more thing. See, related to defects, you just have to go for 2 defects only. One is your Schottky, one is Frankel, right? One is Schottky, one is Frankel. These are the 2 defects in which you will focus more. So first of all, in case of Schottky defect, what happens? Everyone would be knowing. These are the only points which you just have to remember. Imagine that you had a perfectly crystalline solid here. Let's imagine this was the perfectly crystalline solid, right? After every A positive, there was B negative. After every B negative, there was A positive. Imagine that this was a perfectly crystalline solid, okay? Right? Yes? Now, my dear students, for example, suddenly equal number of cations and anions were missing from their sites. See, what I was expecting here, after B negative, I was expecting A positive here. After A positive, I was expecting B negative here. Now suddenly, equal number of cations and anions, right? Equal number of cations and anions are missing from their respective positions. When equal number of cations and anions are missing from their positions, I would say this crystal has undergone a defect. Which defect? That defect which gets created when equal number of cations and anions are missing from their sites. That defect is called a Schottky defect. Equal number of cations and anions are missing, right? Let's imagine before the defect, there were 4 A positives. There were, for example, 4 B negatives as well. So 4:4 means 1:1 stoichiometry. So stoichiometry would have been 1:1. Now equal number of cations and anions are missing. For example, 1 A positive left and 1 B negative left. Now it's going to be A3, B3. But still the stoichiometry is going to remain same. It is 3:3, 1:1. Nothing is happening with the stoichiometry. So basically, in case of Shortcut defect, what happens? Equal number of cations and anions, they'll be missing from their sites, right? But due to this particular defect, nothing happens. Nothing happens to what? Nothing happens to the stoichiometry of the solid. Is that clear to everyone? Is that clear to everyone quickly? Is that clear to everyone? Nothing happens to the stoichiometry of the compound. At the same time, since equal number of cations and anions are leaving, so nothing happens to the neutrality as well. Neutrality of the compound remains the same, right? Neutrality remains the same as well. The crystal as a whole remains neutral. Since vacancies are created here, that's why this defect is called as vacancy defect. That's why this defect is called as vacancy defect. And at the same time, these are the 2 points which you need to remember. For the compound to show this particular defect, cation and anion should not differ much in size. This is important. Cation and anion, they should not differ much in size. What does that mean? That means the size difference between cation and anion should be less, then only you can say the ionic compound is showing the Shortcut effect. So for the ionic compound to show the Shortcut effect, for the crystal to show the Shortcut effect, the cation anion size difference should be less. And at the same time, coordination number should be high. Coordination number should be high. These are the 2 important parameters which must be satisfied, then only the crystal shows Shortcut effect, right? Number one, cation and anion should not differ much in size. Number 2, coordination number should be high. Okay, tell me one more thing. If cations and anions are being missed, if cations and anions are coming out from the crystal, what happens to the mass of crystal? Mass of the crystal decreases. And if the mass of the crystal decreases, eventually you can say density of the crystal also decreases. So that crystal which undergoes Shortcut defect, its density decreases, right? Its density decreases. Perfect? Yes? And my dear students, in the similar way, you have got Frankel defect as well. In the similar way, you have got Frankel defect as well. In Frankel defect, what happens? In Frankel defect, what happens basically? In case of your Frankel defect, an ion leaves its appropriate site in the lattice and occupies an interstitial site. So it is basically the ion which leaves its actual site and occupies the interstitial site. Have a look on this particular thing. Look at this particular scenario. Over here, it was supposed to be A positive here. This was the original position of A positive. But this A positive, it's leaving its original position and going into the interstitial site. Whenever this happens, an ion leaves its original site and enters into the interstitial site. We say the crystal undergoes what? We say the crystal undergoes the Frankel defect. So this particular crystal has undergone what? Frankel defect, right? Perfect. Now can I say again a hole or vacancy got created here? Absolutely, hole vacancy. A hole or vacancy is produced. Perfect. Okay, tell me one thing. Due to this particular defect, tell me whether the stoichiometry of the compound will change or not. Initially, imagine as if there were 4 A positives and 4 B negatives. So the stoichiometry was 1:1, right? 1:1. Now one of the A positive left, right? And that A positive entered into the site, interstitial site. So A positives, B negatives are still the same in the crystal, right? Perfect. Nothing happens. It's 4:4 only. It's 1:1 only. So stoichiometry does not change. Number 1. Number 2. Will anything happen to the density? Will anything happen to the density? Density is equal to mass by volume, right? Since no ion is leaving the crystal, the ions are remaining inside the crystal only. But they are just changing the position. Right? Ions are remaining inside the crystal only, just they are changing the position. That's all. Okay, so density remains unchanged. Perfect. What happens to electrical neutrality? Are the ions increasing or decreasing in the crystal? No, ions are not increasing or decreasing in the crystal. Ions are remaining the same only. Perfect. So neutrality also remains the same. Perfect. Now, which all ionic solids show this kind of the defect? Which all solids show this kind of the defect? Quickly. Which all solids show this kind of the defect? What do you think? For the solid to show this kind of the defect, the cations and anions. Just a second, guys. There is someone here.
Now it's my turn. Now it's my turn.
अबे यार ये कौन आ गया?
How are you?
अबे इसको बाहर निकालो.
Hey warriors, what's up?
Hi everyone.
We are missing you,
I
yaar.
am going to just a minute. I am going to disturb your session. How are you everyone?
Looks like. What is AGCL? We are not AGCL. ZMS. Man, so studious students, yeah? How come?
Huh.
Very studious students. They don't want us.
They are studious, you know, they are my
You got
students.
anything
They
for
are
me?
my
We,
students.
we are going to eat pizza. We can send a slice.
See,
they are going to eat the pizza.
without me, है ना?
I'll talk to them in the hotel.
Yeah, we'll see you in the night.
Now you'll realize how it feels when you disturb someone's session.
Very hard working students, really hard.
Oh my god.
Achha,
See,
wait,
he's always...
she was asking me some biology questions, no? Yesterday.
Okay. It was very nice
Guys,
talking
time
to you.
ask
It was
Ambika
very
ma'am
nice
chemistry
talking to
questions. Guys, ready
you.
for asking Ambika ma'am chemistry questions, what say?
Oh.
Ambika ma'am for chemistry.
Yes, but you have to help me, yaar. We are a team.
I will guess. Because
Okay,
I'm going
okay.
to record a video for how to guess also. No? So I'm going to guess.
Okay. Chalo, ask something.
We'll give them-
Hard-working students. Really
We'll give them one question, guys, huh?
Okay.
And you guys are also going to solve.
hard. Okay, let's see to it.
You have got a solid.
Yes.
Okay.
HSP sir, no hints.
Okay.
I
Okay.
will, but.
Okay.
HSP said no hints.
No.
No.
Guys, you also solve it.
I'm going to
Achha,
disturb you
Sure,
today.
sure.
Achha, do you want to have tea? Tea or filter coffee?
T.
Done.
Okay, we have got a solid in which there are three types of constituent particles, A, B and C.
Okay.
Okay. A particles are present at 50% of the corners of the cube.
Okay.
50% of corners. B particles are present at the face centers.
Okay.
Google mat go. Face centers, and C particles are present at the body center.
Okay.
What is going to be the formula of this compound? You can solve it. You can take your time. Guys, give it a try. Give it a try. Till then, these biology
Just
people
a
will...
minute now. Repeat
Man, this is
yourself.
very difficult question, yeah? It's
Wait.
not fair. It's not fair.
Exactly.
It's simple.
Repeat your question.
First,
Repeat your
first,
question.
first.
No, just a minute. Repeat your question.
Array A is present at the edge.
No.
A is
Corner.
present at
Corner.
50% of the
No,
corners.
where these particles are present in the jungle, or on the road, or in the cube.
No, roots, stem, leaf,
Stem,
flower.
leaf. Just let me
Chalo.
know where these
See,
particles are
you
present.
want me to answer the question. Huh? I am going to answer that. So you repeat your question once.
These,
Repeat
Hi
your
Siri.
question once.
Hi Siri, please help your ma'am.
these
People are saying it's AB6C2. Someone is saying A184. Jaldi sir answer batao.
Don't disturb.
Don't disturb. Don't disturb.
Don't
I
disturb.
am going to disturb him. He always used to disturb me. And I know one word. Ille. Ille.
Oh.
Ille.
Okay. You want me to solve this?
No, I don't want you to solve this.
Leave that.
No, I'm not
Leave.
going. You want tea?
I
Guys,
want tea.
I'm coming tomorrow at 9 o'clock and HSP sir is going to come at 5 o'clock.
I'm not going to. I'm not
6
going
hour
to disturb
sessions
them.
properly.
But this man is really bad. But you're a good teacher.
Of course. We are all.
I'm saying because you forced me to say so. Otherwise, I'm going to say you're not at all a good teacher.
Achha, chalo, let's
Okay,
start now.
chalo.
I'll finish.
Continue,
Guys,
guys.
Okay.
listen, I'll finish this chapter.
Yeah,
I'll
you
give
will.
them a break.
We'll
Okay.
keep
Fir
the
chai
pizza
peete
ka, we'll keep the crust or I don't know.
Huh,
something.
still, I'm a good friend. I'll order something for you.
Yeah, please do that.
Yeah. And tea for Wassim sir.
Okay.
Bye bye guys. See
See,
you.
bye. Huh?
I'm just giving the break after this. Okay? I'll just take like 10-15 minutes.
It's
Chal na. Just a second, guys. Okay, so you're done with this? Alright, the ones who are not done with this, let me show it to you. The question was simple basically, right? A particles are present at 50% of the corners. 50% means 1 by 2. Corner contribution is 1/8. In total, there are 8 corners. Face center contribution is 1 by 2. There are 6 face centered particles. Body center contribution is 1. There is one particle, right? So 8, it got cancelled. This is 1 by 2. This is 3 and this is 1. So multiply throughout by 2. This is 1. This is 6. This is 2. So it's going to be 1, 6, 2. 1, 6, 2. Done and dusted, right? There was nothing to think here, yaar. You took a lot of time, I guess. But majority gave the correct answer. That's great. Okay, we were talking about the Frankel defect basically. So in case of Frankel defect, you need to remember things. What is that? In case of Frankel defect, the ions, they leave their actual positions and enter into the interstitial site. Nothing happens to the neutrality. Nothing happens to the density, right? Nothing happens to the stoichiometry. It does not change. And at the same time, the cations and anions, they should differ much in size. That means the size difference of cation and anion should be more. And coordination number should be less, then only you can say the crystal shows what? Then only you can show the crystal shows the Frankel defect. These are the two defects which are very, very, very important. And these are few examples of the compounds which just show the Frankel defect. And there is one question which is frequently asked. Which of the following shows both Frankel and Schottky defect? It is going to be AGBR. Do remember this one as well. AGBR is the one which shows both the defects. One is your Schottky and one is your Frankel. Is this clear to everyone? Which chapter do you want me to start now? I think your solid state is done and dusted, right? Tell me first of all, which chapter do you want me to start now? Quickly. Quickly guys, everyone. Yes, we'll start after the break only. But tell me which chapter do you want me to start? Do you want to start with electrochemistry? यार जल्दी बताओ. Everyone, quickly. Which chapter do you want me to start after the break? Everyone, guys, everyone. Everyone means everyone. Chalo, majority is saying electrochemistry. So, what is the time now? It's 1:30. So, it's a lunch break for half an hour, okay? Lunch break for 30 minutes, then we'll get back. Right? And don't worry, your syllabus will be completed, okay? Just relax. We just started, okay? Relax, relax. I'll be back. Let's have lunch and get back. See you in a while. Guys, am I audible, visible to you again? Am I properly audible, visible to everyone? Thumbs ups in the chats. Quickly, quickly, quickly. All clear? Perfect. Call up everyone quickly. Guys, call up everybody quickly, we are starting. Call up everybody. Okay, so should we start now? Give me some thumbs ups in the chats now, quickly. Are you done? Are you done with your lunch? Are you all done with your lunch? Yes or no in the chats, quickly. Quickly, guys. Quickly. How was the pizza? I didn't get the pizza yet, yeah. I didn't have it. I just had tea. Maybe they'll be getting me the pizza in some time. Perfect, guys. So let's start the new chapter now. That's going to be your electrochemistry. One of the most important chapters, okay? One of the most important chapters and interesting chapter at the same time. So the first topic which we are going to deal with in electrochemistry, that is Daniell cell. But before talking about the Daniell cell, before talking about the EMF part, let me teach you something which is really basic, okay? So that there won't be no issue in electrochemistry. So first of all, I'm going to talk about the basics which is required for electrochemistry. Have a look. First of all, for example, imagine like this. Imagine like this. Let's say I have a reaction in this format. A general reaction, A plus B, it gives A positive plus B negative. Now I'll be somewhat quick, okay? Now I'll be somewhat quick. Let's say I've got a reaction A plus B gives A positive plus B negative. If I ask you, what is the oxidation state of A? You'll say the oxidation state of A here is 0. There is no charge present on it. What about the oxidation state of B? It's again 0. No charge on B. What about the charge present on A? It's plus 1. Its oxidation state is plus 1. And here, the oxidation state is minus 1. Now, my dear students, if I ask you, in this particular reaction, whether the oxidation state of A has increased or decreased. 0 to plus 1, increase in the oxidation state. And remember from now onwards, increase in the oxidation state is something which you call as oxidation. And oxidation means loss of electrons. Oxidation means loss of electrons. So in this particular reaction, as you saw, the oxidation state of A is increasing from 0 to plus 1. Increase in the oxidation state is something which we call as oxidation. So I must say this A is undergoing oxidation. A is undergoing oxidation means A is losing some electrons. Let me tell you, that species which undergoes oxidation, that's something which you call as a reducing agent. That's something which you call as reducing agent. So in this particular reaction, your A is the reducing agent. Point number one. Point number one. Point number two. Look at the oxidation state of B. Initially it was 0. Now it's minus 1. I can see oxidation state of B is decreasing. And let me tell you, decrease in the oxidation state is something which we call as reduction. And reduction simply means gain of electrons. Reduction simply means gain of electrons. And any species that undergoes reduction, that's something which you call as oxidizing agent. That's something which you call as oxidizing agent. So I hope you got to know what is your oxidizing agent, what is a reducing agent. So that species which undergoes oxidation, loses electrons, behaves like the reducing agent. That species whose oxidation state decreases with time, undergoes reduction, gains electrons, behaves like the oxidizing agent. I hope it's clear. For example, let me give you a scenario like this. Let's say I'm writing a reaction and the reaction is something like this. MnO4 negative plus Fe di positive, it gives Mn di positive plus Fe tri positive. This is the reaction. Now you got to tell me, you guys are going to tell me which one is the oxidizing agent and which one is the reducing agent. Dear students, first of all, if I calculate the oxidation state of manganese over here, let's assume it is X. Oxygen will show -2 oxygen state, 4 oxygen atoms in total, net charge -1. So X value will be +7. So +7 is the oxidation state of manganese here. +2 is the oxidation state of iron here. +2 is the oxidation state of manganese here. +3 is the oxidation state of iron here. Correct? Now you see exactly whether the oxidation state of manganese is increasing or decreasing. +7 to +2. +7 to +2. Decrease in the oxidation state. Decrease in the oxidation state is something which you call as reduction. Reduction means gain of electrons. Any species which undergoes reduction, that's called as oxidizing agent. Right? So it's basically MnO4 negative, which undergoes reduction, which gains electrons and behaves like the oxidizing agent. And eventually, I can say, iron is changing its oxidation state from +2 to +3. +2 to +3 means increase in the oxidation state. Increase in the oxidation state is something which you call as oxidation. Oxidation. Oxidation means a loss of electrons. And any species which undergoes oxidation behaves like the reducing agent. I hope you exactly got to know. I hope you exactly got to know how to identify whether the species is the oxidizing agent or the reducing agent. Right? Now let's have a look. This was just the basics which is required. Now guys, our first topic in the electrochemistry, that is going to be the galvanic cell. That's going to be the galvanic cell. Okay? We have to see its working. So first of all, what is a galvanic cell? Let me quickly tell you, galvanic cell is nothing. It is just the device. It is basically the device which converts. It is the device which converts chemical energy. It is the device which converts chemical energy into the electrical energy. It is the device which converts chemical energy into the electrical energy. And now exactly we'll be seeing in some time how it converts chemical energy into electrical energy. But before talking about that, the most typical example of galvanic cell, that's what you call as Daniell cell. The most typical example of the galvanic cell, that's what you call as Daniell cell. And do remember, in case of Daniell cell, what do? We use 2 electrodes. In case of Daniell cell, we use 2 electrodes. One is going to be your zinc electrode, one is going to be your copper electrode. In your Daniell cell, we actually use 2 electrodes. One is going to be your zinc electrode, one is going to be your copper electrode. Let me tell you, the zinc electrode in the Daniell cell, it behaves like the anode. It behaves like the anode. And copper electrode, it behaves like the cathode. From now onwards, please and please remember, at anode always oxidation takes place. At anode always oxidation takes place. At cathode always reduction takes place. Oxidation, you know, it means loss of electrons. Reduction, you know, it means gain of electrons. The first point which you need to remember. The most typical example of the galvanic cell is the Daniell cell. In the Daniell cell, we'll be using 2 electrodes. One will be zinc, one will be copper. Zinc will be behaving like the anode. Copper will be behaving like the cathode. At anode, oxidation takes place. At cathode, reduction takes place. I hope it is clear. Now, people, there is one more point. How do we make the electrode first of all? How do we make the electrode? Let's say I have to make a zinc electrode. Let's say I have to make a zinc electrode. How exactly I'm going to make it? How exactly I'm going to make it? What I'll be doing, I'll be taking a container, and in this particular container, I am going to take a salt of zinc. I am going to take a salt of zinc. For example, I took zinc sulfate in the container. This zinc sulfate, it's a strong electrolyte. It will get completely dissociated into zinc dye positive and SO4 dye negative. So basically in this container, I took the salt of zinc, which got dissociated into zinc dye positive and SO4 dye negative. So in this container right now, you have got zinc dye positives as well as SO4 dye negatives. Now dear students, in the same container, I am introducing a zinc rod. I have introduced a zinc rod into a solution containing its own ions. I have introduced a zinc rod into a solution containing its own ions. This complete setup over here, I'll be calling as electrode. And which electrode it's going to be? It's going to be your zinc electrode. Got it? In the similar way, if you want to make the copper electrode, how exactly you will make the copper electrode? You will be taking a container, and in this container, you will be taking a salt of copper, which is, for example, your copper sulfate. You took a salt of copper. This copper sulfate would have got dissociated as Cu dye positive and SO4 dye negative. Perfect. Now, in the same container, you are introducing a rod, a copper rod. Can I say, I took a copper rod, introduced the copper rod into its own ions, So this complete setup over here, I'll be calling as copper electrode. I hope you got to know how we are making the electrodes. Yes? Right? Take the rod, introduce it into its own ions. You'll be getting an electrode. That's all. Right? Now what we have to discuss basically? We have to discuss basically the working of the Daniell cell. We have to discuss the working of the Daniell cell. How Daniell cell works. Daniell cell, which is the example of the galvanic cell. How it works. How it converts chemical energy into electrical energy. That's important. Okay. So, as I told you, in case of Daniell cell, you will be taking 2 electrodes. Let's say I am taking those 2 electrodes here. In the Daniell cell, I'll be taking 2 electrodes. Let's say these are 2 containers which I took. In this particular container, I'm keeping zinc sulfate. In this particular container, I'm keeping copper sulfate. This zinc sulfate would have got dissociated completely into zinc dye positive plus SO4 dye negative. This copper sulfate would have got dissociated into copper dye positive plus SO4 dye negative. So dear students, analyze one thing. In this container, you have got right now the equal number of cations and anions. So this particular solution right now is electrically neutral. Similarly, this particular solution contains equal number of cations and anions. So this particular solution again is electrically neutral. Point number 1. Point number 2. Let's introduce a zinc rod here. This is a zinc rod basically. This is your zinc rod. Let's introduce the copper rod here. So can I say I got 2 electrodes? Absolutely, I got 2 electrodes. One is zinc, one is copper. Right? Now dear students, you guys are going to connect them externally. Connect these 2 electrodes externally with the help of voltmeter. Right? Now internally, how you guys are going to connect it? Externally you connected it. Now internally you have to connect it. How internally you guys are going to connect it? You'll be taking one inverted U-type tube. This is an inverted U-type tube. Right? Like this. And what you guys are going to keep inside this inverted U-type tube? Let me tell you that. This inverted U-type tube, it contains an inert electrolyte. For example, K2SO4 mixed with gelatin or agar-agar. Mixed with gelatin or agar-agar. When you mix the inert electrolyte K2SO4 with gelatin or agar-agar, what do we get? We get a jelly-like paste. We get a jelly-like paste. And that jelly-like paste is introduced here in this inverted U-type tube. And these 2 ends are sealed with the cotton balls. These 2 ends are sealed with the cotton balls. This inverted U-type tube, which contains the inert electrolyte, right? This inverted U-type tube is something which you call a salt bridge. This is something which you call as salt bridge. Okay. Now, dear students, if I ask you whether the circuit is externally as well as internally complete, yes, the circuit is externally as well as internally complete. The circuit is complete. Okay. So, what is going to happen? What is going to happen? Understand. First of all, in the salt bridge, what do we have? We have got K2SO4. K2SO4 means we have got K positives as well as SO4 dinegatives. Where? In the salt bridge. This particular zinc electrode, as I told you already, it behaves like the anode. And this one, the copper electrode, it behaves like the cathode. And you know, at anode what happens? At anode oxidation happens. And at cathode what happens? At cathode reduction takes place. And you know, oxidation is nothing, it is just loss of electrons. And reduction is nothing, it is just the gain of electrons. Right? Now, let's see exactly how this cell works. First of all, when we introduce the salt bridge, the circuit gets completed. The circuit gets completed. What is going to happen? At anode, what you will find? At anode, you will find oxidation taking place. At anode, you will find oxidation taking place. Oxidation means loss of electrons. Now, this rod, this zinc rod, which is made up of zinc atoms, those zinc atoms of which rod is made up of, those zinc atoms will undergo oxidation, will lose electrons. So basically, the zinc atoms of which this zinc rod is made up of, those zinc atoms will undergo oxidation. So reaction is going to be very simple. At anode, what is going to happen? At anode, I must say, your zinc atoms from the rod, they will lose 2 electrons and will get converted into zinc dipositives. Perfect. The rod is made up of zinc atoms. Those zinc atoms are undergoing oxidation. Zinc atoms are getting converted into zinc dipositives, 2 electrons. This zinc dipositive which we got, this zinc dipositive enters into left container. First of all, the rod which is made up of zinc atoms, those zinc atoms undergo oxidation, they get converted into zinc dipositive. That zinc dipositive, extra zinc dipositive, that enters into this particular container. Right? Yes? And the 2 electrons will get accumulated on the rod. Similarly, when one more zinc atom undergoes oxidation, one more zinc dipositive enters the left container. 2 more electrons got accumulated on the rod. Similarly, these electrons will keep on getting accumulated on the rod and zinc dipositives will start getting into the solution. Since this particular rod on which electrons have been accumulated, since electrons are accumulated, that's why this particular rod of anode, it carries a negative charge. You must be knowing, anodic rod, it carries a negative charge. That's the reason why this anodic rod carries a negative charge. At the same time, what happens at cathode? This is something which happened at anode, right? Now, what happens at cathode? At cathode, reduction takes place. Reduction means gain of electrons. If I ask you in this particular container, what do we have? We have got copper dipositive ions. These copper dipositive ions which are in the solution already, they are going to collide with the rod. They are going to take 2 electrons from the rod. Copper dipositive ions which were there in the solution, they are going to collide with the rod. They are going to take 2 electrons from the rod and they will be getting converted into copper solid. And this copper solid will start depositing on this rod. This copper solid will start depositing on this rod. Perfect. Now, if I ask you, since copper dipositive ions which were there in the right container, they are colliding with the rod. They are taking 2 electrons from the rod. If electrons are being taken out from the rod, can I say this rod is going to get the positive charge then? Now you tell me. This rod is getting positive charge. On this rod you have electrons. The path is already created. Can I say this positively charged rod is going to attract these electrons towards itself? So can I say there is the movement of electrons happening now? There is the movement of electrons happening? Yes. Is it just the movement of electrons? Okay, it is the directional movement of electrons. I will say it is now going to be the directional movement of electrons. It's going to be the directional movement of electrons. And you know, whenever there will be the directional movement of electrons, whenever there is directional movement of charge, current is generated. Right? Let me know once in the chats if it is clear. Current is generated. Right, people? So, first of all, The electrons are moving in the direction from anode to cathode. This is the direction of movement of electrons. And you know, since it is not only the movement of electrons, it is the directional movement of electrons, due to which current will be generated here. So if I ask you what is the direction of current, what is the direction of current? What is the direction of current? The direction of current is always opposite to the direction of electrons. So the direction of current will be from cathode to anode. The direction of current will be from cathode to anode. Perfect. This is the first point which you need to remember here. This is the first point which you need to remember. This is one more point which I want you guys to remember. Right? Now, there are a few more points. What is happening to the rod, zinc rod? Zinc rod is undergoing oxidation. Zinc rod is made up of zinc atoms. Those zinc atoms are getting oxidized. Those zinc atoms are getting converted into zinc dipositives. And those zinc dipositives, they get into this particular container. So can I say the thickness of this zinc rod will keep on decreasing with time? Absolutely. Zinc rod, its thickness will decrease with time. Similarly, if you talk about the copper rod, copper dye-positive ions which were there in the solution, they collided with the rod, took 2 electrons from the rod, right, got converted into copper solid, and that copper solid got deposited here on the rod. So what happened basically? Can I say the thickness of this copper rod increased with time? Thickness of copper rod increased with time? Absolutely. This is one more thing which you need to remember. Thickness of zinc rod decreased with time, and thickness of copper rod, that increases with time. Okay. Now, since this is the reaction happening at anode, this is the reaction happening at cathode. Now, my dear students, if I ask you what is the net reaction which is happening in the cell? What is the net reaction happening in the cell? Whenever you need to write the net reaction happening in the cell, first you will be writing reaction at anode, then you will be writing reaction at cathode, then you will be seeing whether the electrons in both the reactions are balanced or not. And electrons in both the reactions are balanced. Electrons in both the reactions are balanced. Since the electrons in both the reactions are balanced, now you can directly add these two reactions. Directly add these two reactions. When you add these two reactions, it's going to be zinc solid plus copper dye positive aqueous. Since two electrons cancel, gives zinc dye positive aqueous plus what? Plus copper solid. This is our net reaction. This is our net reaction. This is our net reaction. At the same time, if I ask you how many moles of electrons got exchanged from anode to cathode, how many moles of electrons got exchanged from anode to cathode? That means I'm talking about N. N represents the number of moles. Number of moles of electrons exchanged from cathode to anode. From anode to cathode. How much it is? Simple. How many electrons got cancelled here? 2. That means 2 moles of electrons got exchanged from anode to cathode. Clear? N value is 2. Now, if you ask me, what is the use of this particular salt bridge here? What is the use of this salt bridge here? If you ask me, many uses. Why? See, the first and the important use of salt bridge. Understand. Since this particular rod is undergoing oxidation, the atoms of which this rod is made up of, those zinc atoms are getting oxidized. They are getting converted into zinc dipositive. And that zinc dipositive goes into the rod, due to which, that extra zinc dipositive goes into the solution, due to which this solution gets extra positive charge. It gets additional positive charge, right? Since initially there were equal number of zinc dipositives and SO4 dinegatives, the solution was electrically neutral. Now what is happening? The extra zinc dipositive is going into the solution, due to which this solution gets positive charge. This solution gets positive charge. In the similar way, there were equal number of copper dipositives and SO4 dinegatives in this solution, due to which this solution was neutral. Now one of the copper dipositive, it collided with the rod, took the electrons from the rod, got converted into copper solid and got deposited on the rod. Can I say in the solution, the number of Cu dipositive ions decreased? In this particular solution, the number of Cu dipositives decreased. Initially, the cations and anions were the same. Now, Cu dipositives are decreasing. So, effectively, this solution carries a negative charge now. Right? What this salt bridge does, as soon as this particular solution gets the positive charge. From the salt bridge, SO4 dinegative will come. As soon as the left container gets the positive charge, at the same time SO4 dinegative will come and will neutralize this. As soon as this solution gets a negative charge, at the same time K positive will come and will neutralize this. So the main and the important function of the salt bridge is to maintain the electrical neutrality. Salt bridge maintains, what does it maintain? It maintains the electrical neutrality. It maintains the electrical neutrality in both the solutions. In both the solutions. At the same time, one more thing. This salt bridge, it avoids the liquid junction potential. It avoids the liquid junction potential. What is meant by that? What is meant by that? Let's have a look. Let's see exactly what it means. It avoids the liquid junction potential. Let's see what is exactly meant by that. So, my dear students, let's say instead of two containers, I am taking a single container. Let's say instead of two containers, I am taking a single container. Now, what exactly I am doing? I am dividing this container into two equal parts with the help of a semi-permeable membrane. This is the semi-permeable membrane which I have taken over here. In this left chamber, what do I have? I have kept zinc sulfate. And in this right chamber, we have got copper sulfate. This zinc sulfate is getting converted into zinc dye positive and SO4 dye negative. So, in the left chamber, there are equal number of cations and anions. So, this solution is neutral. In the right chamber, this copper sulfate got converted into copper dye positive and SO4 dye negative. So, equal number of cations and anions in the right chamber. So, this solution is also neutral. So, over here, I am introducing the zinc rod. And right here, I am introducing the copper rod. Perfect. And over here, I am just completing the circuit externally. I completed the circuit externally. Yes. Now, if I ask you whether the circuit is complete or not, externally it's complete. Internally, the solutions are in direct contact because I have used SPM, semi-permeable membrane. So, internally, the solutions are in directly contact. So, I would say this circuit is complete right now. Even without using salt bridge, the circuit is complete. Even without using the salt bridge, the circuit is complete. Right? Now, if I do not use salt bridge, circuit is already complete. So, what is going to happen? What's going to happen? Understand. This is zinc. This is copper. Correct? Zinc is going to behave like the anode. Copper is going to behave like the cathode. And at anode, oxidation takes place. So, zinc rod is made up of zinc atoms. Those zinc atoms will undergo oxidation, will get converted into zinc dye positive, and that zinc dye positive is going to enter into this solution. So, this left chamber gets the positive charge. Similarly, due to the reduction, the left chamber gets the negative charge. Positive charge got accumulated here, negative charge got accumulated here. They can attract and they can get accumulated at the junction. Similarly, one more oxidation takes place here, one more reduction takes place, again positive and negative, again they get accumulated here. So, can I say at this particular junction, this is a junction here, at this particular junction, on one side of it positive charge got developed, on another side negative charge got developed. So, I'll say at this particular junction a potential difference got created, and we call this particular potential difference as the liquid junction potential. We call this particular potential difference as the liquid junction potential. Right? Liquid junction potential got created. And my dear students, have a look exactly what I'm going to say now. If I would have used the salt bridge, as soon as positive charge was accumulated in this left chamber, at the same time from the salt bridge, SO4 dinegative would have come, would have neutralized it. As soon as negative charge got developed in the right container, at the same time K positive would have come from the salt bridge and neutralized it. Due to which no positive and no negative charge would have developed in these two solutions, due to which this junction potential difference would have avoided. Yes? So can I say the main function of the salt bridge is to avoid the liquid junction potential? Is to avoid the liquid junction potential? Yes? This is the main function of the salt bridge, to avoid the liquid junction potential. Let me know once in the chats quickly. Sentimo, you can go to some other channel. Okay? Quickly, guys. Everyone. Thank you, guys. Thank you so much. Everyone, is it clear? Is everything clear? So in this Daniel cell, what all things we have to remember now? What all things we have to remember now? The direction of electrons is from anode to cathode. Current ki direction is from cathode to anode. Zinc rod dissolves with time. Thickness of copper rod increases with time. 2 moles of electrons got exchanged in the net cell reaction. Salt bridge maintains the electrical neutrality of the solution and it avoids the liquid junction potential. That's all. Okay? That's all you need to remember. Perfect? All cool? Of course, MCQs will be also doing, but let's have some theory first. Let's understand some theory first. Perfect. Now, guys. Now. Now the point is, how do we represent the galvanic cells? This is important. How do we represent the galvanic cells? First of all, the Daniel cell which I gave you a few minutes back, this was a net reaction. This was the net reaction happening in that galvanic cell. This was the net reaction happening in that Daniel cell. Now from the cell reaction, how do we represent it? There is a special way to represent the cells basically. And how exactly we are going to do it? Understand what is the special way. First of all, your first step always is to check which species is undergoing oxidation and which species is undergoing reduction. Let's give it a try. Let's check. See, the oxidation state of zinc is 0 here. Over here it's +2. Right here it's +2. Right here it's 0. Correct? Now check whether the oxidation state of zinc is increasing or decreasing. 0 to +2. Increase in the oxidation state means oxidation. So zinc is undergoing oxidation here. Zinc is undergoing oxidation here. In the similar way, copper is changing its oxidation state from +2 to 0. +2 to 0. Decrease in the oxidation state. Decrease in the oxidation state means reduction. So this copper dye positive is undergoing reduction. So I identified that zinc is undergoing oxidation and copper dye positive is undergoing reduction. Do you know oxidation takes place at anode? So it is basically your zinc which is going to behave like the anode in the cell and it's copper which is going to behave like the cathode. You identified from the cell reaction which one is your anode and which one is your cathode. Now how do we represent the cell? First of all, draw 2 lines. These 2 lines, they represent the salt bridge. These 2 lines, they represent the salt bridge. On the left side of the salt bridge, you'll be always writing the anode. On the right side of the salt bridge, you'll be always writing the cathode. And you know, at anode, what is happening? At anode, your zinc is getting converted into zinc dye positive. So at anode, your zinc solid, it's getting converted into zinc dye positive aqueous. And in the similar way, my dear students, on the right side, what do we have? We have cathode. At cathode, what is happening? At cathode, reduction is happening and copper dye positive is getting converted into copper solid. At cathode, copper dye positive aqueous is getting converted into copper solid. Right? That's how you represent the cell. Is it simple? Let me know in the chats quickly if it's clear. Let me know quickly in the chats if it's clear. Everyone. Everyone. Yes? Quickly guys, yes or no? Thumbs ups in the chats. Alright, let me give you one more example so that it becomes clear to you. Let me give you one more example. For example, you have got one more galvanic cell. Let's say you have got one more galvanic cell whose cell reaction is given to you. Whose cell reaction is given to you. Now from this particular cell reaction, you have to represent this cell. Again, the same procedure you guys will be doing. Look at this particular scenario. Iron, its oxidation state is 0 here. Copper, its oxidation state is +2. Iron, its oxidation state is +2. Right here, its oxidation state is 0. Correct? Now check whether the oxidation state of iron is increasing or decreasing. 0 to +2, increase in the oxidation state. +2 to 0, decrease in the oxidation state. Increase in the oxidation state is something which you call as oxidation. And you know, this oxidation, it takes place where? It takes place at anode. Oxidation takes place at anode. In the similar way, if you talk about this particular copper dye positive, its oxidation state is decreasing. Decrease in the oxidation state is something which you call as reduction. And reduction takes place at cathode. So first of all, you identified what is your anode and what is your cathode. You identified it. You identified the cathode and anode. Now, draw two lines. They represent the salt bridge. On the left side, we always write anode. On the right side, we always write the cathode. At anode, what is happening? Oxidation. Iron is getting converted into iron dye positive. So at anode, iron solid is getting converted into iron dye positive aqueous. Correct? Similarly, on the right side, we have got cathode. At cathode, reduction is taking place. And what is happening exactly? Copper dye positive is getting converted into copper solid. Copper dye positive aqueous is getting converted into copper solid. So this is how you represent the cell whose cell reaction is given to you. Is it clear? Is it clear to everyone? Quickly. Quickly, my dear students, everyone. Everyone. Okay, look at this one. Look at this one. There might be slight change now. There might be slight change now. There might be slight change now. Is it clear? Alright, look here now. If you look at the oxidation state of this zinc, it's 0. Oxidation state of this hydrogen, it's +1. The charge is +1 here, right? Oxidation state of this particular zinc, it's +2. There is no charge on this hydrogen here, it's 0. Now check. Oxidation state of zinc is increasing from 0 to +2. And increase in the oxidation state, you know, that's oxidation, and oxidation takes place at anode. So eventually this is going to be your cathode. So you identified your anode and cathode. You identified your anode and cathode, right? Now dear students, these are the two lines which represent the salt bridge. On the left side of the salt bridge, I'll be writing the anode, and at anode, zinc is getting converted into zinc dye positive. So your zinc solid is getting converted into zinc dye positive aqueous at anode, right? Now. On the right side, I'll be writing the cathode, right? And at cathode, reduction takes place. Reduction means gain of electrons, right? Reduction means gain of electrons. See, your H positive is getting converted into H2. So this is your H positive aqueous, which is getting converted into H2 gas. Now, if I ask you whether this cell is complete or not, if I ask you whether this cell is complete or not, the cell is not complete yet. The cell is not complete yet. Because this is a gaseous electrode here. In order to make a gaseous electrode, you have to use either graphite or platinum. Why is that? I'll let you know in some time. Now it's a complete cell representation. Is it clear? Is it clear? Wonderful. Great. Perfect. Moving ahead. Since you got to know from the cell reaction how to represent the cell, you got to know. Yeah, you got to know from the cell reaction how to represent the cell. Now there is something that is a little more important. And what is that? Let's have a look. Let's have a look. Just a second. Something a little more important now. Now, it's going to be something which is really very important. What is that? How to write the cell reactions from the given cell. How to write the cell reactions from the given cell. Now, what does it mean? Now, I'm going to give you a cell. I'll be giving you a cell representation. From the cell representation, we have to write the cell reactions and all the other things too. See, for example, our cell is like this. Zinc solid gives zinc dye positive aqueous, salt bridge, copper dye positive aqueous gives copper solid. This is, for example, the cell, okay? So, from this particular cell, I have to see what will be the cell reactions happening in the cell. See, one thing is clear. This is the salt bridge. On the left side, I would have used the zinc rod. On the right side, I have used the copper rod. I have connected them externally and internally. Then I would have got a complete cell, right? And this is how your cell is represented. Now, from this cell representation, how do I write the cell reactions? That's important. That's important. Understand? Understand now. So, dear students, you know, this is the salt bridge. On the left side of it, we always write the anode. We always write the anode. So, let me write the reaction which will be taking place at anode. What happens at anode? Oxidation takes place. What happens at anode? Oxidation takes place, right? See, zinc is getting converted into zinc dye positive. At anode, zinc is getting converted into zinc dye positive. You can check it out. 0 to +2. Increase in the oxidation state means oxidation, loss of electrons. Your zinc is getting converted into zinc dye positive. So, zinc solid will be losing 2 electrons and will be getting converted into zinc dye positive. Zinc solid will be losing 2 electrons, then it will be getting converted into zinc dye positive. Correct? Reaction at anode. Similarly, if I ask you what is going to be the reaction at cathode, reduction takes place. Reduction takes place, gain of electrons. This is your cathode. Copper dye positive is getting converted into copper solid, +2 to 0. Decrease in the oxidation state means reduction, gain of electrons. So, copper dye positive will be gaining some electrons, then it will be getting converted into copper solid. So, copper dye positive aqueous will be gaining some 2 electrons, then only it will be getting converted into copper solid. So, you wrote the reaction at anode, you wrote the reaction at cathode. Now, dear students, you have to add these two reactions. But I told you in the beginning itself, till the electrons are not balanced, you are not supposed to add. But right here, electrons are balanced. So, you can directly add. You can directly add. Okay. So, when you add these two reactions, these two electrons will get cancelled. The net reaction is going to be zinc solid plus copper dye positive aqueous. It gives zinc dye positive aqueous plus copper solid. This is your net reaction. This is our net reaction. Okay. This is our net reaction. Now, dear students, after writing the net cell reaction, if I ask you how many moles of electrons got exchanged in the net cell reaction, N. 2 moles of electrons got exchanged in the net cell reaction. It's getting cancelled out. 2 moles of electrons are getting exchanged in the net cell reaction. Number 1. Number 2, if I want to write the expression for reaction quotient, how do we write the expression for reaction quotient? You would have studied in your equilibrium as well. How do we write the expression for reaction quotient? Do you know? Do you know? How do we write the expression for reaction quotient? It's simple, yaar. How do you write the expression for reaction quotient? The same way, the way you write the expression for equilibrium constant, in the similar way, you write the expression for reaction quotient. So, see exactly how. You'll be always starting with the product. This is my product and this is my product. That reactant or product which is in aqueous state, you'll be using the term concentration for it. This is an aqueous state. I'll be using the term concentration for it. So, I'll be writing concentration of zinc dye positive raised to the power its stoichiometric coefficient, that's 1. I've got one more product, that's copper, but it's in solid form. That reactant or product which will be in solid form, it's ectomass. You don't have to consider it. that reactant or product which is in solid form, you don't have to consider it. So this part is done, right? Divided by. Now come to the reactant side. This part is done already. Nothing to do with this one. This is an aqueous state, so use concentration. So it's copper dye positive concentration raised per stoichiometric coefficient 1. So this is how you write the expression for QC, reaction quotient. This is how you write the expression for QC, that's reaction quotient. So you got to know here 3 things. 1, how to write the net reaction, how to get the value of N, and how to write the reaction quotient expression. Let me take one more important example so that you can understand it properly, right? Okay, one more example. Understand properly. Let's say I have got some galvanic cell. Let's say I have got some galvanic cell whose, just a second. Wait. Just a second, guys. All right. Let's say this is one galvanic cell that's given to me, and from this particular galvanic cell, I have to write the net cell reaction, number 1. Number 2, I have to get the value of N. Number 3, I have to write the QC expression as well, right? So same procedure again I'll be following, but be careful now and see how exactly I'll be doing it. First of all, these 2 lines, they represent your salt bridge. On the left side of the salt bridge, we'll be always writing the anode. On the right side of the salt bridge, I'll be always writing the cathode. So we wrote anode and cathode first. We identified our anode and cathode. Yes? Now, first of all, at anode, what happens? At anode, oxidation takes place, right? Oxidation takes place, loss of electrons. At anode, your H2 is getting converted into H positive. The oxidation state here is 0. Here it's +1, right? 0 to +1. 0 to +1. Increase in the oxidation state, right? 0 to +1. Increase in the oxidation state. Oxidation, loss of electrons. Perfect. So what should be the reaction taking place at anode? See how exactly you are going to do it. So at anode H2 gas has to get converted into H positive. H2 gas has to get converted into H positive aqueous. Now how do I write this reaction exactly? See, it is 0 to +1. Increase in the oxidation state means oxidation means loss of electrons. So basically when this H2 will be getting converted into H positive, this H2 will be losing electrons. Now the point is how many? See, 0 to +1, calculate the change in the oxidation state. Final minus initial. Final oxygen state minus initial oxygen state. The value is 1. 1 is the change for 1 atom, but I have 2 atoms here. So this H2 will be losing 2 electrons, and then it will be getting converted into 2 times H positive. I hope you got it. Yes? Perfect. This is the reaction taking place at anode. In the similar way, if I ask you what is the reaction taking place at cathode? Guys, it's simple. It's evident, right? It's evident. H2 has to get converted into H positive. You know, if you will be having one hydrogen atom will lose 1 electron and will get converted into H positive. If you will be having H2, 2 hydrogen atoms, they'll be losing 2 electrons and getting converted into 2 times H positive. As simple as that. Nothing else. What is the reaction taking place at cathode? At cathode, what happens? Reduction. Tin is in +4 oxidation state and it has to go from +4 to +2. Decrease. Decrease in the oxidation state means reduction, gain of electrons. So Sn +4 will be gaining 2 electrons. Sn +4 aqueous will be gaining 2 electrons. Then only it will be getting converted into Sn +2 aqueous. Okay. Now if I ask you whether we can add these 2 reactions or not, whether we can add these 2 reactions now or not, what do you think? We cannot add the reactions until electrons are balanced. But electrons are balanced in both the ones. Sorry. The electrons are exactly balanced in both the reactions. So, I can directly add these 2 reactions. So, this 2 and this 2 got cancelled. So, my net reaction has to be H2 gas plus Sn +4 aqueous. What does it give? 2 times H positive aqueous, and with this Sn +2 aqueous. So this is my net reaction. Now dear students, how many moles of electrons got exchanged? I must say 2 moles of electrons got exchanged in the net cell reaction. 2 moles of electrons got exchanged in the net cell reaction. Now it is the time to write the reaction quotient expression. Start with the product. Start with the product. Start with the product. H positive in aqueous form. Use the term concentration. So it's concentration of H positive raised power stoichiometric coefficient, that's 2. Sn di positive is also in aqueous state. So use the term concentration. So it's concentration of Sn di positive raised power stoichiometric coefficient, that's 1, divided by. This is in gaseous state. The one which is in gaseous state, use the term partial pressure for it. Partial pressure of H2 raised power stoichiometric coefficient. This is also in aqueous state. So it's concentration of Sn plus 4 raised power stoichiometric coefficient, that's 1. So this is how you write QC wala expression. Perfect. Clear to everyone? Is it clear to everyone? Is it clear to everyone? Quickly. It should be clear to everyone. It should be clear to everyone. One more example wherein you can do a mistake. One more example wherein you can do a mistake, right? See, understand. Let's say there is some galvanic cell which is given to us, right? This is a galvanic cell which is given to us. From this particular galvanic cell, we have to write the cell reaction, etc., everything, okay? Right? So what I'll be doing, on the left side, we know we always write the anode. On the right side, what do? We always write the cathode. Anode and cathode. Now, you know, at your anode, what happens? At the anode, oxidation takes place. Loss of electrons. Iron here is in +2 oxygen state. It has to go from +2 to +3. Increase in the oxidation state. Oxidation, loss of electrons. So iron di positive has to go to Fe tri positive. So I would say Fe di positive aqueous will be losing 1 electron and will be getting converted into Fe tri positive. So basically Fe di positive, it will be losing 1 electron and then only it will be getting converted into Fe tri positive. Yes? And at the same time, dear students, what is happening at the cathode? At cathode, reduction takes place. By the way, you must be thinking, why I wrote 1 over here, right? It's +2 to +3. Calculate the change in oxidation state. Final minus initial, the value is 1. And I have got only 1 ion here, right? That's why I wrote 1 here. Correct? In the similar way, let me write the reaction taking place at cathode. At cathode, what happens? Reduction. Now understand. Chromium here is in +6 oxidation state when you calculate it. Here it's in +3 oxygen state. So +6 to +3 means decrease in the oxidation state. +6 to +3 means decrease in the oxidation state. And decrease in the oxidation state means reduction, gain of electrons. So basically I must say Cr2O7 di-negative aqueous has to gain some electrons, then only it will be getting converted into what? Then only it will get converted into Cr tri-positive aqueous. Now complete this reaction. +6 to +3, calculate the change in the oxidation state. Final minus initial. The value comes out to be 3. 3 is the change in the oxidation state for 1 atom of chromium, but I have 2 atoms. 3 2s are 6. So this Cr2O7 di-negative will be gaining some 6 electrons and then only it will be getting converted into 2 times Cr tri-positive here. I hope you got it. I hope you got it. Now, my dear students, understand one more thing. Understand one more thing. Whether I can add these 2 reactions directly or not. Can I add these 2 reactions directly or not? Say yes or no. I want to see. Quickly in the chats. Can I add these 2 reactions directly or not? Can I add these 2 reactions directly or not? Yes or no in the chats, everyone. Yes or no in the chats, everyone. Everyone, yes or no in the chats, quickly. Absolutely not. Yes, perfectly done. Over here, you have got 1 electron, you have got 6 electrons. So first of all, you have to make the electrons balanced. So multiply with 6. When you multiply with 6, it's going to be 6 times. This will be 6 times, and here it's going to be 6 times. Since you have multiplied the reaction by number 6, now add the 2 reactions. So this 6 and this 6 got cancelled. So if I ask you, how many moles of electrons got exchanged? You'll say 6 moles of electrons got exchanged. Now add the two reactions. When you add the two reactions, the net reaction has to be 6 times Fe di positive aqueous plus Cr2O7 di negative aqueous. It gives 6 times Fe tri positive aqueous, and with this you'll be writing 2 times Cr tri positive aqueous. Perfect. Okay, now if I ask you whether this is a complete reaction or not, if I ask you whether this is a complete reaction or not, it's still not the complete reaction. You have to make it complete. You have to balance it. You have to balance it in acidic medium. You have to balance the whole reaction in acidic medium. Yeah? And how will you balance it now? See, over here we have got 7 oxygen atoms. On the right hand side there is no oxygen atom. So which side is oxygen deficient? It is basically the right side which is oxygen deficient. It is the right side which is oxygen deficient. Right? On left side we have got 7 oxygen atoms. On right side we have got no oxygen atom. So right hand side is oxygen deficient. Right? In order to balance the oxygen atoms, you have to add the water molecules. So this side is oxygen deficient. There is 7 oxygen deficiency. So add 7 water molecules. Add 7 water molecules. Okay. Now on right hand side you got H hydrogens. 14 hydrogens you have. 14 hydrogens. On left side there is no hydrogen. So on left side what you'll be doing? On left side you will be adding 14 H positives. So do remember, in acidic medium oxygen is balanced by adding water molecules and hydrogens are balanced by adding H positives. Now it's a complete cell. Now it's a complete reaction. It's a balanced reaction now. If it is a complete balanced reaction, now it is the time to write the reaction quotient, QC. Let me see whether you can write the QC expression properly or not. Start with the product. It's an aqueous form. You'll be using the term concentration for it. So it's going to be concentration of Fe tri positive raised power 6. It's stoichiometric coefficient. Look at one more product. It's an aqueous form. So concentration of Cr tri positive raised power, its stoichiometric coefficient, that's 2. This is a liquid form. Solids and liquids, they are not considered basically. Their active mass is taken as unity. Leave that aside. Just remember, solids and pure liquids, they are not taken into consideration. So let's not take this H2O. Divided by. Come to the reactants. This is in aqueous form. So its concentration of H positive raised power stoichiometric coefficient, that's 14. This is an aqueous form. So its concentration of Fe di positive raised power its stoichiometric coefficient 6. And this is Cr2O7 di negative concentration raised power its stoichiometric coefficient 1. So this is how you write the reaction quotient as well. Right? Perfect. So these are very, very important points. Basically, when we study the Nernst equation, when we learn the Nernst equation, in the Nernst equation, the general procedure is the same. First, you have to write anode reaction, cathode reaction, net reaction, N value, right? And then you have to write the QC expression. So all these things you have to do basically. All these things you have to do basically. Okay? Perfect? Perfectly done? Now, since you got to know how to write the net reaction, etc., etc. Okay? Now it is a time to have a look on something called as electrode potential. So what is electrode potential? How do you define the electrode potential? Let's have a look. Electrode potential is basically, it is defined as the potential difference that gets created between the rod and electrolytic solution. Between the rod and the electrolytic solution. What is meant by it? Let me have some water. Guys, is everything clear till here? Say once in the chats. Is every single thing clear till here? Let me know quickly in the chats. Give me some thumbs ups in the chats if every single thing is clear. I can see everyone has not subscribed the channel yet. Yeah. Okay, cool, perfect. Yeah, questions, everything will be done and dusted. Just wait. Everything will be done. Thank you so much. Someone is saying, will we be able to finish? See, till I'll be able to stand, I'll be teaching you. Once I start falling, then maybe I can teach you from the chair or something. And then there'll be a time when my hands will start shivering. At that time, I'll stop. Yeah. Okay, let's move on. Let's move on, guys, now. So basically, this electrode potential, it is defined as the potential difference that gets created between the rod and the electrolytic solution. What is meant by it? How can we understand it? Imagine like this. For example, this is the container which we have. In this container, let's say you have taken zinc sulfate in the container. And this zinc sulfate, let's assume it got completely dissociated into its ions. Right? In this container, I had taken zinc sulfate, and this zinc sulfate, it got completely dissociated into its ions. So can I say in this container, we have got equal number of cations and anions? Yes, right now we have got equal number of cations and anions. Right? So this solution is right now electrically neutral. It's completely neutral. It's completely neutral. Now, dear students, I'm going to introduce one zinc rod here. This is a zinc rod here. Can I say I got an electrode? This setup I'm calling as electrode. This is the electrode, right? I'm calling this setup as electrode. Now, this electrode, it can behave like the anode or even can behave like the cathode. If it behaves like the anode, if this electrode behaves like the anode, what happens then? This electrode, if it behaves like the anode, oxidation will happen. Oxidation will happen, right? So basically the rod, the zinc rod, it's made up of zinc atoms, correct? Those zinc atoms will undergo oxidation. Those zinc atoms will undergo oxidation. That means the zinc atoms, they'll lose electrons. They'll get converted into zinc di positive. Correct? So initially there were equal number of cations and anions in the container. Now the rod is undergoing oxidation. The rod, which is made up of zinc atoms, those zinc atoms are undergoing oxidation, getting converted to zinc di positive. And these zinc di positives are entering into the solution. When this extra zinc di positive enters into the solution, so the solution gets the positive charge. Solution gets the positive charge. And these two electrons, they are accumulated on the rod, right? Due to which this rod gets which charge? This rod gets negative charge. Look at it carefully. Can I say the rod got negative charge and the solution got positive charge? Absolutely. Rod got negative, solution got positive. Rod got negative, solution got positive. So can I say a potential difference got created between the rod and the solution? Absolutely, a potential difference got created between the rod and the solution. This potential difference which is getting created between the rod and the solution, this is something which we call as electrode potential. Yes? This is something which we call as electrode potential. I hope you got it. This potential difference which got created between the rod and the solution, this is something which you call as electrode potential. Perfectly done? And this electrode potential, which is basically the potential difference getting created between the rod and solution, this potential difference, this electrode potential, it is represented by what? It's represented by E. It is represented by E. Okay? Number one. Number two. This electrode potential which I am representing by E, it is further classified into two types. This E is further classified into two types. One is called as oxidation potential. One is called as reduction potential. The potential difference which is being created between the rod and the solution, that's called as electrode potential in general. Now I am dividing it further into two types. Oxidation potential and reduction potential. How do I represent the oxidation potential? Either you can represent it with EOX or you can represent it like this. E of M change into Mn positive. M change into Mn positive. See, M change into Mn positive. Let's say I've got the general electrode in which I've got the metal rod M introduced into its own ions, Mn positive. Right? So, look at the oxidation state of M here, it's 0. Look at the oxidation state of M here, it's plus N. 0 to plus N means increase in the oxidation state. Increase in the oxidation state means oxidation. That means this term, it represents what? It represents the oxidation potential. Now similarly, reduction potential you can represent in this way. E of Mn positive. E of Mn positive change into M solid. E of Mn positive change to M solid. You can check it out too. The oxidation state of M over here, it's plus N. Here it is 0. Plus N to 0. Decrease in the oxidation state means reduction. Reduction means this whole term, it represents the reduction potential. Yes? Correct? Now, dear students, one more important point. Electrode potential, when it's measured under standard conditions, when it's measured under standard conditions, electrode potential when measured under standard conditions is then termed as standard electrode potential. It is then termed as standard electrode potential. And this standard electrode potential is represented by E naught. It is represented by E naught. Now you must be thinking what these standard conditions are. What these standard conditions are. Standard conditions are when the pressure is kept as 1 atm or 1 bar, you can say. When the temperature is kept constant, generally 25 degrees centigrade. And when the concentration of electrolyte in the container is kept 1 molar. These are the things which define the standard conditions. So whenever from now onwards I'll say the standard condition. Standard condition means I've kept the pressure 1 bar or 1 atm. I've kept the temperature constant, generally 25, and I've kept the concentration equal to 1 molar. Okay? Perfect? So whenever electrode potential is measured under standard conditions, you do not call it as electrode potential then. You call it as standard electrode potential. Yes? Now, if I talk about this standard electrode potential carefully, E naught, standard electrode potential. Well, dear students, I can classify this E naught into 2 categories now. Standard electrode potential. Standard electrode potential. We can classify into 2 types, right? Let me start from here, E naught. E naught. I can divide it into 2 categories. One is called as standard oxidation potential and one more is called as standard reduction potential. One is called as standard oxidation potential and one more is called as standard reduction potential, right? Dear students, the standard oxidation potential you can represent like this as well. E naught of M changes to Mn positive. E naught of M changes into Mn positive, right? You can check it out. 0 to plus N, increase in the oxidation state, oxidation. That means this is standard oxidation potential, or you can just represent it with like this, SOP, standard oxidation potential. Similarly, standard reduction potential, you can represent it like this, E naught of Mn positive change into M, or you can directly call it as SRP, standard reduction potential. Now, there is one thing which I would want you guys to remember. Every element has a fixed. Every element has a fixed SRP or SOP value. Every single element, it has got a fixed SOP, fixed SRP. And this standard oxidation potential of an element is calculated with the help of a reference electrode. That reference electrode is called as hydrogen electrode. So I'm writing a statement, SOP as well as SRP of an element. Is measured with the help of a reference, with the help of reference electrode, and that reference electrode is called as SHE, standard hydrogen electrode. That's called as standard hydrogen electrode. Yes? That's called as standard hydrogen electrode. At the same time, there are a few more things which I would want to discuss with you. Do remember, for every element, SOP is equal to minus SRP. For example, I'm writing something like this. Let's say I'm writing E naught of M changed to Mn positive is equal to 3.1 volts. Can you let me know in the chats? Is it SOP or SRP? Am I mentioning SOP or SRP? Quickly. Am I mentioning SOP or SRP? Quickly. M changed to Mn positive. M changed to Mn positive. 0 to plus N. Increase in the oxidation state. Increase in the oxidation state. Oxidation. That means SOP. Absolutely. So this is your SOP. This is SOP. For the same element, I want to write its SRP. In order to write the SRP, I'm just going to reverse it. It's going to Mn positive gives M. Now it's going to be minus 3.1 volt. Now it's not SOP, it's SRP now. It's SRP now. Got it? So you just have to reverse the sign, that's all. Okay? Now there are questions which are asked people from this oxidation reduction potential. Before solving the questions, I would want you guys to remember a few more things. And what are few more things? Have a look. Do remember, more the standard oxidation potential, more is the tendency to undergo oxidation. More is the tendency to undergo oxidation. Better is the reducing agent. Better is the reducing agent. More is the reducing power. More is the reducing power. First statement. I'll show its application in some time. Similarly, more the standard reduction potential, more is the tendency to undergo reduction. More is the tendency to undergo reduction. More is the tendency to undergo reduction. Better is the oxidizing agent. And more is the reducing power. These are two very important statements, guys. These are two very important statements. These are two very important statements. Let's try to understand them. Let's try to understand these, okay? Let's try to understand these statements. For example, just take the screenshot of this slide once. Just the screenshot, because I want you to take this. Take the screenshot of this slide once because I have to show you certain questions. Because I don't want to change the slides afterwards. Yes, this is reducing power, absolutely. This is the reducing power, absolutely. All right. Now look here now. Let me give you one simple question so that you can understand it properly. Did I make any mistake while writing? More the SRP, more is the tendency to undergo reduction, better oxidizing agent. Oh, sorry. This oxidizing power. Okay. Got it now? Perfect. Now take the screenshot. Perfect now. You tell me the answer of these questions now, okay? For example, I have got few elements A, B, C and D. I have got few elements A, B, C and D. Here I am writing E naught. E naught of M gives M positive. Okay? Here I am mentioning that E naught of, again, E naught of M gives Mn positive. And here I am mentioning as E naught of Mn positive change to M. Here also I'm mentioning that E naught of Mn positive change to M. These are all the things which I mentioned, right? Now, understand. Let's say the value here I'm giving you as 1.1. It's 2.1 volts. It's 3.1 volts. It's 4.1 volts. First of all, you tell me, you guys are going to tell me whether this term indicates SOP or SRP. Whether this term indicates SOP or SRP. What do you think? Quickly. What does this term indicate? SOP or SRP? SOP or SRP? Quickly. SOP or SRP? See, it is M changing into Mn positive. So 0 to plus N, increase in the oxidation state. And increase in the oxidation state means oxidation. So this is definitely SOP. These are all the values of SOPs. These are the SOP values of all these elements, right? So which SOP value you find maximum? Which SOP value is maximum? I'll say this SOP is maximum. This SOP is maximum, right? More the SOP, more is the tendency to undergo oxidation, better reducing agent. So if you have to identify which one among the all, as per these values, is the better reducing agent, this is the better reducing agent. If it is the better reducing agent, its reducing power will be definitely more. So you can categorically arrange them on the basis of increasing, decreasing order of reducing agent capability, reducing power capability, right? Number one. Number two, look at this particular value. Tell me in chats whether this is SOP or SRP. Let me know in the chats carefully. Achha, by the way, see, this D, better reducing agent, more reducing power. Better reducing agent means bad oxidizing agent. More reducing power means less oxidizing power. Just reverse the things. That's all. Alright, again this is SOP. As I can see your chats, you're all telling this SOP. Now, which SOP value you are seeing maximum here? This is now the maximum SOP. This is now the maximum SOP. More the SOP, more the SOP, more the tendency to undergo oxidation, better reducing agent. Now the better reducing agent is this one. Now it will be having more reducing power as well. Done, understood? Yeah? Simple. Now we will look at the third scenario. E naught of Mn positive change to M. Look at this one. Tell me in the chats whether this is SOP or SRP now. Tell me in the chats whether this is SOP or SRP now. Quickly. Now, as you can see, Mn positive change to M plus N to 0. Decrease in the oxidation state means reduction. Reduction means gain of electrons, right? So this is SRP values. These are all SRP values. This SRP I can see maximum here. More the SRP, more the SRP, more the tendency to undergo reduction, better oxidizing agent. So this is the better oxidizing agent. It will be having more oxidizing power. Absolutely. Perfectly done, understood. Wonderful, guys. Good job. Yes? Perfecto. Got it. So let's try to do certain questions. Then only I can see whether I can get that confidence that you got it properly. Yeah? Just a second. Give it a try. Give it a try quickly. Let me see what should be your answer. I'm giving you 30 seconds ka time. I'm giving you 30 seconds ka time quickly. Thirty seconds time I'm giving you. Give it a try, people, quickly. noise, noise. All right, let's have a look. Let's have a look now. Let's see how it's done. First of all, in all the reactions, as you can see, electrons are being added. Gain of electrons is happening basically. Gain of electron means reduction. So first reaction is the reduction reaction. Mg dipositive is gaining electrons. So Mg dipositive is undergoing reduction. Mg dipositive undergoing reduction. Zinc dipositive undergoing reduction. Nickel dipositive, Fe dipositive, all these undergoing reduction. So that means these values are SRP values. These are SRP values. These are SRP values of what? These are SRP values of all these ions. SRP values of all these ions. Correct? What do I have to identify? I need to identify the reducing agent. I need to identify the reducing agent. You know, your reducing agent undergoes oxidation. You know that, right? Reducing agent undergoes oxidation. And the one which undergoes oxidation easily, that will be better reducing agent. Now, which one can undergo oxidation easily? The one which will be having maximum SOP. The one which will be having maximum SOP will be undergoing oxidation easily, better reducing agent. But are these SOP values or SRP values? These are SRP values. So I need to reverse the reactions. When I reverse the first reaction, for example, it becomes like this. Magnesium gives Mg dipositive plus 2 electrons. I have reversed the first reaction. Now I can say this magnesium is undergoing oxidation. It's losing electrons. This magnesium is undergoing oxidation. Correct? If magnesium is undergoing oxidation here, what should be the standard oxidation potential of magnesium then? Standard oxidation potential of magnesium should be, just reverse the sign, plus 2.37 volts. You got it? So what my point here is this minus 2.37 volts. It is the standard reduction potential of Mg dipositive. And this plus 2.37 is standard oxidation potential of magnesium, because I have reversed the reaction. Got it? Now reverse the signs everywhere. Where do you find the maximum SOP? Maximum SOP, when you reverse the sign, it will be plus 2.37, plus 0.76, plus 0.73, plus 0.04. So maximum SOP will be for magnesium. If magnesium has got maximum SOP, so it will undergo oxidation easily, better reducing agent. Done and dusted, right? Done and dusted. Quickly. Yes or no in the chats? Yes or no in the chats? I hope it's super clear to everyone. I hope it's super clear to everyone. All right, let's have a look on a few more things. Acha, by the way, has everyone subscribed to the channel yet? Has everyone subscribed to the channel? Just asking. Say yes or no. Of course, nobody is going to say no. Has everyone subscribed to the channel? Yes or no? The ones who have not done yet, please do. I just want to see the subscriber count increasing. I just want to see the subscriber count increasing right now. All right. People are asking for the breaks. When is the next break? I gave you the break 5 minutes back only, right? Or what time did I give you a break? We started at 2 again, right? So it's been 1.5 hours. Okay, let's wait for some time. See now. Now is one more point, EMF, electromotive force. EMF of the cell. How do you calculate? So I'll be using the term, first of all, standard EMF. The term I'm using here, that is standard EMF, okay, which I use frequently. Standard EMF, how do we calculate? Basically, when you talk about the galvanic cell, when you have the galvanic cell, right? In the galvanic cell, what happens basically? Current is generated. Current flows only due to potential difference. You know it. If I talk about the galvanic cell, which has got 2 electrodes connected externally as well as internally, correct? What is the work of the galvanic cell? What does galvanic cell do? It generates current. It produces current. Now, current flows only due to potential difference. So that means the electrodes which you have taken, between them there must be some potential difference due to which current is flowing. Between them there must be some potential difference due to which current is flowing. The maximum potential difference between the electrodes when the cell is not in use. The maximum potential difference between the electrodes when the cell is not in use, when no current is drawn from the cell, that's something which you call as EMF. That's something which you call as EMF. Now I'm talking about standard EMF. That means I'm measuring the maximum potential difference between the electrodes under standard conditions. Right? Yes? So people, standard EMF which I'm representing by E naught cell. Only remember this thing. E naught cell is always equal. E naught cell is always equal. E naught cathode minus E naught anode. E naught cell, it's always equal to what? E naught cathode minus E naught anode. But here, do remember a few more things. This E naught cathode is something which you call as standard reduction potential of cathode. And this E naught anode is something which you call as standard reduction potential of anode. So when you use this particular result, to calculate the E naught cell will be equal to E naught of cathode minus E naught of anode. This is SRP of cathode, this is SRP of anode. Now understand what I'm going to say. Properly understand. For example, I'm giving you this kind of a scenario. Let's say I've got 2 electrodes. A and B. For example, I've got 2 electrodes A and B. Let's say E naught of A positive gives A. Let's say it's equal to 3.1 volts. Similarly, let's say E naught of B positive change to B. It's equal to 5.1 volts. How many electrodes I have? I've taken 2 electrodes. Electrode A, electrode B. Right? Now, dear students, if I connect these electrodes externally as internally, if I connect these 2 electrodes externally as well as internally, I'll be getting a complete cell for sure, right? That complete cell which I am getting, I need to calculate its E naught cell. That complete cell which I am getting after connecting these 2 electrodes, right? I need to calculate its E naught cell. E naught cell is equal to E naught of cathode minus E naught of anode. Correct? So first of all, I have to identify among these 2 electrodes which one is cathode, which one is anode. Now identify. What do you think? Identify now. First of all, this is SRP. This is also SRP. Which one is having more SRP? This is the more SRP value. More the value of SRP, more the tendency to undergo reduction. And reduction happens at cathode. So this has to be a cathode and this has to be anode. Khatam. Right? This has to be a cathode and this has to be anode. Now, dear students, it's going to be E naught cell is equal to E naught cathode, standard reduction potential of cathode, it's 5.1 volt, minus standard reduction potential of anode, 3.1 volts. The value comes out to be 2 volts. So this is your E naught cell. Got it? This is your E naught cell. Is it clear? Okay, one more I'm giving you. Let me see if you can do it or not. For example, I'm writing E naught of M changed to Mn positive is equal to 5.2 volts. Then I'm writing E naught of B changed to B positive is equal to 6.7 volts. I've got two electrodes. This is the first one, M electrode, second one, B electrode. Now I'm going to connect them externally as well as internally. I am going to connect them externally as well as internally. When I connect them, I'll be getting a complete cell, absolutely. And I need to calculate standard EMF of that complete cell. What do you think? Quickly. I need to complete the standard EMF of that complete cell. I need to calculate the standard EMF of that complete cell. Quickly. So first of all, you need to know out of these two electrodes, which one will be cathode and which one will be anode. Understand? This is M gives Mn positive. So if I reverse it, Mn positive gives M, it will be minus 5.2 volts. If I reverse this, it's going to be B positive gives B is equal to minus 6.7 volts. Now I got SRP of both. Now which one is more SRP? This is the more SRP value. More the SRP, more the tendency to undergo reduction, right? And reduction takes place at cathode. So this has to be a cathode, and over here, this has to be an anode, right? You identified your cathode and anode. Since you identified your cathode and anode, now you are simply going to write E naught cell. And E naught cell is nothing, that is just E naught of cathode minus what? Minus E naught of anode. So write SRP of cathode first. Write SRP of cathode, it's minus 5.2, minus times. Write SRP of anode. SRP of anode is minus 6.7. Solve it, and the answer will be in volts. I hope you got to know how to calculate E naught cell, right? You got to know how to calculate E naught cell? These are all the false rumors which people are spreading in the chats that NEET is postponed or something like that. There is nothing, no announcement as such. These are nonsense people. Okay. So relax. These people take 5 to 6 years for NEET to get qualified. You don't worry about that. Let them carry on. Someone is saying, sir, speed thodi badhao na. Maybe I should teach 10% of the chapter then. You'll be fine, right? You can use SOP values as well. Someone is saying, please do important topics. Wow, you're done with your preparation. You just want the important topics now. Yeah? Rest, everything is done and dusted. Your biology, physics is up to the mark. Now you just want to have a look on the important topics to shoot the bullseye, yeah? Nonsense. I'm teaching you everything in detail. Every single thing in detail. I'm not skipping a single thing. If we were not able to finish the whole in one session, maybe I'll take 2 sessions. What's wrong in that? Nothing, right? But everything has to be covered. Yes, I've studied in Chennai. So, what should be the answer of this question now? Guys, just study, no? Just study. Why are you asking me why you left that, why you left this? That's my personal choice, right? It depends on me. Where I want to work, I'll work in that organization. You've got nothing to do with that. Just see if you are getting benefited from the session. That should be your main, utmost motive. Nothing else. All right, so majority of the students are coming out with option B. Let's see exactly, is the answer going to be option B or not? All right, the question is, standard oxidation potential for the half cell reactions are given. So basically, this is the standard oxidation potential of zinc, which is undergoing oxidation here. This is the standard oxidation potential of iron, which is undergoing oxidation. What do I need to calculate? I need to calculate the EMF of this cell reaction. This is the cell reaction. This is the cell reaction. I need to calculate its E naught cell. I need to calculate its E naught cell. E naught cell is E naught cathode minus E naught anode. E naught cathode means SRP of cathode. E naught cathode means SRP of cathode minus SRP of anode as well. Minus SRP of anode as well. Now, first of all, you have to identify which one is cathode and which one is anode, right? You have to identify. See, your zinc over here, it has got the oxidation 0. Here, it has got the oxidation state of +2. 0 to +2 means increase in the oxidation state, oxidation, right? So, it has to be your anode. Similarly, this has to be your cathode. So, you identified the anode and cathode. Now, it's going to be E naught of cathode, SRP of cathode, SRP of iron, SRP of iron, right? So, this is SOP, but what do I need? I need SRP, so reverse the sign. It's minus 0.41 minus SRP of anode. Anode is your zinc and SRP of zinc. So, this is SOP of zinc, just reverse the sign. It is minus 0.76. Now, we can solve it and get the desired answer in volts. I hope it's clear. I hope it's clear, right? Okay. Now, dear students, one more thing. One more thing. One more thing. What is that? That is the relation between delta G and E cell. I'm not going to derive it. Let's just write the relation and try to utilize it. A relation between delta G and E cell. Let me tell you delta G, which is the Gibbs free energy change. Gibbs free energy change. Delta G for a cell is always equal to minus NF E cell. Delta G for the cell is always equal to minus NF E cell. Now, first of all, what is this delta G all about? This delta G is basically the Gibbs free energy, which is also called as available energy, or leave this aside, just write Gibbs free energy. What is N over here? N represents the number of moles of electrons exchanged in the net cell reaction. F represents the Faraday's constant, and its value is basically 96500 coulombs. And this E cell represents the EMF of the cell. One thing, just tell me one thing, is E cell and E naught cell same? Is E cell and E naught cell same? Is E cell and E naught cell same? Quickly. Is E cell and E naught cell same? No, right? Wonderful, good. E cell is, what is E naught cell? E naught cell is basically the maximum potential difference between the electrodes when the cell is not in use, when no current is drawn from the cell, but under standard conditions. If I change the standard conditions, we don't call it then the E naught cell, we call it normally as E cell. E cell is EMF of the cell under non-standard conditions. E naught cell is EMF of the cell under standard conditions. I hope it's clear. I hope it's clear, right? Number one. Number two, if I write the same equation under standard conditions, then it becomes delta G naught is equal to minus NF E naught cell. It becomes delta G naught is equal to minus NF E naught cell. Correct? Right? At the same time, one more thing. One more thing. First of all, I told you in the galvanic cell there are two electrodes. You just need to connect them externally and internally. You will be getting a cell. No doubt you can make a lot of cells. You can make millions of cells. You just have to take 2 electrodes, connect them externally, internally. You'll be getting definitely a one complete cell. Now the point is whether that cell will be working or not. Whether that cell can produce current or not. That is the point. That's also the point. See, you will take 2 electrodes, you will connect them externally, you will connect them internally, you will be getting a complete cell for sure. But the point is whether that cell will work or not. There should be some parameter, right, on which it should depend. Of course, it depends on something. It depends on something. Whenever you take 2 electrodes, when you connect them externally, when you connect them internally, if spontaneously reactions start at anode cathode, if spontaneously, automatically, after just connecting the cell, after just completing the circuit, if spontaneously reaction at anode takes place, reaction at cathode takes place, I would say the cell will work. And for any process, for the reaction to be spontaneous, delta G has to be, delta G for the system at constant pressure and temperature, it should be negative. For any process to be spontaneous, right? For any process to be spontaneous, delta G has to be negative. So I must say something like this. If delta G for the reaction comes out to be negative, if delta G for the cell reaction comes out to be negative, since you know delta G is equal to minus NF E cell, that means minus NF Cl will be negative. When can be this whole term negative? This whole term can be only negative if E cell is positive. If E cell is positive, correct? Now, dear students, this is the criteria. Criteria is if delta G for the reaction comes out to be negative, if delta G for the net cell reaction comes out to be negative, or EMF of the cell comes out to be positive, or EMF of the cell comes out to be positive, then only the cell reactions will be spontaneous. Then only the cell reactions will be spontaneous. And current is drawn from the cell. Okay? First point, important point, right? Whenever from now onwards, you need to check whether the cell will work or not, whether current can be drawn from the cell or not. Either you calculate the value of delta G or you calculate the value of E cell. Perfect? If delta G value comes out to be negative, then cell reactions will be spontaneous. And if cell reactions are spontaneous, that means cell will be working like a normal galvanic cell. Nothing else. Number two, whenever delta G for the reaction comes out to be positive, delta G for the cell reaction comes out to be positive, that means minus NF E cell would be positive. And how exactly? It's only possible if E cell is negative. If E cell is negative. Now you got one more thing. If delta G for the reaction comes out to be positive, we'll say cell reactions will be non-spontaneous. Cell reactions are non-spontaneous, right? And cell does not work. So here the cell won't be working at all. One more thing. If delta G for the reaction comes out to be 0, that means E cell comes out to be 0. We say at that point of time, the cell is at equilibrium. What does that mean? You'll get the idea in some time. The cell is at equilibrium. Do remember these 3 conditions as well. These are some important conditions, okay? Some very, very, very important conditions. Okay? I hope this is clear. Now, till now, I showed you how to calculate the standard EMF of the cell, right? I told you how to calculate the EMF of the cell under standard conditions. But what if conditions are changed? What if conditions were changed? What you will do at that time? What if conditions will be changed? What you will do at that time? That means I'm asking you, how can you calculate the EMF of the cell under non-standard conditions? How can you calculate the EMF of the cell under non-standard conditions? For that, there is one equation which we need to discuss. That is the most important topic from this chapter, the Nernst equation. And this year, for sure, you'll be getting a question from Nernst equation. Because last year 2 questions were asked from Kohlrausch law, so this year they'll ask it from here. Nernst equation. Nernst equation. Have a look. First of all, there is one equation which we have to discuss in thermodynamics. Delta G is equal to, or let me not derive it, let me just give it to you directly. There is no need of derivation at this point of time. Nernst equation can be written like this. E cell is equal to E naught cell minus 2.303 RT divided by NF log of QC. Log of QC. Log of QC. This is first of all the equation which is used, number 1, to calculate the EMF of the cell under non-standard conditions. Under non-standard conditions. Okay. Now first thing, let's have a look on the terminologies which we have here. First is E cell, right? What this E cell is all about? What is this E cell? Let's have a look. This E cell is nothing. It is basically the EMF of the cell. It is basically the EMF of the cell under non-standard conditions. EMF of the cell under non-standard conditions. Now, what is this E naught cell? E naught cell already you know. It is the standard EMF of the cell. It is basically the standard EMF of the cell. Okay. What is this QC? I hope you remember all these things. I have taught you how to calculate. QC is something which you call as reaction quotient. It's called as a reaction quotient, right? This F over here, it represents the Faraday's constant. Faraday's constant. T temperature, R gas constant, and number of moles of electrons exchanged. Now here is a point. If, for example, I'm using the if condition, okay? If for example, I keep the temperature 25 degrees centigrade, that means I'm using 298 Kelvin. If I put the value of R here as 8.314 joules per Kelvin per mole, right? If I put the value of R as 8.314, if I keep the temperature as 298 Kelvin, if I take the Faraday's constant as in 96500 coulombs, then I can modify this equation furthermore. I can write it then, E cell is equal to E naught cell minus 0.0591 divided by N, and it's going to be log of QC. And it's going to be log of QC. In majority of the questions, I'll be using this particular equation to calculate the EMF of the cell. To calculate the EMF of the cell. Right? Is it clear till here? Is it clear till here? Now, dear students, let's have a look exactly on the uses of this equation. Where do we use this particular equation? Where do we use this particular equation? Someone is asking for a break. It is right now 3:50. Let's take a break at 5. Right? But let me teach for an hour because it's important. It's very important. Let me teach for an hour first. Let's take a break at 5. Okay? Cool? Guys, I'm standing. You guys are sitting and reading, right? I'm talking from past 5 hours. And this is completely free of cost. You guys are not giving me anything. If I can do this much, then you should do like double of it, right? Thoda use your brains at times also, no? No, even I did not have lunch also. I just had tea in between. Understand now, have a look. This N is not the N factor here. This N is not the N factor here. This N is number of moles of electrons exchanged. Have a look. Now let's see. let's see where do we use this Nernst equation and how do we use it. That's the point, right? How do we use it? First thing, Nernst equation is used. It is used to calculate Nernst equation. It's used to calculate what? To calculate the oxidation potential of the half cell. Half cell is also called as electrode, okay? Half cell means electrode. Oxidation potential of the half cell under non-standard conditions. Under non-standard conditions. Point number one. It's again used to calculate the reduction potential. The reduction potential of the half cell under non-standard conditions. One more usage of it. The third one. It's used to calculate the EMF of a complete cell. EMF of a complete cell. Under what? Again under non-standard conditions. These are its three important uses. We use Nernst equation for these three purposes. To calculate oxidation potential of the half cell under non-standard conditions, to calculate reduction potential of the half cell under non-standard conditions, to calculate EMF of the complete cell under non-standard conditions. Okay, now let's see how exactly we are going to use it. So first of all, I'll show you the Nernst equation for half cells. Let's see how do we write the Nernst equation for half cells. Let's see exactly how do we use the Nernst equation for half cells. So let's imagine that, let's assume that this is the electrode which we have, this is the half cell which we have, and in this half cell, for example, you have got Mn positive ions. Mn positive ions. You are introducing the rod in the solution containing Mn positive ions, right? So basically, this setup I'm calling as electrode. Now this electrode, it can behave like the anode as well as cathode, right? Let's assume that this electrode behaves like the cathode. Let's assume that this electrode behaves like the cathode. When this electrode behaves like the cathode, there will be a reduction. At cathode, reduction takes place. So what has to be the reaction then? What has to be the reaction? If reduction takes place here, Mn positive in the solution, it is going to collide with the rod. It's going to take n electrons from the rod. So basically, Mn positive aqueous, it's going to take some n electrons from the rod, get converted into M solid. This will be the reaction. If this electrode will be behaving like the cathode, this has to be the reaction then. Once you write this reaction, tell me how many moles of electrons got exchanged. N moles of electrons got exchanged. Can you write the QC expression? Absolutely. Start from the product. It's in solid form. Its ectomass is unity. Leave it aside. 1 divided by concentration of what? Mn positive raised power stoichiometric coefficient 1. Perfect. This is QC. This is QC. Correct? Correct? Now guys, after you write this particular reaction, after you get the QC value, now you can write the Nernst equation. Right now, I want to calculate the reduction potential of this half cell. I want to calculate the reduction potential of this half cell. So, I'll be using the Nernst equation in this format. Instead of E cell, I'll be writing ERED, reduction potential of the half cell, is equal to, now it's going to be E naught RED minus 0.0591 divided by N, and it's going to be log of QC. Instead of QC, it's going to be 1 upon concentration of Mn positive. And in the question, and when you solve the question, all these terms will be given to you. Standard reduction potential of the half cell will be given to you. N, you can easily calculate. Mn positive concentration will be easily given to us as well. Now, here's the point. Here's the point basically. Here's the point. Basically, in this solution, you had an electrolyte. From that electrolyte, you got these ions. From that electrolyte, you got these ions, right? For example, in this particular container, just a second, guys. क्या है?
I'm leaving, so you can have it.
श्रेय सर कहाँ है?
Sure, sir is not there. कहीं गया है?
HSB sir? Where is he?
He's not there.
Seriously?
हाँ.
वो कहाँ है?
हाँ.
Ma'am has
I
got
am
some.
here, okay?
Ma'am
Only
has
I am
got some
here.
food for me.
Exactly. See, I have a proof.
What is it? I have no idea. What is it?
It's a food, obviously. It's
Shukriya.
food.
Thank you so much.
Huh. So, you are teaching them nicely, right? You know na how to teach.
No, I don't know.
Is he teaching you nicely?
No.
Yes.
No.
Is he?
No. This. See what's written here?
I know that.
Good handwriting, no? You wish.
Even my handwriting is
You
better.
wish you had
Oh,
something like
please. Even my handwriting is good. You can ask them. Literally, you can ask them.
अच्छा ठीक है.
Literally. How's my handwriting? Tell me honestly. How's my handwriting? Yes, you should take a break and you should have your meal.
I'll just finish it off. उसके बाद I'll take a break.
Okay,
I'll go
now
down.
I'm leaving this.
Hotel.
Yeah.
ठीक है. Shreyas or HSB?
They are not here.
To call them. Go with them.
So they are busy. They all are not here. So I'm leaving. So I just bought this for you, so you can have it and ask them. See, my handwriting is good. Even my teaching is good.
अच्छा ठीक.
Learn something. Okay. Bye.
अच्छा चलो.
Have it.
Just a second, guys. Okay. Of course, my writing is better, yaar. She cannot compare it with mine. No way. All right, now. So here's the point, basically. Here's the point. In this particular container, you have taken a solution, right? From that solution, you got these Mn positive ions. From that solution, you got these Mn positive ions. Now, if I, for example, increase the concentration of the electrolyte in the container, if I increase the concentration of electrolyte in the container, what will happen? If you increase the concentration of electrolyte, can I say the concentration of Mn positives in the container will increase? Absolutely. Concentration of Mn positives in the container will increase. And dear students, if you are increasing the concentration of Mn positive, that means you are increasing the denominator. So this whole term will decrease. That means this whole term is decreasing. If this whole term is decreasing, that means this whole term is increasing basically. So it is the reduction potential which increases. It is the reduction potential of the half cell which increases. So you got one very, very, very important statement here. You got this very, very, very important statement here. On increasing the concentration of electrolyte, in the container, what is happening to the reduction potential of the electrode? Reduction potential is increasing, right? So dear students, let me summarize it. Let me summarize it quickly. I'm going to summarize it like this. On increasing the concentration, of electrolyte, a reduction potential of the half cell increases. Now, if I ask you a very simple question, let's say this is zinc sulfate in the container. Its concentration is, for example, 2 molar. This is, for example, again zinc sulfate in the container. Its concentration is 5 molar. This is the zinc rod here. This is the zinc rod here. Both the electrodes are same, right? Zinc electrode, zinc electrode. It is just I'm keeping the concentration different. Can you let me know which electrode, which half cell will be having more reduction potential? Can you let me know quickly in the chats? What do you think? Can you let me know which electrode will be having more reduction potential? First one or second one? More the concentration of electrolyte, more is the reduction potential. As simple as that. Nothing else, okay? Perfect. Done. So you got to know how to write the Nernst equation for the half cell. This is how you do it. Achha, by the way, one more thing. Let's say, since you made the electrode to behave like the cathode in the beginning, correct? Now, if you would have made the same electrode to behave like the anode in the beginning, then the reaction would have been opposite, right? It should have been like this. M solid gives Mn positive aqueous, and with this, you'll be writing N electrons. This should have been the reaction. Now, this is the number of moles of electrons exchanged. QC value over here will be concentration of what? Concentration of Mn positive raised power 1. Correct? Since you made sure that the electrode behaves like the anode, that means you are going to calculate the oxidation potential under non-standard conditions, which is going to be E0OX, standard oxidation potential, minus 0.0591 divided by N. It's going to be log of QC. QC is concentration of Mn positive here. So this is how you calculate the oxidation potential of the half cell under non-standard conditions. The way you calculated the reduction potential of the half cell under non-standard conditions. In the similar way, you are calculating the oxidation potential of the half cell under non-standard conditions. Correct? Yes. Now, I can say something like this. I can say, on increasing the concentration of electrolyte, what will happen? Oxidation potential of the half cell will decrease. Okay? On increasing the concentration of electrolyte, reduction potential increases. That means oxidation potential automatically decreases. Do take a note of this thing as well. It's important. It is very, very, very important. Okay? So people, this is how you use the Nernst equation for the half cells, right? Yeah? Now, how do we use the Nernst equation for the full cells, complete cells? Complete cell means, half cell means electrode. Full cell means you have taken two half cells, you have connected them externally, internally, you have got a complete cell. If you want to use the Nernst equation for a complete cell, this is how you are going to write it. EMF of this cell is equal to E0 cell, you know how to calculate. E0 cathode minus E0 anode. N value you already know after adding the reactions, right? QC value you already know. Now let's try to do certain questions so that everything seems clear to us. Okay? Let's try to do some questions now. All right. The first question on the screen. Just first of all say yes or no in the chats whether, if you think you can solve this question. What do you think? Yes, I'll eat afterwards. We'll take a break at 5. I told you, no? Let me know in the chats whether you think you can solve this question. Okay, let's give it a try. Perfect, wonderful. Look at this one. After looking at the question, we are supposed to calculate the oxidation potential of this particular half cell. This is a half cell. Basically, you have taken an iron rod. You have dipped this iron rod into a solution containing FeSO4. You have dipped an iron rod into the solution containing FeSO4, right? That means an electrode got created, half cell got created. You have to calculate the oxidation potential of the half cell when the concentration of FeSO4 in the solution is 0.1 molar, right? How exactly I'm going to do it? First of all, I need to calculate oxidation potential. Since I have to calculate oxidation potential, so I'll make sure that electrode behaves like the anode, because at anode only oxidation takes place. And when the electrode behaves like the anode, oxidation state here is 0. Here it's plus 2. 0 to plus 2, increase in the oxidation state. So Fe solid, since at anode oxidation takes place, loss of electrons. So iron is getting converted into Fe di positive. So iron will be getting converted into Fe di positive aqueous, and with this you will be getting 2 electrons. This is the reaction taking place at anode. The reaction taking place at anode, right? So how many moles of electrons got exchanged? 2. So N value here comes out to be 2. N value you got to know as 2. At the same time, write the reaction quotient. Start from the product. It's going to be concentration of Fe di positive raised by stoichiometric coefficient. That's it. What is the concentration of Fe di positive? It's given to me. 0.1 means 10 raised power minus 1. Raised power 1 only. QC you know. Now you can just use an Nernst equation to calculate the oxidation potential. Oxidation potential is equal to E naught OX. E naught OX. E naught OX. Is this standard oxidation potential or standard reduction potential? This is SRP, standard reduction potential. But we need SOP, standard oxidation potential. So change the sign. So it is plus 0.44 minus 0.0591 divided by N value is 2, and it's going to be log of QC. QC is just 10 raised power minus 1. Now it's a matter of calculation only. 0.44 minus 0.0591 divided by 2. Log of M raised power N is N log M. So minus 1 comes to the front. Log 10 is 1, right? Then you can easily solve this equation. Get the answer in volts. Is it simple? Can you do it from here? Number 1. Let's solve one more question. Let's solve one more question. This is one more question. Calculate the oxidation potential of the following half cell. Calculate the oxidation potential of the following half cell. Have a look. This is the half cell that's given to us. It is basically the hydrogen electrode, right? H2 gas using platinum solid. Using platinum solid. Introduction of H2. See, basically we have the platinum rod. On the surface of the platinum rod, you will find H2 gas. And that rod, whose surface is covered with H2 gas, that is introduced into a solution containing HCl. So you have got hydrogen electrode basically. We are given with hydrogen electrode, right? Now the point is, calculate the oxidation potential of this hydrogen electrode. Since I need to calculate oxidation potential, so let's make sure that the electrode behaves like the anode, right? Because at anode only oxidation takes place. Yeah, at anode only oxidation takes place. Oxidation means loss of electrons. Say, oxidation state here is 0, here it's plus 1. 0 to plus 1. 0 to plus 1. Increase in the oxidation state. Loss of electrons, right? So what should be the reaction? When this hydrogen electrode behaves like the anode, the reaction has to be like this. H2 gas, it gives 2 times H positive aqueous plus 2 electrons. This is the reaction which will be taking place when this hydrogen electrode will be behaving like the anode, right? How many moles of electrons are being exchanged? 2. So N value is 2. Get the QC value. QC. Start from the product. Concentration of H positive raised power 2 divided by, it's going to be partial pressure of H2 raised power 1. What is the concentration of H positive? It's 10 raised power minus 1. 10 raised power minus 1 square means 10 raised power minus 2. Partial pressure of H2 is 10. Right, the value comes out to be 10 raised power minus 3. This is the QC value which we got. This is the QC value. Since you got the QC value, you got the N value. What do we need to calculate? We need to calculate oxidation potential of the half cell, which will be equal to standard oxidation potential minus 0.0591 divided by N, and then it's going to be log of QC. Correct? Since it is the hydrogen electrode basically, I forgot to tell you one thing. For the hydrogen electrode, SOP as well as SRP is 0. For hydrogen electrode, SOP as well as SRP both are 0. Do remember that. Okay, for hydrogen electrode particularly. So this value for hydrogen electrode, that's 0. Since EOX we have to calculate, it's going to be minus 0.0591 divided by N. What is N? N value is 2. And it's log of QC. What is QC? QC we have already calculated, 10 raised power minus 3. Log of M raised power N, N log M. So minus 3 comes to the front. So it's minus 3 log 10. So minus 3 here, log 10, 1. Just solve this, get the answer in volts. That's it. Clear? Is it clear to everyone? Say yes or no in the chats with the thumbs ups, guys, once. Then only I can solve one more. Let me know quickly in the chats. Everyone, if it is clear till here, give me some thumbs ups in the chats. Quickly. Quickly, quickly, quickly. Quickly, everyone. Perfect. All right, let's have a look on this particular question now. Wonderful. A solution containing this and this shows a pH of 1. So first of all, as per the question, we have got a solution which has got the pH of 1. All right, we have got a pH of 1. We have got a solution which has got a pH of 1. If the pH of the solution is X, do remember, if the pH of the solution is X, then you can say concentration of H positive in the solution is 10 raised power minus X. Okay, from now onwards, you are going to remember this. Anyways, I'm going to teach you this in ionic equilibrium. If the pH of the solution is X, then the H positive concentration is taken as 10 raised power minus X. Okay, perfect. Now, since we need to calculate the reduction potential of the half cell, and the half cell which is given to us is something like this. Cr2O7 dinegative gives Cr tri positive. This is the half cell that's given to us. We have to calculate its reduction potential. So, in order to calculate the reduction potential of this particular half cell, I'll make sure this half cell behaves like the cathode. I'll make sure this half cell behaves like the cathode. Because you know, at cathode what happens? Reduction takes place, and I have to calculate reduction potential only, right? So, when this half cell will be behaving like the cathode, this is oxidation state of chromium, here is +6, here it's +3. +6 to +3 means decrease in the oxidation state. Decrease in the oxidation state means reduction, and reduction takes place at cathode. So, I have to write the reaction like this. Cr2O7 dinegative, Cr2O7 dinegative will be getting converted finally into what? Cr tri positive during the reduction, +6 to +3, right? Now, write the reaction in the complete form. See, it is +6, here it's +3. Change in the oxidation state, final minus initial, the value comes out to be 3. 3 is the change for one atom, but out 2, so 3 2s are 6. So, it's going to be +6 electrons, correct? 2 chromium this side, 2 chromium this side as well. Again, the reaction is not balanced yet. 7 oxygen, that means here we'll be adding 7 water molecules. 14 hydrogens, so on this side we'll be adding 14 H positives as well. Okay, so this is my complete reaction. This is my complete reaction here. Yeah, this is my complete reaction. Now, dear students, after writing the complete reaction, let's try to write the QC value. Start with the product. It's going to be concentration of Cr tri positive raised to the power stoichiometric coefficient, that's 2. This water is in liquid state, leave it, divided by concentration of Cr2O7 dinegative raised power its stoichiometric coefficient, that's 1. And at the same time, it's going to be concentration of H positive raised power 14. Okay. Now, look what all things are given to us. So, concentration of Cr tri positive as per the question is given to me as 2 into 10 raised power minus 2. So, 2 into 10 raised power minus 2 ka square, that is going to be 4 into 10 raised power minus 4 divided by Cr2O7 dinegative concentration, 4 into 10 raised power minus 4. 4 into 10 raised power minus 4. H positive concentration. H positive concentration already we know, that's 10 raised power minus 1 raised power 14. So, 10 raised power minus 14. Correct? So, this term and this term got cancelled. This value 10 raised power minus 14 comes up. It becomes 10 raised power 14. So, QC we got. QC we got. Since we got the QC value, what are we supposed to calculate? Reduction potential. So, I can say the reduction potential of the half cell is equal to standard reduction potential, that's 1.5 minus 0.0591 divided by N. How much is N? N is 6 log of QC. QC value is 10 raised power 14. Log of M raised power N. N log M, so 14 comes to the front and log 10 is 1. Just solve this, get the answer in volts. Okay. I hope you can easily solve these sort of questions from now onwards. I hope that. One more question. Oh, it's a nice question basically. Let's see how this question is to be solved. Is it clear till here? All clear? All right. So let's have a look on this particular question once. Look here now. As far as this particular question is concerned, we are given with a copper electrode. This is the copper electrode that we are given with. We are supposed to calculate the reduction potential at a pH of 14. So pH is given to us as 14. pH is given to us as 14. Reduction potential of the half cell is also given to us. Reduction potential of the half cell is also given to us. KSP, solubility product of CuOH whole twice, is also given to us. What do we need to calculate? We need to calculate a reduction potential of this particular half cell. Since in order to calculate the reduction potential of this half cell, we'll make sure that this electrode behaves like the cathode, because at cathode only reduction takes place, right? So let's make sure that this electrode behaves like the cathode. At cathode, what happens? Reduction. Copper dye positive getting converted into copper. So reaction has to be copper dye positive aqueous will be definitely gaining some 2 electrons. Then only it will be getting converted into copper solid. This is the reaction which will be taking place at cathode. Now you tell me, in this particular reaction, how many moles of electrons are being exchanged? 2 moles of electrons are being exchanged. So N value is equal to 2. So N value here is equal to 2. Okay, number 1. Now I need to get the value of QC. QC, start with the product. It's going to be, it's in solid form, its active mass is 1 divided by concentration of what? Cu dye positive raised power 1. Now you tell me, anywhere in the question, are we given with the copper dye positive concentration? Nowhere, right? Now the point is, how can I get the copper dye positive concentration? That's the point now. So how do I get the copper dye positive concentration? For that, have a look. pH of the solution is given to us as 14, right? If pH is given to us as 14, that means pOH will be 0. Why is that? Because you know, at 25 degrees centigrade, pH plus pOH is equal to 14, right? At 25 degrees centigrade, pH plus pOH is equal to 14. So I can say pOH is equal to 0. If pOH is equal to 0, let me tell you this P. This P, it stands for minus log. P stands for minus log. So minus log of OH negative is 0 to the base 10. So from here you can say OH negative concentration is 10 raised power 0. That means 1 molar. So you got OH negative concentration. Do you know why did I calculate the OH negative concentration? Why did I calculate the OH negative concentration? Because I am given with the KSP of copper hydroxide. If I talk about CuOH whole twice, tell me how it's going to get dissociated. It will be getting dissociated as copper dye positive plus 2 times OH negative, right? So write the KSP expression. Write the KSP expression for this copper hydroxide. It's going to be concentration of Cu dye positive raised power 1, concentration of OH negative raised power 2. Now KSP value as per the question that's given to me as 10 raised power minus 19 is equal to copper dye positive concentration. Copper dye positive concentration I need to calculate, right? OH negative concentration we already calculated. So you got copper dye positive concentration, put it here. 1 divided by copper dye positive concentration. So finally the value comes out to be 10 raised power 19. So QC you got. So I got all the parameters which are needed. QC we got, right? QC we got. Since QC we got, everything we got. Now what do we need to calculate? Reduction potential. So I must say the reduction potential of the half cell is equal to E naught RED, standard reduction potential, which is 0.34 volt minus 0.0591 divided by N. N value is equal to log of QC. QC value we got to know that's 10 raised power 19. Log of 10 raised power 19, which is 19 log 10. So 19 comes to the front. 19 comes to the front, log 10 is 1. Just solve this equation, get the answer in volt. Is it clear? Is it clear? Quickly everyone, is it clear? Is it clear to everyone? Let me know in the chats. You got to know how do I solve this sort of equation? Okay, by the way, you are going to get the PDF of this particular session on this one. This is my official Telegram channel, as well as you can get it on the official Telegram channel of this channel as well. This is the Telegram channel in which you will be getting the PDF, and even on the channel's official Telegram as well. Okay. I told you break at 5. Break at 5. Till 5 no break. At 5 we can take the break. Alright. So till now we saw how do we use the Nernst equation for the half cells. Now let's have a look. How do we write the Nernst equation for full cells? Okay. How do we write the Nernst equation for full cells, complete cells? As you can see, this is one complete cell that's given to me. We are given with 2 electrodes which are connected basically. These 2 lines, they represent the salt bridge. They represent the salt bridge. On the left side of the salt bridge, you have anode. On the right side of the salt bridge, you have got cathode. We need to calculate the EMF of this particular complete cell, right? EMF under non-standard conditions. How exactly? See, first of all, in order to calculate EMF, let's first of all see what is the reaction taking place at anode. At anode, tin is getting converted into Sn di positive, and at anode oxidation takes place, matlab loss of electrons. So tin is getting converted into Sn di positive. So the reaction has to be tin solid. It gives Sn di positive aqueous plus how many electrons? Plus 2 electrons. This is the reaction taking place at anode, oxidation reaction. Similarly, what is going to be the reaction taking place at cathode? At cathode, reduction takes place. Pb di positive gets converted into Pb. So the reaction has to be Pb di positive aqueous plus 2 electrons. What does it give? It gives Pb solid. This is the reaction taking place at cathode. This is the reduction reaction. This is the reaction at anode, oxidation. This is the reaction at cathode, which is a reduction. Okay. Now, dear students, one more thing. In both the reactions, the electrons are balanced. So just add the 2 reactions. So I can say tin solid plus Pb di positive aqueous. It gives Sn di positive aqueous plus Pb solid. This is the net reaction. This is the net reaction which we got. Okay. If I ask you how many moles of electrons got exchanged, you can say 2 moles of electrons got exchanged in the net cell reaction. N value you got. Let's write the QC expression. Start from the product. It's concentration of Sn di positive raised to the power stoichiometric coefficient 1. This is solid, its ectomass is unity, divided by solid ectomass unity. It's going to be concentration of Pb di positive raised power stoichiometric coefficient, that's 1. Now tell me what is the concentration of Sn di positive? It's 1 molar, divided by concentration of Pb di positive, that's 10 raised power minus 3 molar. The value comes out to be 10 raised power 3. So this is QC, right? This is QC. Since you got QC, now there is one thing which is missing. What is that? That is E naught cell. Let's calculate E naught cell first. So I must say your E naught cell is nothing. It is just E naught cathode minus E naught anode. E naught cathode minus E naught anode. So your E naught cell here, it's going to be equal to E naught of cathode. Cathode is your lead electrode, and this is the standard reduction potential of lead electrode, minus 0.13, minus E naught anode, standard reduction potential of anode, which also given to me as minus 0.14. The value comes out to be 0.01 volt. So this is basically your E naught cell. Since you got the E naught cell, now you can use the Nernst equation. So you can say E cell is equal to E naught cell minus 0.0591 divided by N. Now it's going to be log of what? It's going to be log of QC here, right? So E cell, we need to calculate, is equal to E naught cell. E naught cell is given 0.01 volts minus 0.0591 divided by N value. We have already calculated, that's 2, and it's going to be log of QC, which is 10 raised power 3. Now you can use some calculations here. Log of m raised power n, n log m. So 3 comes to the front, and log 10 is 1. Just solve this at the end and get the answer, n volts which you were supposed to calculate. EMF of the cell you were supposed to calculate. I hope you can solve these sort of questions also when they come in your examination. Is it clear? Everyone? Everyone tell me quickly, is it clear? Is it clear to everyone? Yes? Okay, so electrolysis, let's do after the break. So what time you'll be back? What is the time now? Sir, please check, isn't E naught anode 0.14? Where? Where you are saying? Where are you saying E naught anode? This is your anode, right? And this is the cathode. So this is SRP of cathode minus 0.13. And this is SRP of anode minus 0.14. Correct only. I don't know whether I'll be able to complete all the physical chemistry, but for sure class 12 physical chemistry to I'll complete today. I told you, no, if by chance we were not able to finish it in this session, I will take one more. What is wrong? There's no need to hurry, right? So chalo, be back by 5, huh? See you all at 5. See you all again at 5. Okay, everyone be back. Everyone be back.
Okay, guys, can you hear me? Can you hear me? Can you hear me? Can you hear me now? Can you hear me now? Audible? All right, all right, all right, all right. Okay, looks like I'm audible now. Okay, so here I am. No sound? No sound? Hello? Guys, can you hear me? Can you see me? Audible, audible. All right, all right, all right. So here I am, to continue the class. No, just kidding, guys. So here I am to just appreciate Wassim sir because he has stood here for almost 6 hours. It's a 6-hour long marathon, and I was just talking to him and I asked him when is he going to end. He said that he does not know. Till the Josh is high, till the students are fully energetic. So let's make Wassim sir stand for really wrong time. Are you ready for that? Are you ready for that? Let's make Wassim sir stand for a very long time. He is not going to give up. Either you give up or Wassim sir gives up. But I don't think Wassim sir will give up. So yes, very good. Looks like you guys are fully energetic. It's time that you actually put in that dedication towards the channel, because we teachers are putting in our heart and soul. So today Wassim sir is coming. Tomorrow morning 9 o'clock I will be taking a marathon session. Then HSP sir is going to come at 5 o'clock, and then the day after again Wassim sir and Ambika ma'am, and then again me and HSP sir are going to come to take marathons for all of you. So these last few days are the days which you are going to remember, because your preparation will be taken to the next level. You are going to study with full of energy, with full of josh, with lots of love. And remember, this is your channel. So my dear students, why am I saying your likes are only 3.5? Won't you like? Don't you love yourself? Won't you like yourself? So this is your channel. This is not Shreyas sir's, Wassim sir's or Unacademy's channel. This is your channel. Remember that. So you are supposed to like your own channel. Make sure you do that right now. I want that 3.5 going up to 4 immediately. Very good. So here is Wassim sir back on the screen.
Start kare fir.
Yes, looks like students are all pumped up and ready to do.
Yes, all pumped up, guys.
Very good.
All set.
Chalo, all the best, Wassim sir. Take care. I'll see you for dinner.
Yeah.
Yeah. The way the energy is, I feel that you are not going to have dinner also today. Straight away breakfast. Okay, chalo, all the best. Take care.
What's up? Can you hear me, guys? Am I audible, visible perfectly? Am I perfectly audible, visible? Yes. So till now, we are done with the AMF part. Now, one more part we'll discuss. That's going to be Faraday's laws of electrolysis, right? Let's finish it off and let's move on to chemical kinetics. By the way, which chapter do you want me to start after this? Kinetics, right? Is it kinetics? Is it kinetics, guys? Just a second, just a second. All right, perfect. Okay, so after this particular chapter, we'll be starting the chemical kinetics. Cool. All right, so let's get going then. Let's get started with the new topic. That's going to be electrolysis, right? Electrolysis. And after this electrolysis is done, then we shall start the chemical kinetics. But I would want you guys to be with me till the end. Are you ready for that? Are you ready for that? And the josh has to be super high. Josh has to be super high, yes? Wonderful, okay, perfect. A lot of people are saying equilibrium, equilibrium. So after this, do you want me to start equilibrium? Is that? Let's see. Let's finish this off first of all. All right, so let's move on and let's start with something called as electrolysis. Okay. So dear students, this is again one important topic from which question frequently comes. Electrolysis. I'll give you first of all the example. I'll make you understand this electrolysis with the help of a perfect example. Okay. Now understand what exactly I'm going to do. Till now, I used to take two containers. I used to take two electrodes in two different containers, right? I used to take two rods in two different containers. Now in electrolysis, what exactly we'll be doing, we'll be taking a single container. This is one container which I took, okay? And in this particular container, what am I going to keep? I am going to keep the molten NaCl. I'm going to keep the molten NaCl inside this container. That means in this particular container, we have got two types of ions. One is Na positive and one is Cl negative. These are the two types of ions which are present in this particular container. Okay. Now, dear students, let me introduce two rods. This is the first rod and this is the second rod. I've introduced two rods in the same container. And these rods, externally, I'm connecting with the battery. This is the external battery with which I'm connecting the rods. My dear students, this negative terminal of the battery, I'm connecting with this electrode, and the positive terminal of the battery, I'm connecting with the other electrode. Okay. That rod which is connected with the negative terminal, that will be getting the negative charge. And the rod which is connected with the positive terminal, that will be getting the positive charge. Absolutely. Do remember, in case of electrolysis, this negatively charged rod is something which we call as cathode. This negatively charged rod is something which we call as cathode. And this positively charged rod over here is something which we call as anode. Right? During the electrolysis. In the electrolysis, I'm saying. Okay? Now, dear students, at cathode, you already know what happens. Reduction takes place. Reduction means gain of electrons. And similarly, at anode, oxidation takes place. And oxidation, you already know, it means the loss of electrons. Okay. Now, first of all, what is going to happen? When you'll connect these rods with the external battery, there will be certain reactions. Let's see what all reactions will be taking place at anode and cathode. Let's check what all reactions will be taking place at cathode and anode. Understand. Understand. My dear students, you have got two types of ions in the container. One is Na positive, one is Cl negative. Can I say this negatively charged rod, it's going to attract this Na positive towards itself, and positively charged rod, it's going to attract this Cl negative towards itself, right? So towards the cathode, which is coming, it is going to be Na positive, which is coming towards the cathode. And you know, at cathode, reduction takes place. Reduction means gain of electrons. So this Na positive, when it reaches the cathode, it's going to gain one electron and will get converted into Na solid. And this Na solid, it will be getting deposited on this rod. This Na solid will be getting deposited on this particular rod. Similarly, what will happen at the anode? Anode is the positively charged rod. And positively charged rod is going to attract Cl negative towards itself. Right? Perfect. So Cl negative will move towards anode, will undergo oxidation. Oxidation means loss of electrons. So the reaction has to be 2 times Cl negative, right? It reaches the anode, gets converted into Cl2 gas, and with this, it gives 2 electrons. Perfect. So these are the two reactions. One happening at anode, another one happening at cathode. Right? Perfect. Now the question which is asked to you, the question is, during the electrolysis of molten NaCl, what is happening at anode? At anode, as you can see, Cl2 gas is produced. Cl2 gas is liberated, right? Cl2 gas is liberated. Similarly, at cathode, what is happening? At cathode, sodium is getting deposited. So this is basically the conclusion. This is the final conclusion. So what is the final conclusion which we need to remember here? We need to remember only one thing, that at anode Cl2 gas is liberated and at cathode it is sodium solid which is being deposited. Correct? Very simple and basic. Wonderful. Now dear students, let's take similarly one more case and let's try to analyze it properly. Have a look. Let's do the electrolysis of molten PBr2. I'm just doing the electrolysis of molten electrolytes. I did not take aqueous yet. I did not take aqueous electrolytes yet. I'm going to do the electrolysis of molten PbBr2. Right? So first thing, if I ask you, let's say this is the container first. And in this particular container, what exactly am I going to keep now? I'm going to keep molten PbBr2. That means in this container, you'll find Pb di positive ions and at the same time, you'll find Br negative ions. Absolutely, right? And at the same time, people, again, two rods I'm introducing. And these rods I'm connecting with the external battery. External battery. The rod which is connected to the negative terminal carries the negative charge. The rod which is connected to the positive terminal carries the positive charge. Again, I'm calling the same things. This negatively charged rod I'm calling as cathode. Positively charged rod I'm calling as anode. And you know, at cathode oxidation takes place. At cathode reduction takes place. And at anode oxidation takes place. Perfect. This is something which I've told you already. Now dear students, this cathode, negatively charged rod, it's going to attract this positively charged ion towards itself. Similarly, this positively charged rod, it's going to attract this negatively charged ion towards itself. So what are the possible reactions which are taking place at cathode and anode? Let's try to see that. Let's see the reactions taking place at cathode and anode. So first of all, towards this cathode, Pb di positive is coming. Pb di positive is coming to cathode. At cathode, reduction takes place. So Pb di positive at cathode will be gaining electrons. Pb di positive at cathode will be gaining some 2 electrons and will be getting converted into Pb solid. Right? Perfect. Simple. So it is basically lead which is being deposited. It is basically lead which is being deposited at cathode. Similarly, if I ask you what will be deposited or liberated at anode it's Br negative which is coming. And at anode oxidation takes place. So Br negative at anode undergoes what? Undergoes oxidation. Oxidation means loss of electrons. So the reaction has to be what? The reaction should be like this. 2 times Br negative, it gives Br2 plus what? Plus 2 electrons. The simple basic question which is asked to you, the products of electrolysis. The products of electrolysis. At cathode, Pb is getting deposited. And at anode, it is Br2 which is being liberated. These are the two possible questions which can be asked from the electrolysis of molten PbBr2. Is it clear to everyone? Let me know once quickly in the chats. Everyone with the thumbs ups. Till now, I did not use the aqueous electrolytes. I'm right now using the molten electrolytes. Diksha, cells and all, I mean, that's a complete theoretical topic. That you can do from NCERT as well, right? I'm just focusing on more important stuff. Okay, so give me some thumbs ups in the chats, people, if it's clear. Give me some thumbs ups in the chats if it is super clear. Cathode is negative here, right? In case of electrolytic cell. By the way, this particular cell which I'm showing you, it is electrolytic cell. Huh? Perfect. Quickly guys, quickly everyone. All right, good job done. Now dear students, before talking about the electrolysis of aqueous electrolytes, I need to tell you a few important things. Which you guys are going to remember. And what are those important things? Have a look. Before talking about the electrolysis of aqueous electrolytes, till now I was doing the electrolysis of molten electrolytes. Before doing the electrolysis of aqueous electrolytes, there are a few things which you need to remember. First reaction which I would want all of you to remember, that is the oxidation reaction of water. Dear students, this particular reaction It is called as oxidation reaction of water. You can have a look in this reactions. In this reaction, electrons are being lost. Loss of electron means oxidation. So this particular reaction is basically the oxidation reaction of water. So whenever from now onwards I say that water is undergoing oxidation, so you have to write this particular reaction at that time. Even you can check it like this as well. Oxygen has got the oxidation state of -2 here. Here its oxidation state is 0. -2 to 0 means increase in the oxidation state. Increase in the oxidation state means oxidation, right? So it's water here which is undergoing oxidation. Similarly, when we talk about the reduction reaction of water, look at this particular reaction in which gain of electrons is happening, right? Gain of electrons is called as reduction. Gain of electrons is called as reduction. Or look at the oxidation state of hydrogen over here, it's +1. Look at the oxidation state of hydrogen here, it's 0. +1 to 0 means decrease in the oxidation state. +1 to 0 means decrease in the oxidation state. Decrease in the oxidation state is something which we call as reduction, right? So basically, this is the reduction reaction of water. This is the oxidation reaction of water, this is the reduction reaction of water. Perfect. Why am I giving you these two reactions? There is a reason for that. There is a reason for that. For example, understand, I'm going to tell you something really important. Understand properly what I'm going to say. See guys, for example, imagine that instead of molten NaCl, you are taking aqueous NaCl. Imagine that instead of molten NaCl, you are taking aqueous NaCl. That means in this particular container, what all different ions will be present? First of all, you will find Na positives, you will find Cl negatives, of course. Since it's aqueous, that means there will be H positives and OH negatives as well in this particular container. So till now, we always used to have only one cation, one anion, one type of cation, one type of anion. Now we have got two types of cations and two types of anions, correct? Now what's going to happen? What's going to happen? What's going to happen? What's going to happen? Understand. So over here, I'm going to introduce two rods. These are two rods, right? And let me connect these rods externally with the battery. This is the negatively charged rod, this is the positively charged rod. Negatively charged rod is something which you call as, your cathode here, and this is something which you call as anode. Okay? And what's going to happen here? At cathode, reduction is going to happen. At anode, oxidation is going to happen. Now, dear students, this negatively charged rod is going to attract H positive as well as Na positive towards it, right? This negatively charged rod is going to attract Na positive as well as H positive towards it. And both these cations over here, they would want to undergo reduction at cathode. Both these cations would want to undergo reduction at cathode. But both the ones won't undergo reduction. Only one among the two cations will undergo reduction. And that cation among the two, which will be having lesser discharge potential, will undergo reduction. Now, Na positive and H positive. Na positive and H positive. Na positive and H positive. Just a second. Na positive. This is the discharge potential series for cations. This is the discharge potential series for anions. Now, compare your Na positive with H positive. Compare your Na positive with H positive. Have a look. Which one is having lesser discharge potential? I would say H positive is having lesser discharge potential. That cation which will be having lesser discharge potential, will undergo a reduction here. So it is basically going to be H positive which will undergo reduction here. Right? Similarly, you have got two types of anions, Cl negative and OH negative. This positively charged rod, this anode, it's going to attract both towards itself. So both the anions would want to undergo oxidation here, but both won't undergo oxidation. Only one will undergo oxidation. That anion among the two, which will be having lesser discharge potential again, will undergo oxidation. Now compare which anion, Cl negative or OH negative. Cl negative or OH negative? Which one is having lesser discharge potential? Cl negative. So Cl negative will undergo oxidation. Cl negative will undergo oxidation. It is going to be Cl negative which will undergo oxidation. I hope you got it. Now comes the scenario. Now I would want you guys to write the reaction taking place at cathode. At cathode, reduction is taking place. Reduction of what? Reduction of H positive. Reduction of what? Reduction of H positive. Correct? Reduction of H positive. Now, first of all, this H positive, it has come from water basically, right? This H positive has come from water. So, I will be writing the reduction reaction of water. And what is the reduction reaction of water? A few minutes back only I gave you 2 times H2O plus 2 times H2O plus 2 electrons. It gives H2 plus 2 times OH negative. Correct? This is the reduction reaction of water basically, which is happening. And due to this reduction reaction of water, what is being liberated? H2 gas is being liberated at cathode. So at cathode, it's H2 gas which is being liberated. Similarly, if I ask you what happens at anode oxidation takes place, right? At anode oxidation takes place. Oxidation of what? Cl negative. So the reaction has to be 2 times Cl negative gives Cl2 gas plus 2 electrons. So it's going to be Cl2 which is liberated at anode. So this is something which is asked. This is something which is asked. At cathode, your H2 gas is right now being liberated. At anode, Cl2 gas is being liberated. Okay? Perfect. Is it clear to everyone? Is it clear to everyone? Quickly. Quickly give me some thumbs ups, people. Everyone. Okay, one more let's do. Let's do one more electrolysis and then let's talk about the questions. Let's do one more electrolysis first. Electrolysis of aqueous CuSO4. So basically, again I'm taking one electrolytic cell, right, in which you are keeping aqueous CuSO4. That means in this particular container, you have got copper dye positive, you have got SO4 dye negative, you have got H positive, you have got OH negative because you are taking aqueous CuSO4, correct? Now, the same procedure you will be doing. This is the first rod, this is the second rod, and connect them with the battery. This rod carries negative, this rod carries positive. Perfect. Negatively charged rod is your cathode here. Positively charged rod again is your anode here. And at cathode, you know reduction takes place. At anode, you know oxidation takes place. Now, this negatively charged rod, it can attract Cu positive as well as H positive. So both these cations would want to go to this cathode and would want to undergo reduction. But which one among the two cations will undergo reduction? The one with the lesser discharge potential. That cation among the two which will be having lesser discharge potential value will undergo reduction. So is it H positive or copper dye positive? It's copper dye positive basically which has lesser discharge potential than that of H positive. Correct? It is copper dye positive which has got lesser discharge potential than H positive. So copper dye positive will undergo reduction here. Reduction means gain of electrons. So copper dye positive plus 2 electrons gives copper solid. So basically on this rod, copper solid is being deposited. Correct? Now, among SO4 dye negative and OH negative, since both of them would want to undergo oxidation here, but the one with the least discharge potential value will undergo reduction. Now, among SO4 dye negative and OH negative, which one will have least discharge potential? It is OH negative. It is OH negative which has got less discharge potential than SO4 dye negative. So, OH negative will undergo oxidation here and OH negative is undergoing oxidation. OH negative has come from water. So, you will write the oxidation reaction of water basically, which I already gave you. So, have a look at anode, what is being liberated? It's O2 gas which is being liberated at anode. It is O2 gas which is being liberated at anode, right? It's copper solid which is being deposited at cathode. And this is the conclusion final which you need to remember. Is this clear to everyone? Is this clear to everyone? Quickly. Quickly guys, everyone. Yes or no in the chats? Yes or no in the chats? Yes or no in the chats quickly? Perfect. Perfectly clear? Wonderful. So dear students, now let's have a look on Faraday's first law of electrolysis. Let's have a look on Faraday's first law of electrolysis. It's a simple phenomenon basically. First of all, you got to know till now, on the electrode either metal is being deposited or the gas is liberated, right? You saw a few minutes back only. Either metal was being deposited or gas was being liberated, right? Something was deposited or liberated at the electrode. Now Faraday's first law says, mass of the substance in grams, deposited or liberated is directly proportional to the charge which goes into the solution. Since you are connecting these electrodes with the external battery, so more the voltage of the external battery, more is the charge which goes into the solution. And more charge going into the solution means more will be the metal deposited or more will be the gas liberated. Right? So, as per Faraday's first law, mass of substance deposited or liberated is directly proportional to the charge which goes into the solution. Yes? So, I can remove the proportionality sign here. It's equal to constant Z multiplied by Q. This Z is what we call as, its value is first of all E divided by 96500, and this Z is called as electrochemical equivalent. It's called as electrochemical equivalent. Electrochemical equivalent. Now dear students, I can say mass of the substance deposited or liberated is equal to, instead of Z you can write E divided by 96500 multiplied by what? Multiplied by Q, right? So we can write it like this: mass of the substance deposited or liberated is equal to E, I am writing as such, Q will be current into time divided by what? Divided by 96500. So this is the first and the important relation which I would want you guys to remember. So there are a lot of questions based on this particular relation. Calculate the mass of substance deposited. Calculate the mass of gas liberated, like that. Okay? Do remember this E. This E stands for the equivalent mass. E stands for the equivalent mass of the substance which is being deposited or liberated. Right? Now one more result we can form from here, from which we can do the questions a little bit easily, and result is going to be like this. We know mass of the substance deposited or liberated in grams is equal. Instead of equivalent mass, I'll be writing molar mass of the same substance which is being deposited or liberated divided by n factor. In the denominator you have got 96500, right? In the numerator you have got I multiplied by T. So you can write mass of the substance deposited or liberated divided by molar mass of the substance which gets deposited or liberated is equal to I multiplied by T divided by n factor multiplied by 96500. So mass of substance deposited or liberated divided by molar mass of substance deposited or liberated. So this whole term I'll be calling as number of moles of substance deposited or liberated is equal to I multiplied by T divided by n factor multiplied by 96500. So dear students, from this particular result, from now onwards you can easily calculate the number of moles of substance which are being deposited or liberated, right? Let's try to use these two equations first of all. Let's see what kind of questions can be solved from these two equations. So first, let me know in the chats if everything is clear till here. These two results are very important. Okay, let's try to utilize these results. But before doing the questions, I would want you guys to understand one more thing. How do you calculate n factor from the balanced chemical equation? How do you calculate the n factor from the balanced chemical equation? Have a look. We have got a reaction here, and in this particular reaction, 12 moles of electrons are being exchanged. 12 moles of electrons are being exchanged, right? Okay. So dear students, let's say I need to calculate the n factor of A. let's say I need to calculate the n factor of A. I'll see in this particular reaction, 12 moles of electrons are being exchanged divided by stoichiometric coefficient of A is 1. So n factor of A is directly going to be 12. If I ask you what is the n factor of B, you will say it's going to be 12 divided by stoichiometric coefficient of B, that's 2. The value comes out to be 6. Similarly, if I ask you about the n factor of C, it's going to be 12 divided by 3, the value is 4. Similarly, n factor of D, if I ask you, it's going to be 12 divided by 4, the value comes out to be 3. So this is how, in short, you calculate the n factors. This is how, in short, you calculate the n factors. Now, after knowing how to calculate the n factors, let's try to do few questions. Let's try to do few questions so that you can analyze it properly. See, guys, the first question, the first question which is on your screen, have a look. A solution of aqueous copper sulfate. A solution of aqueous copper sulfate. You have taken aqueous copper sulfate. It is being electrolyzed for 10 minutes with a current of 1.5 amperes. With a current of 1.5 amperes. What is the mass of copper deposited at cathode? So basically, as per this question, we are doing the electrolysis of aqueous CuSO4. And you know, when we do the electrolysis of aqueous CuSO4, at cathode, copper gets deposited. We have seen that few minutes back. At cathode, copper gets deposited. Before solving the question, just tell me, what is the n factor of copper here? N factor of copper. How many moles of electrons are exchanged? 2 divided by stoichiometric coefficient 1. So the value comes out to be 2 only. So n factor of copper is 2. Okay. What do we need to calculate? The mass of copper deposited. So I must say the mass of copper deposited in grams is equal to equivalent mass of copper multiplied by I multiplied by T divided by 96500. Few minutes back only we saw this relation, right? So equivalent mass of copper is going to be molar mass of copper, right? Molar mass of copper, correct? Molar mass of copper divided by n factor of copper, that's 2. Current, it's mentioned in the question that 1.5 amperes of current goes into the solution. For how much time? For 10 minutes. I want it to be in seconds, so multiplied with 60. In the denominator, there is 96500. Now again, it's a matter of calculation. You'll be getting the answer in grams, right? After solving this, you'll get to know the mass of copper which is being deposited at the cathode. When we do the electrolysis of aqueous CuSO4 by the passage of 1.5 amperes of current for 10 minutes. I hope this is clear. I hope you all will be easily solving these sort of questions from now on. Okay? Is this clear? Once tell me in the chats, then only I'll move on to one more. If this is clear, then only I'll be moving on to one more. Quickly. If the same question is clear, then only I'll be moving on to one more. Quickly, let me know in the chats. Everyone. Everyone. Everyone, quickly. Perfect. Perfect, guys. Let's try to solve one more question. A current of 96.5 amperes is passed for 96.5 amperes is passed for 10 seconds through 1 liter of a solution of aqueous CuSO4. Calculate the pH of the solution. Calculate the pH of the solution. So as per the question, again, we are doing the electrolysis of aqueous CuSO4 only, right? As per the question, we are again doing the electrolysis of aqueous CuSO4, correct? Okay. When we do the electrolysis of aqueous CuSO4, this is the reaction taking place at cathode. At cathode, copper gets deposited. At anode, O2 gas is produced. And at the same time, as you can see from this reaction, at the anode, H positive is liberated as well. H positive is liberated and these H positives, they go into the solution. Right? So at cathode, copper is being deposited. At anode, H positives, they get liberated and they go into the solution. Right? They go into the solution. Perfect? Now, dear students, there is one more thing. There is one more thing. What do we need to calculate? We need to calculate the pH of the solution. We need to calculate the pH of the solution. Since at anode, what is happening? At anode, H positives are going into the solution. So, due to these H positives which are going into the solution, the resulting solution becomes acidic because of these H positives which go into the solution. Right? Now, dear students, what are we supposed to calculate? We are supposed to calculate pH of the solution. We are supposed to calculate pH of the solution. pH of the solution is to be calculated. Right? In order to calculate pH, you know, P stands for minus log of H positive concentration. This is what you need to calculate basically. So, in order to calculate pH, you should know the value of H positive concentration. So, how do I get the H positive concentration? H positive concentration means number of moles of H positives which are liberated in the solution, right, divided by volume of the solution in liters. So, first of all, what I'll be doing, I'll be calculating the number of moles of H positive which are liberated in the solution, dividing it with total volume. I'll be getting the concentration of H positive. And once I get the concentration of H positive, we can easily calculate pH, right? Done and dusted. So, dear students, what I'll be getting? I will be just doing one thing. I'll be focusing on this reaction because from this particular reaction only, H positive is being introduced. H positive is being liberated. So, first of all, if I ask you, what is the N factor of H positive, which is being liberated inside the solution? Moles of electrons, that's 2, divided by stoichiometric coefficient of H positive, that's 2, the value comes out to be 1. So, N factor of H positive here in this reaction is 1, correct? Now, if I write the equation, number of moles of H positive liberated, number of moles, I gave you two relations, mass of substance deposited or liberated, second one was moles of substance deposited or liberated. So, I am writing moles of H positive liberated will be equal to I multiplied by T divided by N factor of the substance which is liberated, that's H positive, multiplied by 96500. Perfect. Now, you tell me, this I multiplied by T is basically charge, Q, right? And how much charge is given? Okay, charge is not given. We are given with current. Current is given to us as 96.5 amperes. For how long the current goes into the solution? For 10 seconds. Divided by N factor of H positive is 1. Multiplied by 96500. The value comes out to be 10 raised power minus 2. So, these many moles of H positives go into the solution. These many moles of H positive go into the solution. Correct? So, if you got to know the moles of H positives which are going into the solution, just calculate the concentration of H positive in the solution, which is equal to number of moles of H positive in the solution divided by volume of solution in liters. So, it's 10 raised power minus 2 divided by volume of solution is how much? 1 liter. The value comes out to be 10 raised power minus 2. So, this is the concentration of H positive in the final solution after the electrolysis is done. So, my dear students, since you calculated the concentration of H positive, now it's the time to calculate the pH. It is the time to calculate the pH. So, pH is just going to be minus log of H positive, correct? So, it's going to be minus log of H positive concentration is 10 raised power minus 2. So, it's going to be minus log of m raised power n, log of m raised power n, n log m. So, minus 2, then it's going to be log of 10, log of 10 is 1. So, pH of the resulting solution finally came out to be 2. That's something which you were supposed to calculate. Will you be able to solve this sort of equation from now on if this sort of equation comes? Quickly let me know in the chats. Quickly, everyone. So, in order to calculate the pH, I need H positive concentration. To calculate H positive concentration, we need number of moles of H positives in the solution, right? Then divide it with the total volume to get the H positive concentration. And finally, multiplying that with minus log, you'll get the answer. Perfect, yes. All right, wonderful. Moving on. Let's move on to one more. Let's move on to one more. Just a second. There is something called as Faraday's second law of electrolysis. Let's have a look what Faraday's second law of electrolysis exactly says, what it's all about. Okay? It's again simple. For example, I'm taking some 2 containers. I've taken some 2 electrolytic cells, or maybe, yeah, let's keep it at 2. Okay? These are the rods. These are the rods. Okay? Now, first of all, I'm connecting these with the external battery. I'm connecting these with the external battery. I'm connecting them internally as well. This negative terminal will give negative charge to this rod. So, this will get positive, this will get negative, and this will get positive. Perfect. This negatively charged rod is something which we call as cathode here. This is anode, this is cathode, and this is anode. What Faraday's second law of electrolysis says exactly? Whenever, if a current is passed in 2 or more electrolytic solutions containing different electrolytes. Let's assume that there are different electrolytes present in these 2 containers. Let's assume that. Faraday's second law of electrolysis says that when a current is passed in 2 or more electrolytic solutions containing different electrolytes, the mass of substance deposited or liberated on every rod, on every electrode, the mass of the substance deposited, right, will be in the ratio of their equivalent masses. Or let me keep it very simple. Have a look. Let's assume that since this is the cathode, let's say there is something which is getting deposited. Let's say number 1 is getting deposited here. Number 2 is getting liberated here. Number 3 is something is getting deposited here. Something is getting liberated here. Just to make you understand. Faraday's second law says when 2 or more than 2 electrolytic cells are connected in series, the number of gram equivalents of substance, deposited or liberated on every electrode will be the same. What does that mean? That means gram equivalents of 1 deposited must be equal to gram equivalents of 2 liberated, must be equal to gram equivalents of 3 deposited, must be equal to gram equivalents of 4 liberated. Perfect. So, in short, the gram equivalents of substance deposited or liberated on every electrode will be the same. Now, the point is, how do we calculate the gram equivalents? Gram equivalents of, I'm assuming this one is being deposited here, right? Gram equivalents of 1 deposited means mass of 1 deposited in grams divided by equivalent mass of 1. Similarly, gram equivalents of 2, I'm assuming 2 is being liberated here. Gram equivalents of 2 liberated means mass of 2 in grams liberated divided by equivalent mass of 2. Similarly, gram equivalents of 3 means mass of 3 which is being deposited in grams divided by equivalent mass of 3. And similarly, you can write it in terms of 4 as well. Right? Perfect. Yes? Perfect, guys. Now, let's try to see exactly how this particular equation is used in the questions. I'll be just solving one question with you so that you can understand it properly. See what the question is. Look at the question carefully. The question is during the electrolysis of aqueous copper sulfate, the mass of the metal deposited is equal to 63.5 grams. Calculate the mass of gas released and volume of the gas released at STP. So what are we doing? We are doing the electrolysis of what? We are doing the electrolysis of copper sulfate, right? We are doing the electrolysis of copper sulfate. Let's say this is your electrolytic cell. Let's say this is your electrolytic cell, right? This is, for example, the negatively charged rod. This is the positively charged rod. This is something which you call as cathode. This is something which you call as anode. Correct? Now, at cathode, we already know copper is being deposited. At cathode, copper is being deposited. At anode, what is happening? At anode, O2 gas is being liberated. At anode, O2 gas is being liberated. Now, what Faraday's second law suggests? Faraday's second law says the gram equivalence deposited or liberated on every electrode will be the same. So, I can say from the Faraday's second law, the gram equivalence of copper deposited here, the gram equivalence of copper deposited should be equal to the gram equivalence of O2 liberated. Simple, right? As per Faraday's second law, I can say the gram equivalence of copper deposited here should be equal to the gram equivalence of O2 liberated, as per Faraday's second law is concerned. Now, gram equivalence of copper deposited means mass of copper deposited divided by equivalent mass of copper, right? Gram equivalence of O2 means mass of O2 liberated divided by equivalent mass of O2. Now, you tell me, what is the mass of copper deposited? It's 63.5 grams divided by equivalent mass of copper means molar mass of copper divided by n factor of copper. Check the n factor of copper. 2 divided by 1, that's 2, is equal to mass of O2 liberated. Mass of O2 liberated, I'll be calculating that in grams, divided by equivalent mass of O2. Equivalent mass of O2 means molar mass of O2 divided by n factor of O2. N factor of O2 means electrons divided by stoichiometric coefficient. So 2 divided by 1 by 2 comes out to be 4. Correct? So this and this got cancelled. 2 came up. So from this particular equation, I can say mass of O2 liberated is equal to, this is going to be 2 this is going to be 2 8s are 16, so it's going to be 16 grams. So we got to know 16 grams of O2 has been liberated at anode as per the question. Correct? Yes? Perfect. And dear students, at the same time, we are supposed to calculate the volume of gas released as well, volume of gas liberated as well. Since you calculated the mass of gas liberated, now calculate the moles of O2 liberated. Given mass in grams, divide by molar mass, right? So the value is 0.5. So 0.5 moles of O2 got liberated. We are supposed to calculate the volume of O2 liberated at STP. So it's going to be equal to moles of O2 liberated multiplied by 22.4 liters. The value is going to be 0.5 multiplied by 22.4. The value comes out to be 11.2. Perfect. Is it clear? 11.2 liters of O2 got liberated at the end. Okay? Yes? Perfect, guys. Is it clear till here? Let me know quickly. Let me know quickly in the chats with the thumbs ups if it is clear. Can you solve these sort of questions on your own now? What if we don't know the molar mass? Then you are gone. Quickly, guys, everything clear? Everyone. Complete physical chemistry cannot, I don't think it will get completed today. So we'll take one more session for it. That's not a big deal, but I want to complete all the topics. Okay? I want to complete all the topics in detail with the questions, the way we are doing. If it takes one more session also, it's completely okay. Perfect. Perfect, guys. Perfect. Now let's start one more chapter. These were some very, very important topics from this particular chapter, electrochemistry, and I'm 100% sure when question comes from electrochemistry, it will be from these two topics only, which we discussed, right? So which chapter do you want me to do now? I think we'll start with kinetics now. Should we? Should we start with kinetics? Let's finish class 12th physical chemistry today. In the next session, we'll do class 11th physical chemistry. What is wrong? I'm saying in the today's session, let's complete class 12th physical chemistry. In the next session, let's complete class 11th. What do you say? Cool with it? Quickly, yaar. Everyone. Everyone. Let's keep it like this only. Class 12th physical chemistry today, and in the next session, class 11th physical chemistry. So equilibrium is in your class 11th, so that will be done in the next session then. Okay? Let's start with the chemical kinetics now. Let's start with the kinetics now. You can call up your friends. You can call up your friends. You can call up your friends quickly. What is this, yaar? The like count is still at 3.7k. It has to cross 4k, right? It has to cross 4k. All right, so let's get going. Let's start with the kinetics now. It's again one important chapter, right? And it won't take a lot of time to finish because it's not that huge basically. Okay, let's start. Let's start, guys. Okay. Let's start with the first topic, that is rate of reaction as per stoichiometry. First of all, how do we exactly define the rate? How do we exactly define the rate? Let me teach you certain basics first so that it becomes clear to you, then we can move on to this topic, okay? Just a second. Let me teach you some basic things first. You just keep on telling me the answers in the chats. Let's say I have to define the rate of the reaction. Or instead of rate, let's say I have to define the average rate of the reaction. Average rate of the reaction. How do we define this average rate of reaction? What is average rate of reaction all about? Average rate of reaction is defined as change in the concentration of either reactants or products divided by time interval. This is one of the ways by means of which you can calculate rate in terms of concentration. So dear students, let's try to define the average rate of reaction first of all. Let's try to define the average rate of reaction. Have a look. For example, you have got an equation A gives B. This is a reaction A gives B, okay? First of all, here's a term concentration. How do we exactly define the concentration? Number of moles per unit volume. Number of moles per unit volume. For example, you want to write concentration of reactant. Concentration of reactant means number of moles of reactant divided by total volume in liters. Let's say you want to define concentration of products. It's going to be number of moles of products divided by volume of solution in liters, right? Okay. That means on increasing the moles of reactants, if the number of moles of reactants increase, the concentration of reactants will increase too. If the concentration of products increase, that means, if the moles of products increase, that means concentration of products will increase too. So, your concentration and moles, they are directly proportional basically. The point is that. Why you guys are continuously spamming with the Kohl-Ross law? Why you are continuously spamming with the Kohl-Ross law? That is the simplest among all, yaar. Something to at least you guys should also do. Yeah? Focus on the topics first. Focus on these topics first, what I'm saying. Focus on these topics now. It looks easy, it's not easy. Just wait. You'll get the idea in some time. Okay? Understand. So first of all, in this particular reaction, let's say at time t is equal to 0. Or let's say at time t1. Let's say at time t1, the concentration of reactant I'm denoting with C1. The concentration of B at time t1, for example, it's C2. Right? Let's say at time t2, I'm again analyzing this chemical equation and I'm observing the concentration of A now is C2 and concentration of B now is C3. Okay? You tell me one thing. You tell me one thing. When the reaction starts, what happens to the number of moles of reactants? Number of moles of reactants decrease with time. If number of moles of reactants decrease with time, so concentration of reactant also decrease with time, right? Of course, concentration of reactant decrease with time. So at time t1, the concentration of reactant was C1. At time t2, the concentration of reactant is C2. Can I say C2 will be less than C1? Because concentration of reactant decrease with time. As the time goes on, the concentration of reactant decreases. Number one. What happens to the concentration of products? First, what happens to the moles of products? As the reaction proceeds, the number of moles of products, they increase with time. The number of moles of products, they increase with time. Due to which, the concentration of products increase with time. So, I must say, as the time proceeds from T1 to T2, the concentration of products will increase with time. So, I must say, C3 value will be greater than C2. Right? This must be clear to you. Now, this particular time interval which I am choosing from T1 to T2, I am calling this time interval as T2 minus T1. This is T2 minus T1 time interval. So, in this particular time interval, I need to define the average rate of reaction. How do I define the average rate of reaction? Average rate of reaction, you can define either in terms of reactants or you can define in terms of products. Let's define the average rate of reaction in terms of reactants. How exactly? I'll be writing change in the concentration of reactants divided by time interval. What is the change in the concentration of reactants? This is initial, this is final. So, it's going to be final concentration of reactant minus initial concentration divided by time interval C2 minus C1, right? Similarly, you can calculate the average rate of reaction with respect to products as well. It's going to be change in the concentration of product, which is C3 minus C2 divided by time interval T2 minus T1. Correct? Now, my dear students, understand one important thing. Understand one important thing. C2 minus C1. You know C2 is less than C1. If C2 is less than C1, that means the difference of the two will come out to be negative. That means the difference of the two will come out to be negative. But have you ever heard rate of reaction coming out to be negative? Rate of reaction can never be negative, right? So what do I have to do? I have to multiply here with the negative sign. So the final result comes out to be positive. So that final result comes out to be positive. Okay? Yes? And at the same time here, average rate of reaction with respect to products, C3 minus C2. We already know C3 is greater than C2. So here already it's coming out to be positive only. Here already it's coming out to be positive only. So no need to multiply with the negative sign. It will be positive only. So if I want to define the average rate of reaction now, it will be change in the concentration of either reactant or product divided by time interval and with the sign minus plus over here. Depends on whether we are defining the average rate of reaction with respect to reactants or with respect to products. Right? Perfect. I hope this is clear. Now, my dear students, there is one more thing about the rate of reaction. That's something which you call as instantaneous rate. How do you define the instantaneous rate? Instantaneous rate of reaction. How do you define it? How do you define the instantaneous rate of reaction? So first of all, this particular term, delta C divided by delta T. This is something which you call as average rate of reaction. Now put the limits, make the time interval approaching towards 0. Now this particular term, you can represent it like this, dC upon dt, and you can call it as the instantaneous rate of reaction. Right? You can call it as the instantaneous rate of reaction. Yes? You can call it as the instantaneous rate of reaction. Now, dear students, dC upon dt, mathematically or graphically you can say, it gives you the slope of the tangent. It gives you the slope of the tangent at a point on concentration versus time curve. Okay, perfect. So what you need to do exactly, for example, I'm making a graph for reactants. The graph is going to be between concentration of reactant versus time. Concentration versus time. We know with time concentration of reactant decreases. We know with time the concentration of reactant decreases, right? We know with time the concentration of reactant decreases. So the graph has to be like this. Concentration of reactant decreases with time. Okay. Now if I mark a point here at this particular point, or I can say in a very small time interval, very small time interval, let's calculate the rate of the reaction, which I call as instantaneous rate. What I need to do, I just need to calculate the slope of the tangent at a point on concentration versus time curve. That means I'll be drawing a tangent here. Just draw the tangent. After drawing the tangent, let's calculate this angle, which I'm representing with theta, right? Which the tangent makes with the positive x-axis in the anticlockwise direction. And then after calculating this theta, take tan of this theta here. Take the tan value of this theta. Tan of this theta, it gives you what? It gives you the slope of the tangent, and slope of the tangent is represented by dC upon dt, which is what you call as average rate of reaction. Perfect. Now at the same time, the theta over here is obtuse. Tan of obtuse angle comes out to be negative, but rate can never be negative. So you have to multiply it with minus sign. Perfect. So this is for reactants. This is for reactants. This is for reactants. This is for reactants. Perfect. Perfect. Now in the similar way, let's do it with respect to products. Let's do it in terms of products. Have a look. My dear students, you all must be knowing, if I plot a graph between concentration and time, concentration versus time for products, you know, with time, the concentration of product increases with time, right? You know, with time, the concentration of products increase. So the graph has to be like this. With time, the concentration of product increases. Now, in a very small interval, for example, this is the very small time interval. At this particular point, I need to calculate the instantaneous rate of reaction. How exactly I'll be doing? I'll be again drawing a tangent at this particular point. I'll be calculating the angle with the tangent mixed with the positive x-axis in the anticlockwise direction, that means theta, right? Let's calculate tan of this theta. Tan of this theta, it gives me what? It gives me the slope. It gives me the slope of the tangent at a point on concentration versus time curve. That means it will give me the instantaneous rate of reaction. It will give me the instantaneous rate of reaction. Correct? It's going to give me the instantaneous rate of reaction. And anyways, theta is positive here. Theta is positive. And tan of acute angle. Sorry, theta is acute here. And tan of acute angle. It comes out to be positive only. Perfect? Right? So you're not supposed to multiply with minus or something here. I hope it's clear. Right? Who is this nonsense, Roy? Bro, you can go to some other channel, bro. Are you a paid user or something? Has anyone paid you something to continuously spam? All right. I hope this is clear to everyone. Right? Now I'm going to come to the actual point. This was all basics which I was teaching you till now. Correct? Now I'm going to the actual point. That is rate of reaction as per stoichiometry. This is something which we have to discuss. Rate of reaction as per stoichiometry. Rate of reaction as per stoichiometry. Praniti, where exactly? Can you tell me? Can you tell me? What happened? Where do you find? Did I use some sign? Yahan wahan? All cool, right? You got it perfectly, right? Let's move on. Let's move on now. So now let's have a look on the rate of reaction as per stoichiometry. My dear students, in this particular reaction, we have got A and B as the reactant and C and D as the product. Now, there are few terminologies which I'm going to introduce now. Few terminologies. You must be knowing, with time, reactants keep on disappearing with time, right? And with time, products keep on appearing. So, whenever I'll be defining a term, rate of disappearance. Rate of disappearance. For example, I'm writing rate of disappearance of what? Let's say I'm writing rate of disappearance of A. A is a reactant, right? Disappearance is the term which is used for reactants basically. Okay, how exactly I'm going to write it mathematically? Since I'm writing rate of disappearance, so I'll be starting with the minus sign. Then I'll write change in the concentration of A divided by dt. This whole term, it gives me the rate of disappearance of A. Okay, minus times change in the concentration of A divided by time. Similarly, if I want to write the rate of disappearance of B, if I want to write the rate of disappearance of what? Rate of disappearance of B. Again, I'm using the term disappearance, so I'll be starting with minus sign. Change in the concentration of B divided by dt. This term also, it gives me the rate of disappearance of B. Perfect. Similarly, I can define one more term, that is the rate of appearance. Rate of appearance, let me tell you, rate of appearance, it's defined for the products, and product here is C and D. For example, I want to write mathematically the rate of appearance of C. How am I going to write it? Since I'm using the term appearance, so I'll be using the sign positive because I'm using the term appearance, right? Now I'll be writing change in the concentration of C divided by dt. Similarly, if I write rate of appearance of D, how do I write the rate of appearance of D? Rate of appearance of D. Since I'm using the term appearance, I'll start with the sign plus. It is change in the concentration of D divided by dt. This term gives you the rate of appearance of D. I hope this is clear, right? I hope you got to know exactly how to write rate of disappearance and rate of appearance. Number one. Number two. Let me write the reaction again. The reaction is N1A plus N2B. It gives N3C plus N4D. This is the reaction. Okay. Now, let me tell you one more thing. Till now, I told you how to write the rate of appearance and rate of disappearance. Correct? Now, let's have a look like how to write the exact rate of reaction. How to calculate the rate of reaction. Rate of reaction can be written as, it can be written as the rate of disappearance or appearance of reactant or product divided by the stoichiometric coefficient of reactant or product. What is meant by that? See how it's to be written. See guys, rate of reaction is equal to, let's try to write the rate of reaction in terms of A. A is a reactant. What is the stoichiometric coefficient of A? It's N1. A is a reactant and it disappears with time. So I'll be starting with minus sign. 1 divided by stoichiometric coefficient is N1. Change in the concentration of A divided by dt. This whole term is going to give me the rate of the reaction. Similarly, rate of reaction in terms of B. B is again the reactant. So start with minus sign. 1 divided by stoichiometric coefficient is N2. Change in the concentration of B divided by dt. This whole term is going to give me again the rate of reaction only. Yes. At the same time, write the rate of reaction with respect to C. C is the product and product appears with time. Right? Stoichiometric coefficient is N3. Since I'm writing with respect to product, so I'll start with plus sign. 1 divided by stoichiometric coefficient is N3. It's going to be change in the concentration of C divided by dt. Similarly, in terms of D, it's going to be plus 1 divided by N4 d of D divided by dt. Perfect. So this is something which you must know how to write. You must know how to write this particular equation. And this equation we call as differential form. You call it as differential form of rate. Differential form of rate. And my dear students, just remember one thing. Just remember one thing. Just remember one thing. Whenever you have to write the rate of disappearance or rate of appearance, you do not have to divide with the stoichiometric coefficient. You do not have to divide with the stoichiometric coefficient. But whenever you have to calculate the rate of reaction, you have to divide with the respect to stoichiometric coefficients. Yes, got it? Perfect. Is it clear? Let me know once in the chats, everyone. Is everything clear? Quickly let me know in the chats. Quickly let me know in the chats if every single thing is clear. Let me know quickly in the chats. Quickly, everyone. Everyone, quickly. All right, one more thing. One more thing, guys. One more thing. Let's assume all the reactants and products right here are in gaseous state. Let's assume all the reactants and products right here are in gaseous state. Let's assume this reaction is carried out at constant temperature. Let's assume this reaction is carried out at constant temperature, okay? Now, you must be knowing, as far as your ideal gas equation is concerned, P is equal to nRT divided by V, right? This is something every one of you would be knowing. Now, dear students, N by V, number of moles per unit volume. Do we call it as concentration? Yes. Number of moles per unit volume is concentration. So, if I write PA, PA means concentration of A multiplied by R multiplied by T. If I write PB, it's going to be concentration of B multiplied by R multiplied by T. Similarly, PC, concentration of C multiplied by R multiplied by T. Right? Now, guys, I can say R is equal to minus 1 divided by N1. It is going to be D of. Instead of concentration of A, can I write pressure of A divided by RT? Yes, you can write pressure of A divided by RT, and already there is dt. Similarly, minus 1 divided by N2. Minus 1 divided by N2. It's going to be D of. Concentration of B means pressure of B divided by R T multiplied by dt. Similarly, it's going to be plus 1 divided by N3. D of pressure of C divided by RT, and it's going to be dt. And in the similar way, plus 1 divided by N4, right? 1 divided by N4 is going to be D of pressure of D divided by RT multiplied by dt. Perfect. Now, what you can do over here, this RT and RT everywhere gets cancelled. So, you got one more differential form of rate in terms of pressure. It's minus 1 divided by N1, change in the pressure of A divided by time interval dt, which is equal to minus 1 upon N2, change in the pressure of B divided by dt. Similarly, plus 1 divided by N3, change in the pressure of C divided by dt. And similarly, it's going to be plus 1 divided by N4, change in the pressure of D divided by dt. So over here you got one more differential form. Over here you got one more differential form. Perfect. Now it's completely your wish. It's completely your wish. This is also called as differential form of rate. This is also called as differential form of rate. And do remember, whenever you use any of these terms, either this one or this one or this one or this one, whenever you use any of these terms to calculate the rate of reaction, do remember the units of rate at that time will be moles, liter inverse, second inverse, right? Or moles, liter inverse, minute inverse, hour inverse, whatever. But my dear students, whenever you use any of these terms, to calculate rate of the reaction, do remember the value comes in ATM second inverse or bar second inverse or bar liter inverse, bar minute inverse, etc., etc. Perfect. So one thing which I would want you guys to remember from now onwards, whenever in a question they ask you to calculate the rate of reaction in terms of moles per liter per second, use any of these terms. Whenever they ask you to calculate the rate of reaction in terms of ATM second inverse or bar second inverse or ATM, let's say R inverse, use one of these terms as per the question. Right? I hope this is clear to everyone. Let's try to do few questions first so that you can understand it, you can analyze it properly. Okay? One very simple question which I'm giving you. Just look at the question and see whether you can solve it or not. Lately, a lot of spammers have started coming into the chats. It's okay, welcome spammers. You're all nonsense. Yeah? Quickly, let me know in the chats. Can you do this question? Quickly, guys. Guys, I'll try to do as much as possible. You know, like since I started today, it was just like only teaching, right? I did not stop. I wanted to complete all the very, very, very important topics basically. So if it's not completing today, it's completely fine. We'll take one more session, okay? We have time, chill. All right, let's have a look on this question. We are given with a reaction. The reaction is given to us in the balanced form. If the rate of appearance of O2, is given. First of all, how do you write rate of appearance of O2 mathematically? Rate of appearance of O2 mathematically plus d of O2 divided by dt. This is your rate of appearance of O2. It's given to us as 0.5 moles liter inverse second inverse. What are we supposed to calculate? We are supposed to calculate the rate of disappearance of N2O5. How do you write rate of disappearance of N2O5? Rate of disappearance, start with the minus sign because disappearance is there. d of N2O5 divided by dt. This is what you call as the rate of disappearance of N2O5. You have to get the value of this particular term. One term is given to us and this particular term we need to calculate. How exactly you are going to do it? Look at this particular reaction carefully. The reaction is given in the balanced format. Let's write the differential form of rate for this particular reaction. I'll say rate of reaction is equal to, in terms of N2O5. N2O5 is a reactant, so start with minus sign. 1 divided by stoichiometric coefficient is 2. Change in the concentration of N2O5 divided by what? Divided by dt is equal to N2O4. It's a product. Start with a plus sign. 1 divided by stoichiometric coefficient is 2. Change in the concentration of N2O4 divided by dt. Similarly, in terms of O2, plus, it's going to be d of O2 divided by dt because its stoichiometric coefficient is 1. Now, my dear students, what you can do, you can just take this term, and this particular term out of this equation. Just equate them individually. When you equate them individually, what you'll be getting? You'll be writing minus d of N2O5 divided by dt is equal to, take 2 here in the numerator, it's plus 2 times d of O2 divided by dt, which will be equal to 2 times d of O2 divided by dt is given 0.5. So multiplied by 0.5, the value comes out to be 1. It's going to be mole liter inverse second inverse. Is this something which we were supposed to calculate? Yes, this is the term which we were supposed to calculate. Correct? This is what you call as rate of disappearance of N2O5. That's something which you were supposed to calculate. The rate of disappearance of N2O5, which came out to be 1 mole liter inverse second inverse. I hope this is clear to everyone. Let me know quickly in the chats with the thumbs ups, everyone. Everyone means everyone. Quickly. Quickly, guys. Everyone. Everyone in the chats. Is it clear? No, minus won't stay there. How come minus will stay there? A rate can never be negative, right? That's why we start with minus sign when it comes to reactants, so that negative becomes positive at the end. Done? All right, let's see how exactly this question is to be solved. Calculate the rate of reaction in the interval 5 to 15 seconds. 5 to 15 seconds. Look at the interval. This is 5, this is 15. In this particular interval, you have to calculate the rate of the reaction. This 5 to 15 second means it is the interval of 10 seconds. It is the interval of 10 seconds. In this 10-second interval, we need to calculate the rate of reaction. Okay? Now, my dear students, the graph which is given to you, look at the graph carefully. With the time, the concentration is decreasing. So, it has to be the graph of reactant. Because you know, with time, it is the concentration of reactant which decreases. Right? It is the concentration of reactant that decreases with time. So, it has to be the graph of reactant. And reactant in this particular reaction is your NH3. So, it has to be the graph of NH3. It has to be the graph of NH3. So, what are we supposed to calculate? I am supposed to calculate the rate of the reaction in the interval 5 to 15 seconds. So, I'll say rate of reaction in terms of NH3. In terms of NH3, start with minus sign because it's a reactant. 1 divided by 2. Change in the concentration of NH3 divided by time interval, that's delta T. Right? So, you can write it like this. R is equal to minus 1 by 2. Change in the concentration of NH3. At 5 seconds, the concentration of NH3 is 0.6. At 15 seconds, the concentration of NH3 is 0.1. So, this was the initial concentration of reactant. Now, this is the final concentration. So, change in the concentration of reactant will be equal to final concentration minus initial concentration divided by time interval, that is 10 seconds. You just need to solve it and get the answer in moles per liter per second. That's all. Right? Done, understood? I'm sure it's clear and you can easily solve it. You can easily solve it. One more question. Look at the question carefully. Look at the question carefully. The question is for the reaction, for the following reaction, some parameters are given. Okay. Reaction is also given. And there is few data. There is some data which is given to us as well. Let's properly see what we are supposed to calculate. We are supposed to calculate the relation between K1, K2 and K3. How are you going to solve this? How are you going to solve this? First of all, the reaction that's given to me, let's try to write the differential form of rate for this particular reaction. How exactly? It's going to be rate of reaction is equal to N2O5 is the reactant, so start with minus sign, 1 divided by stoichiometric coefficient is 1 only. Change in the concentration of N2O5 divided by dt is equal to, with respect to NO2, NO2 is the product, so start with plus 1 divided by stoichiometric coefficient 2, change in the concentration of NO2 divided by dt. With respect to O2, it's plus 1 divided by stoichiometric coefficient is 1 by 2. So 1 divided by 1 by 2 makes it 2, right? It is change in the concentration of O2 divided by dt. Correct? Now, my dear students, look at all the parameters that are given to us. Minus dN2O5 by dt, minus dN2O5 by dt, its value is given, K1, its value is given as K1 multiplied by N2O5 concentration is equal to, plus dNO2 divided by dt, plus dNO2 divided by dt, it's given to me as K2 N2O5. So it will be K2 and here it's going to be N2O5 divided by what? Divided by 2 is equal to 2 times. D of O2 divided by dt is also given to me. It's given to me as K3 multiplied by N2O5 concentration. So dear students, this N2O5, N2O5, N2O5 is cancelled out. So finally I'm left with K1 is equal to K2 divided by 2, which is equal to 2 times K3. If you multiply throughout with 2, you get 2 times K1 is equal to K2 is equal to 4 times K3. This is the relation between K1, K2 and K3, which you were supposed to calculate as far as the question, right? Is it clear to everyone? Is it clear to everyone quickly? Quickly, guys. Is it clear to everyone? Right? Is it clear to everyone? Quickly, quickly, everyone. Clear? Clear till here? Quickly. I don't know abhi kitna time more. Okay, so let's have a look on this particular topic. It's a simpler one only. It's law of mass action. Okay. वैसे it's not much needed. Let's move on directly to, just a second. This law of mass action is not needed. Just a second. Yeah. This is the topic from which question comes. This is the topic from which question comes. Experimental determination of order. Experimental determination of order. In this one only, I'll tell you this law of mass action and all, okay? For example, you've got a reaction in this format. N1A plus N2B, it gives products. Let's say this is the reaction that's given to us. A balanced reaction. A balanced reaction. How can we calculate the rate of this particular reaction? One way is the differential form that you know. One way is the differential form that you know, right? Okay. Another one is going to be the law of mass action. As per law of mass action is concerned, rate of reaction is directly proportional to the product of active masses of reactants. Product of active masses of reactants raised to the power of the respective stoichiometric coefficients, N1, N2. Right? If I remove this proportionality sign, I'll be getting a constant. I'll be writing active mass of A raised power n1, active mass of B raised power n2. This is one more way of getting the rate of reaction. But my dear students, since we are using law of mass action to calculate rate of reaction, so whatever rate you will be getting after using this law of mass action, that's called as theoretical rate. That's called as theoretical rate. Since we are using law of mass action, we are using law of mass action. By using law of mass action, when you calculate the rate value which you get by using law of mass action, that's what we call as theoretical rate. Okay. Now at the same time, there are some reactions in which experimentally determined rate comes out to be different as that of expected from law of mass action. There are some reactions in which the experimentally determined rate, since there are many ways by means of which you can calculate rate. One way is to use the law of mass action. Another way, do some experiments in the laboratory and get the experimentally determined rate. Correct? There are some reactions in which the experimentally determined rate comes out to be different from that of theoretically determined rate. That means, does that mean from this particular equation we always get the right answer? Does that mean from this particular equation we always get the 100% correct rate? What do you think? There are some reactions in which the experimentally determined rate comes out to be different than that of what? Than that of theoretically determined rate. That means this equation does not gives you 100% correct information. Okay? So that means we need to modify this equation. We need to modify this equation, and since I wrote a law of mass action here, now we are going to modify it and we are going to make it as rate law. We are going to make it as rate law. So rate law is basically, it is based on, rate law is based on law of mass action. Rate law is based on law of mass action. Okay? It's based on law of mass action. How exactly? Let's keep the reaction same. N1A plus N2B gives products. If you use rate law says R is equal to rate constant. Now you will write active mass of A raised power X, active mass of B raised power Y. Now what do you think is the difference between rate law and law of mass action? In the law of mass action, the powers were taken as the stoichiometric coefficients. Here the powers are kept as X and Y. And this X and Y, these are the two terms which are calculated experimentally. Right? Yes, this X and Y, these are the terms which are calculated experimentally. And let me tell you, this X over here, it's called as order of the reaction with respect to A, and similarly Y is also called as order of the reaction with respect to B, and if I take the sum of the two, it is something which you call as overall order of the reaction. Overall order of the reaction. Okay. There are some reactions in which theoretical rate and experimental rate can be equal, but it's not necessary that it will be always equal. It's not necessary that it will be always equal. Right? There are some reactions in which theoretical rate and experimental rate both will get from both you will get the same value. But in some reactions it can be different as well. And this is the actual, this is the corrected one. This is the corrected form. Okay. You must have studied something called as elementary reactions. You must have come across something called as elementary reactions. Elementary reactions are the ones which are completed in a single step basically. Which are completed basically in a single step, right? Which are completed in a single step. You must be knowing about that. Yes? Right? Now, dear students, when we talk about elementary reactions, in case of elementary reactions, if you want to calculate rate with the help of law of mass action, that means theoretical rate. And when you calculate rate with the help of rate law, that means experimental rate. For elementary reactions, these values will come out to be same. These values will come out to be same. Whether you want to calculate the rate with the help of law of mass action, or you want to calculate rate by means of rate law. From both the equations, you will get the same result. What does that mean? That means for elementary reactions, N1 is equal to X and N2 is equal to Y. N1 is equal to X, N2 is equal to Y. Right? What was this N1, N2? N1 and N2 were the stoichiometric coefficients here, and X and Y were something which were measured experimentally. Okay? Let me know once in the chats if this concept is clear to everyone, if this part is clear. If this part is clear, quickly. Quickly, everyone. Okay, tell me one more thing. For example, you have got a reaction like this. A plus 2B, it gives C. It gives C. I'm telling you this reaction is elementary. I'm telling you this reaction is elementary. Can you tell me the order of the reaction? Can you tell me the order of the reaction quickly? Can you tell me the order of this particular reaction? So first of all, I'll be writing rate law for this. Its rate law is going to be simple. R is equal to K. It's going to be, for example, concentration of A or active mass of A and raised per X, concentration of B raised per Y. I'm using rate law. But you know, for elementary reactions, X is N1, Y is N2. So you can modify it. It's going to be concentration of A raised per 1, concentration of B raised per 2. And these powers are something which you call as order. So I must say the overall order of the reaction. The overall order of the reaction is going to be 2 plus 1, that comes out to be 3. Done and dusted, right? Yes? Clear? Perfect. Now we are going to have a look on how order is calculated experimentally. Or before that, let's try to do few basic questions. Let me see if you can solve this question or not. What do you think? Akansh, yes, you're right. You're right. Now focus on the session. For a chemical reaction A gives B, it is found that the rate doubles when the concentration of A is increased 4 times. Find out the order of the reaction. How to do it? See, the reaction that's given to us, it is A gives B. Okay? Its rate constant is K. Let's assume that the order of this particular reaction is N. Let's assume that. Order of this particular reaction is N. Okay? In order to calculate order, do remember whenever you need to calculate the order of any reaction, you'll be always writing the rate law. Write the rate law for this particular reaction. I'll say R is equal to K, concentration of A raised per N. Let's call this as equation number 1. Let's call this as equation number 1. Now, as per the question, the rate doubles. The rate doubles. Instead of R, you are writing 2R. Rate is doubling when the concentration of A is increased 4 times. When the concentration of A is increasing 4 times. Right? So, initially, A was the concentration, now it's 4A. After doing the concentration of A 4 times, rate is doubling basically. We need to calculate the value of N. So, how am I going to calculate the value of N from here? Dear students, just do one thing. Just divide both the equations. Just divide 2 by 1. When you divide equation second by 1, you get 2R divided by R, that comes out to be 2, is equal to K and K got cancelled, A power N cancelled, is going to be 4 raised per N, right? So you can write 2 is equal to 4, you can write 2 square, so it's going to be 2 raised power 2n. Over here the power is 1, that means 2n is equal to 1. This 2n is equal to 1, so n has to be equal to 1 by 2. So what was n? N was the order of reaction, overall order of the reaction, 1 by 2. Clear? Is it clear to everyone? Quickly. Perfect. Let's try to solve one more question of the similar manner. Let me see if you can do that or not. What do you think about this one? Quickly. What do you think about this one quickly? Look at the question carefully. See what the question says. We are given first of all with the equation, with the chemical reaction A gives B. Okay, this is the chemical reaction A gives B. Its rate constant is given to us as K. Let's assume order of this particular reaction is equal to N. Let's assume order of this particular reaction is N, okay? Some people are saying 1 is the answer, yeah? Let's see, let's give it a try. Now, as per the question is concerned, if I want to calculate the order of this particular reaction, I will have to write the rate law. R is equal to K. It's going to be concentration of A raised by N. Now, you know, concentration of A means number of moles of A divided by volume, total volume of the system in liters raised by N. Correct? Let's call this as equation number 1. Let's call this as equation number 1. Yeah? Let's call this as equation number 1. Now, dear students, as per the question is concerned, the rate of the reaction becomes half. Rate becomes half. Earlier rate was R, now it becomes R by 2. When? When the volume of the vessel is doubled. So, initially the volume was V. Now we are doubling the volume. It's becoming 2V now, raised by N. Let's call this as equation number 2. Just divide the two equations. 1 by 2. It's going to be R divided by R by 2 is equal to K got cancelled, right? So, it's NA divided by V raised by N multiplied by, it's 2V divided by NA raised by N. Simple calculation I'm doing. Simple calculation. Correct? So, first of all, R got cancelled, 2 will come up is equal. NA cancel, V cancel. So, on right hand side, you're only getting 2 raised by N. So, this equation is only valid when the value of N is equal to 1. And what was this N? N was the order of the reaction. Is this clear? Is this clear to everyone quickly? Quickly guys, quickly. It should be clear, yeah? Now there is one more type of question that's asked from kinetics, that's experimental determination of order. Experimental determination of order. How can we calculate the order of reaction experimentally? Have a look now. Have a look. I'll show you one question. From this, everything will be clear, okay? As per this particular question is concerned, as you can see clearly, we are given with a reaction, okay? And some experiments have been carried out. From the first experiment, when the concentration of NO is kept this much, H2 concentration is kept this much, at that time rate of the reaction was observed as this much experimentally. Similarly, 3 experiments have been carried out. 3 experiments have been carried out, okay? Now, from this particular data, from these experiments, I need to get the order of the reaction. And how we are going to solve it? See, first thing, just do one thing. Just write the rate law for this particular reaction. It's going to be K, concentration of NO raised by X, concentration of H2 raised by Y. This is the rate law for the reaction. Now, look at the data carefully. Look at the data carefully. Look at the data carefully. First of all, dear students, let me select those 2 experiments wherein the concentration of H2 is kept same. So, let me focus on the first 2 experiments where the concentration of H2 is same. Imagine as if H2 is not here in the equation. Imagine as if H2 is not here in the equation. Now, when you move from 1 to 2, what is happening to the concentration of NO? Concentration of NO is increasing 3 times. Concentration of NO is increasing 3 times. So, when you are making this 3 times, when you are increasing the concentration of NO 3 times, what is happening to the rate of the reaction? Rate of the reaction is also increasing 3 times. Rate of the reaction is also increasing 3 times. Imagine as if H2 is not here. On increasing the concentration of NO 3 times, the rate is also increasing 3 times. So, the power of NO has to be 1 because 3 raised power 1 comes out to be 3. If the power is 2, then 3 ka square comes out to be 9. But it's observed that on increasing the concentration of NO 3 times, rate also increases 3 times. That means we got to know X value has to be 1, then only that observation is valid. X is 1. Now, Y. How do you get the Y value? How do you get the Y value? Now, do one thing. Select experiment number 2 and experiment number 3 in which the concentration of NO is kept constant, right? Imagine as if NO now is not here. Now, when you are moving from 2 to 3, Is the concentration of H2 being increased 4 times? Yes. Rate of reaction is also being increased 4 times. So, when you increase the concentration of H2 4 times, rate is increased 4 times. Making this 4 times makes this 4 times. That means the Y value again has to be Y only, 1 only, right? Because if Y was 2, then on increasing this 4 times, it would have been 16 times, right? Yes? Clear? So you got X, you got Y. So what is going to be the overall order of the reaction then? I must say the overall order of the reaction is X plus Y, that comes out to be 2. Done? Clear to everyone? Quickly let me know in the chats if it is super clear. Perfect. Moving on. Now let's talk about something which is interesting, that is zero order reactions. Zero order reactions. First, tell me in the chats if every single thing is properly done till here. Are you getting that confidence of solving things? Quickly, everyone. Everyone. We are not going to take any break now. Okay. Perfect, guys. Now let's have a look on the zero order reactions. Let's say I've got the reaction like this, A gives B, whose rate constant is K, and I'm assuming the order of this particular reaction is 0. I'm assuming the order of this particular reaction is 0. Okay? Order is 0. I'm assuming certain things. Let's say initially at time t is equal to 0, the concentration of reactant is A0, this is 0. This is something which I'm assuming. Initially, the concentration of reactant is A0, the concentration of product is 0. Now, as the time passes, what happens to the concentration of reactant? Concentration of reactant decreases with time, right? So, at any time t, let's assume the concentration of reactant left in the container is AT. The concentration of product formed is BT. Let's assume that. Okay? Initially, the concentration of the reactant at time t is equal to 0 is A0. With time, the concentration of reactant decreases, right? With time, the concentration of reactant decreases. So, I must say the concentration of reactant left at time t is AT. Okay? So, can I first of all say something like this? Can I say AT value will be definitely less than A0? This is understood, everyone? Is this understood? Yes in the chats. Is this understood? Is this understood? Quickly. Okay. Now, guys. Now, first of all, I want you guys to write the rate law for this zero order reaction. Like this. R is equal to, it's going to be rate constant K, concentration of A raised per order. Order is 0. This is how you write rate law. This is how you write rate law for the zero order reactions. Okay. This is how you write rate law for the zero order reactions. Now, what about the integrated rate equation? I'm not going to derive the equations. I'm just going to give you the equations and let's see their application part. Okay. What about the integrated rate equation for the zero order kinetics? It's written like this. AT is equal to A0 minus KT. This equation is something which you call as the integrated rate equation for the zero order kinetics. Integrated rate equation for the zero order kinetics. Basically, this T is the time in which the concentration of reactant is changing from A0 to AT. Matlab this T is the time in which the concentration of reactant. This T is the time in which the concentration of reactant is changing from A0 to AT. Perfect. This is the first equation which you need to remember. Okay, number one. Number two, there is something called as half-life, T half. T half for the zero order reactions, as you all must be knowing, it is A0 divided by 2K, where A0 is the initial concentration of reactant and K is the rate constant. T half, half-life of the reaction. Half-life of the reaction, right? Half-life of the reaction. At the same time, guys, one more thing. At the same time, let's have a look on one more thing. Let's have a look on one more thing. This was half-life. There is something called as completion time as well, right? I hope you know completion time. Time taken to complete 100% of the reaction. Time taken to complete 100% of the reaction. Time taken to complete 100% of the zero order reaction, that's A0 divided by K. That's A0 divided by K. Remember these equations. These are very important, right? See, time taken to complete 50% of the reaction is A0 by 2K. Time taken to complete 100% of the reaction, that's A0 divided by K. So, from these two equations, can I say a zero order reaction, is 100% completed. A zero order reaction is 100% completed in a zero order reaction is 100% completed in 2 half-lives, right? Just by having a look on these two expressions, we can categorically say it. A zero order reaction is 100% completed in 2 half-lives, correct? Now, there is one more thing. There is one more thing. This is the reaction, a zero order reaction, for example. Let's say I need to calculate the degree of dissociation alpha for the zero order reaction. How do I calculate the degree of dissociation alpha for the zero order reaction? How do I get it? Alpha is basically number of moles of reactants dissociated divided by initial moles of reactants taken. Number of moles of reactants dissociated divided by initial moles of reactants taken. So, I can say alpha is nothing. How many moles of reactants dissociated? Initially, the moles were A0. Finally, the moles of reactant left were 80. So, initially, there were A0 moles of reactants. The left out moles are 80 divided by initial moles are A0. So, alpha is going to be A0 minus. Instead of 80, you can write A0 minus KT as per integrated rate equation. Divided by what? Divided by A0. So, alpha from here comes out to be KT divided by A0. This is alpha. This is alpha. Alpha is equal to KT divided by A0. This is the question which can be directly asked to you. This is the question which can be directly asked to you. Alpha, degree of dissociation for the first order reactions is equal to, it's going to be KT divided by A0. What else can be asked from here? Just a second. What else can be asked from here? Yeah. You must know about the units of rate constant as well for the zero order reactions. Units of rate constant. Yes. Units of K for the zero order reactions. Well, K has got units, moles, liter inverse, raised power 1 minus n and second inverse, right? Where n represents the order of the reaction. Well, in case of your zero order reactions, n value is 1. So, rate constant unit is simply going to be moles, liter inverse, second inverse, or in terms of pressure, it's going to be ATM second inverse. Okay. Well, there are certain graphs related to zero order reactions as well. Or before the graphs, let me show you one more scenario. Let's say the reaction is like this. A gives B, its rate constant is K, and its order is 0. Order of the reaction is 0. Let's assume this. Okay, let's assume this. Now, people, at time t is equal to 0, the initial concentration of reactant is A0. At time t1, the concentration of reactant left is AT1. At time t2, the concentration of reactant left is AT2. Now, there is one more equation which we can basically derive, but I'm not going to derive that. I'm just going to give it to you. right? So it's going to be AT2 is equal to AT1 minus K times T2 minus T1. This is one direct equation which can maybe solve a lot of time while solving the questions. Okay, this is one more equation from which you can get the the rate constant of the reaction, rate constant of the zero order reaction. Yes, perfect. Now after this, let's have a look on the graphs which are related to zero order reactions, right? The graphs which are related, then we can go on to the questions. We can move on to the questions. The graphs related to zero order. The first graph which I'm plotting here, it's between rate of reaction versus concentration of reactant. You know, as far as your rate law is concerned, you know, rate of reaction is equal to rate constant multiplied by concentration of A raised power 0. So you can write R is equal to K, A raised power 0 is 1. So is the rate dependent on the initial concentration? No, rate is not dependent on the initial concentration. Independent, right? Okay, number one. Number two, if you want to plot a graph between AT versus T, if you want to plot a graph between AT versus T, you can do that. Since in case of zero order reactions, I told you a few minutes back, AT is equal to A naught minus KT. AT abhi you are plotting along y-axis, T you are plotting along x-axis. So this is your M, this is minus sign here, and this term is your C. So y is equal to minus mx plus C. It's going to be like this. What about the slope of this particular graph? Slope of this particular graph is equal to minus K, and intercept of this particular graph, which is C, that is A naught. This is one more graph which you need to know. Okay. Similarly, if you want to plot a graph between T half-life versus what? Just have a look. T half is equal to A naught divided by 2K. Let's plot a graph between T half versus A naught. Since you know your half-life, that's equal to A naught divided by 2K. Or you can say 1 by 2K into A naught. 1 by 2K multiplied by A naught. T half you are plotting along y-axis. A naught you are plotting along x-axis. This whole term is your M. Y is equal to mx. It's a straight line. What about the slope of this graph? Slope means the value of M. And M value over here is 1 by 2K. Okay, this is one more graph which can be asked. Right? Similarly, there is one more equation which I gave you a few minutes back. That was completion time. T 100% versus A naught. T 100% versus A naught, it's going to be again the same graph, but its slope is not 1 by 2K, its slope will be 1 by K. Okay. Then there is one more final graph for the zero order reactions. What is that? The final graph will be between, just a second. Oh, what just happened? Okay. The final graph is going to be between alpha versus A naught. Alpha versus A naught. Okay. So let's say this alpha, this A naught here. In case of zero order reactions, we got to know alpha is equal to A naught divided by, how much is it? Which we derived a few minutes back. Alpha is equal to KT divided by A naught. Alpha is equal to KT divided by A naught. So this is, for example, your KT and this is A naught. What do you think about alpha and A naught? Alpha and A naught, are they directly proportional or inversely? Alpha and A naught, directly or inversely? Inversely proportional to each other. So nature of the curve is going to be rectangular hyperbola. Perfect. These are few graphs from which questions can be asked basically. I hope everything is clear till here. Is that? Is it clear to everyone quickly? Class 11th physical chemistry will be doing in the separate session, okay? Are you tired? You want a break, huh? Okay, let's take a break. Let's take a break, then we'll continue. What is the time? Let's take a break for 30 minutes again. Let's take a break. I'll see you exactly at 7:35 again, okay? We have to complete first order, then we have to complete the Arrhenius equation as well. I'll let you know about the mock test, etc. as well, okay? Just take a break, have some tea, get refreshed, cool, and I'll get back also, huh? Happy birthday, Akash. God bless you. Happy birthday. See you guys in a while, huh? Bye-bye. Guys, am I audible, visible to you? Can you all hear me? Can you see me? Yes? Can you all hear me? Am I perfectly audible and visible to everyone? Quickly let me know in the chats. Yes, you don't worry. I'll take one more marathon, guys. Relax. I'll take one more marathon. See, tomorrow it's going to be Shreyas and HSP sir. Tomorrow is Wednesday. On Thursday, it's Ambika ma'am. On Friday, I'll take one more marathon. On Friday, I'll take one more marathon in which class 11th chapters will be done. Need not to worry about that. Okay? Because I'm teaching everything in the detailed manner, right? Should we start then? Let me have some water first. Then we shall be starting. Just call up all your friends again. Call up everyone, cool. Call up everyone, guys, quickly. Okay. So let's get going then. Till now, we were done with the zero order reactions and its graphs, right? So now we are going to see the questions basically. Let's have a look on the questions, like what kind of questions can be asked related to these zero order reactions. Are you guys ready for it? Perfect, guys, wonderful. Okay. All right then. The first question related to the zero order reactions, let's have a look. Let's see how this sort of a question is to be solved. For a zero order reaction, A gives B. So I'm given with a reaction A gives B, whose rate constant, for example, is K, and it's mentioned that the order of the reaction is 0. It was observed that at the end of an hour, 75% of A has reacted. Okay, have a look, properly understand. First thing, let's assume at time t is equal to 0, initially the concentration of reactant is A naught. Let's say initially at time t is equal to 0, the concentration of reactant is A naught. Okay. So the concentration of product right now is absolutely going to be 0. Right. Now it's mentioned in the question that at the end of an hour, it was observed that 75% of A has reacted. Now you tell me. It is observed that at the end of an hour, 75% of A has reacted. What does that mean? That means 75% of reactant has got converted into products. After 1 hour, it is observed that 75% of reactant has got converted into product. So I will be left with 25% of the reactant. I'll be left with only 25% of the reactant. Right? So I would say at the end of an hour, 25% of reactant will be left in the container. 25% of what? Of reactant. 25% of A naught. This is going to be the concentration of reactant left after 1 hour. And concentration of reactant left is always represented by AT. Concentration of reactant left is always represented by AT. So I must say this AT is equal to A naught divided by 4 when you solve it. AT is equal to A naught divided by 4 when you solve it, right? So I got one condition basically. The condition is after 1 hour, the concentration of reactant left, which I'm representing with AT, is equal to A naught by 4. What are we supposed to calculate? At what time A will be 10% unreacted? At what time A will be 10% unreacted? That means at what time 10% of reactant will be left? 10% of reactant means 10 divided by 100 multiplied by A naught, which you can write as A naught divided by 10. So, I am supposed to calculate basically at what time, the concentration of reactant left in the container will be A naught divided by 10. So, two conditions we have, two conditions. At t is equal to 1 hour, the concentration of reactant left is A naught by 4. At what time the concentration of reactant left will be A naught by 10. So, dear students, I'll be using the integrated rate equation. Let's use the integrated rate equation for the zero order reactions. And let's see how integrated rate equation is used. What is our integrated rate equation all about? AT is equal to A naught minus KT, right? This is the integrated rate equation. In this equation, use the first expression, use the first condition. In the first condition, AT is equal to A naught by 4 is equal to, this is A naught minus K. In the first condition, T is equal to 1 hour. T is equal to 1 hour, right? So, from this particular equation, K comes out to be equal to 3 divided by 4 A naught, right? This is something which you got. K is equal to 3 divided by 4 A naught. So, from the first condition, I got the value of rate constant. From the first condition, I got the value of rate constant. Now, let's talk about the second condition. Use the second condition in this particular integrated rate equation now. In the second condition, AT is given to me as A naught by 10. A naught divided by 10 is equal to A naught, I am writing as such, minus K value is given to me as 3 by 4 A naught multiplied by time T I need to calculate. So, A naught gets cancelled out. When you solve this equation, you will be getting T value exactly as, I think you will be getting it as 1.2 hours. T value you got to know as 1.2 hours. What is meant by this? What is meant by this? It simply means after 1.2 hours, 10% of the reactant will be still left in the container as such in the unreacted form. Is that clear to everyone? Let me know once in the chats. Did you get how this sort of equation is to be solved? Quickly, everyone. Quickly. I'll show you one more similar type of question so that you can analyze, you can understand it properly. One more similar type of question I'll show, then maybe it'll be properly clear to you. Look at this question. But before solving this question, let me know once in the chats if everything seems clear. Quickly, guys, everyone, with the thumbs ups. With the thumbs ups, quickly. Okay, I'll show one similar type of question so that this concept gets properly clear to you. Similar type of question I'm going to show you. Similar type of question. Have a look. A zero order reaction. Let's say I've got a zero order reaction in this format. A gives B. First of all, initially at time t is equal to 0, the concentration of reactant, let's assume it as A naught. So this is going to be 0. Now it's mentioned that a zero order reaction is 20% completed in 10 minutes. So it's mentioned that after 10 minutes, 20% reaction has got completed. That means after 10 minutes, 20% reactant has got converted into product. If 20% reactant has got converted into product, I must say 80% of the reactant will be still left as such. So after 10 minutes, 80% of the reaction will be left. 80% means 80 divided by 100, or you can write 0.8 A naught. This is basically the concentration of reactant left, and the concentration of reactant left we always represent with 80. So I got the first condition. The first condition is pretty simple. After 10 minutes, the concentration of reactant left is 0.8 A naught. It is 0.8 A naught. Now, at what time? At what time it will be 80% completed? At what time the reaction will be 80% completed? At what time 80% of reactant would have got converted? At what time 80% reaction gets completed? What does that mean? That means 80% of reactant has to get converted into products. 20% reactant will be still left. So at what time 20% reactant will be left? That's the question. So 20% of reactant means 0.2 A naught. So this is the one more condition. Look at this condition. Look at this condition. Look at the two conditions. The first condition says after 10 minutes, 20% reaction is completed. That means 80% reactant will be left. Now we have to check at what time 80% reaction is completed. That means 20% reactant is left. So how many? So how many conditions we got? We got two conditions. From the first condition, you will be calculating the rate constant. From the second condition, you will be calculating the time. First condition you will be using for the rate constant calculation, and second condition you will be using to calculate time. So what is my integrated rate equation? AT is equal to A naught minus KT. This is our integrated rate equation. Now dear students, in this particular equation, put the condition number 1. AT in the first condition is 0.8 A naught is equal to, this is going to be A naught minus K multiplied by time in the first condition is 10 minutes. So from this particular equation, you can get the value of K. It's going to be 0.2 A naught divided by 10. So you got the rate constant value from the first condition. Now from the second condition, we are going to get the time. Put the second condition data in the integrated rate equation. AT in the second condition is 0.2 A naught is equal to A naught minus K value. K value we got to know, that's 0.2 A naught divided by 10 multiplied by T, which we have to calculate. So A naught gets cancelled. So you got the equation 0.2 is equal to 1 minus 0.2 divided by 10 multiplied by T. From this particular equation, you will be getting the T value exactly as 40 minutes. So what is this T? T is the time at which 80% of reaction is completed. T is the time at which 20% of the reactant is still left in the container as such, which we were supposed to calculate. Let me know quickly in the chats if it's clear. Got it? Is it clear to everyone quickly? Is it clear to everyone quickly? Now you got to know. First condition you'll be using for the rate constant calculation. Second condition you'll be using to get the time. That's all. Right? Perfect. One more question I'm going to give you. Let me see if you can solve this one or not. Okay, look at this particular question. Look at this particular condition. The question is, for example, we are given with a zero order reaction A gives B. Okay, and the table is given. At time t is equal to 0, the concentration of reactant is 1 molar. At time t is equal to 0, the concentration of reactant is 1 molar. And you know, concentration of reactant at time t is equal to 0 is denoted by A naught. So as per the question, A naught value, the concentration of reactant at time t is equal to 0 is equal to 1 molar. A naught is equal to 1 molar. And look at the table carefully. After 120 seconds, the concentration of reactant left is 0. After 120 seconds, the concentration of reactant left is 0. What does that mean? That means this 120 seconds, it is the completion time when concentration of reactant left is 0. When 100% reactant has got converted into products. Right? So, as per the question, we are given with T 100% as well, which is equal to 120 seconds. What are we supposed to calculate? We are supposed to calculate the rate constant. Dear students, we know time taken to complete 100% of the zero order reaction, that's equal to A naught divided by K. Few minutes back only I told you, is equal to 120. So K value will be simply equal to A naught divided by 120. A naught value is equal to 1 divided by 120. And the units of K, you know, it's moles, liter inverse, second inverse. This is the answer of the question. Let me know quickly in the chats if it is again super clear to everyone. Quickly, with the thumbs ups. With the thumbs ups. With the thumbs ups. Quickly. Quickly, guys, everyone. These are some zero order reactions. Please and please remember them. They can be directly asked, right? These are the common examples of the zero order reactions. Okay, photochemical reaction between H2Cl2, photochemical reaction between H2 and Cl2, it is the common example of zero order. Decomposition of Hi over gold, it is the example of zero order. Decomposition of NH3 over molybdenum, it is again the zero order reaction. This can be the memory based question which can be asked to you. Okay, so please and please do remember these three reactions properly. These are given in your NCERT as well. Okay, perfect. Now let's move on to something called as first order reactions, right? Let's see first order reactions and their integrated rate equations. Again, I'm not going to derive any expression. I'll be just giving you the expressions. For example, the reaction is, I've got a reaction as A gives B. Let's assume it's a balanced chemical equation whose rate constant is K, and I'm assuming the order of the reaction is 1. I'm assuming the order of the reaction is 1. Okay. Now, dear students, at time t is equal to 0, let's assume the concentration of reactant is A naught. This will be 0. At any time t, the concentration of reactant left is denoted by AT, and the concentration of product formed is denoted by BT. First of all, let me write it over here. This A naught is nothing. It is just the initial concentration of reactant. It is just the initial concentration of reactant. Okay. What is AT? AT is basically the concentration of reactant. The concentration of reactant left at time t. Left at time t. Okay. Perfect. Now, if you write the rate law for this particular reaction, R is equal. It's going to be rate constant K, concentration of A, raised per order, that's 1. This is the first equation which you need to take a note of. Rate law for the first order reactions. Number 1. Number 2, what about the integrated rate equations? There are many ways of writing the integrated rate equation for the first order reactions. Okay. Now have a look. I can say the first form is ln of AT is equal to ln of A naught minus KT. Ln of AT is equal to ln of A naught minus KT. This is the first way of writing the integrated rate equation for the first order reactions. Number 1. Number 2. Log of AT is equal to log of A naught minus K divided by 2.303 multiplied by T. This is one more way of writing the integrated rate equation for the first order kinetics. Okay. This is one more way of writing the integrated rate equation for the first order kinetics. In the similar way, there are few more ways as well which I would want you guys to take a note of, because in the questions you will have to use all these equations basically. You can write the integrated equation in this form as well. K is equal to 1 divided by T. It's going to be ln of A naught divided by AT. Ln of A naught divided by AT. One more equation. Similarly, K is equal to 2.303 divided by T. It's going to be log of A naught divided by AT. One more expression for the integrated rate equation. Okay, one more expression. Similarly, K is equal to, or just a second. Have a look. Yes, guys, this is a live session. A lot of people asking, is this a live session? Of course. This is a live session. So these are, first of all, few forms of integrated rate equation for the first order kinetics, which you need to remember. And I'll show you its application in some time. Its application part, I'll show you in some time. Okay. Now, there are few more things which you need to know. For example, if I ask you time taken to complete X% of the first order reaction. X% means anything. Time taken to complete 20% of the first order reaction, time taken to complete 30%, 40%, etc., etc. Right? The equation is simple. Time taken to complete X% of the first order reaction, it's equal to 2.303 divided by K. It's going to be log of 100 divided by 100 minus X. Okay, this is one more thing which you need to know. Time taken to complete X% of the first order reaction is equal to 2.303 divided by K log of 100 divided by 100 minus X. Now, apart from that, is that it? No, this is not it. There are a few more things which you need to take a note of. Let's have a look what those things are exactly. Let's have a look exactly what those things are all about. Okay. One more way of writing the integrated rate equation for the first order reactions is AT is equal to A naught e raised power minus KT. AT is equal to A naught A raised power minus KT. This is one more way of writing the integrated rate equation for the first order reactions. In the similar way, there are few more things which you need to analyze, which you need to know. Let's say I need to calculate the degree of dissociation alpha. Let's say I need to calculate degree of dissociation alpha for this first order reaction, whose stoichiometry is 1:1. How do I get it? Degree of dissociation is calculated as number of moles of reactants dissociated divided by initial moles of reactants, right? So if I ask you how many moles of reactants got dissociated into products, initially we had A naught moles. Now we are left with 80 moles. So A naught minus 80. So A naught minus 80, right? A naught minus 80. It gives me moles of reactants which got dissociated into products divided by initial moles of reactant means A naught, right? So alpha you can calculate from here. It's going to be A naught minus. Instead of 80, you can write A naught A raised power minus KT divided by what? Divided by A naught. So A naught everywhere gets cancelled out. It's going to be 1 minus A raised power minus KT. This is how you calculate the degree of dissociation alpha for the first order reaction. Okay? Degree of dissociation alpha for the first order reaction. Now, dear students, if you look at this particular expression, in this particular expression, nowhere you can see A naught term. Nowhere you can see the initial concentration of reactant. So do remember one more thing. Degree of dissociation. Do remember degree of dissociation. Do remember degree of dissociation, right? Degree of dissociation is independent. Degree of dissociation is independent of the initial concentration of reactant in case of what? In case of first order reactions. In case of first order reactions. Do take a note of this. Similarly, if you look at this particular expression, in this particular expression, again you do not see any A naught term. Again you do not see any A naught term. What does that mean? That means time taken to complete X% of the first order reaction, it's again independent. It's again independent of the initial concentration of reactant. This particular term, it's very important. From this, I'll be showing you one question in some time. There are a few more important things which you need to know about the first order reactions. What is that? How do we calculate the half-life? Time taken to complete 50%, or you can say T half. Directly you can say T half. How do we calculate half-life in case of first order reactions? Half-life is equal to 0.693 divided by K in case of first order kinetics, in case of first order reactions, right? This is your half-life, okay? Now, if you ask me, how much time does it take to complete 100% of the first order reaction? Time taken to complete 100% of the first order reaction is infinite. A first order reaction never undergoes 100% completion, right? Do remember this thing as well. A first order reaction never undergoes. A first order reaction never undergoes 100% completion. Never undergoes 100% completion, right? It never undergoes 100% completion, unlike your zero order reactions, okay? There are a few more things which might be helpful to you. Do remember time taken to complete 75% of the first order reaction, it's equal to 2 times the half-life. Similarly, time taken to complete 87.5% of the first order reaction is equal to 3 times the half-life, and time taken to complete 99.9% of the first order reaction is equal to 10 times the half-life. These are few important results which I would want every one of you to know, okay? Now, after these results, we are going to apply them, but before the application of these results, I would want you guys to show all the graphs which we can make in the first order kinetics, all the graphs. Let's have a look on the graphs first of all, then we can go ahead with the questions. Is everything clear till here? Once, let me know in the chats quickly. Is everything clear till here? Is everything clear till here? All right, let's have a look on the graphs. The first graph which we are going to plot for the first order kinetics, the graph is like this. Rate of the reaction versus concentration of reactant. Rate of reaction versus concentration of reactant. You know, In case of your first order reaction, rate of reaction is equal to rate constant, concentration of A raised power 1. You are plotting rate along y-axis, you are plotting concentration of A along x-axis. So this is y, this is going to be your x, this is going to be your m. Y is equal to mx, so it's absolutely going to be a straight line, and the slope of this particular line is basically m, which is equal to k. The slope is k. This is the first graph which you need to know. First graph, okay? Second graph, let's try to plot it. Let's try to plot the second graph, which is ln 80 versus t. Ln 80 versus t. Few minutes back, I gave you one equation. Ln of 80 is equal to ln of A naught minus kt. So ln 80 you're plotting along y-axis, t you're plotting along x-axis, k is your m, and this minus is as such, and this ln of A naught is c. So y is equal to minus mx plus c, straight line with a negative slope. If I ask you, what is the slope of this particular curve? Slope is basically minus k for this. What about this intercept? Intercept is basically equal to ln of A naught, right? Intercept is equal to ln of A naught. This is one more graph which I would want you guys to remember. Yes? Perfect. Now at the same time, look at this particular one. Log of 80 versus t. When you plot log of 80 versus t, the curve is going to remain the same. It is just the slope of the curve will change. Slope now will be minus k upon 2.303. And intercept now it's going to be log of A naught. Log of A naught, right? These are few basic graphs which you need to remember. In the similar way, if you want to plot a graph between t half T half versus A naught for the first order reactions, you know, your T half is nothing, it is 0.693 divided by K, right? So T half is independent of the initial concentration of reactant, so it's like this straight line, independent, okay? Yes? Similarly, let's see a few more graphs. Let's see a few more graphs. Let's see a few more graphs, just a second. I think this much is enough. So, what we are going to do now, just a second. Forgot to give you the units of rate constant for the zero order reaction. Units of rate constant for the first order reaction, sorry. Units of rate constant. You know, K units are generally moles, liter inverse, raised power of 1 minus n, second inverse. Since we are talking about the first order reaction, so n is equal to 1, order is 1. So K value will be simply, its units will be simply second inverse or minute inverse or R inverse or whatever. Okay, just remember this one as well. Unit of rate constant for the first order reactions. I hope this is clear to everyone. Yeah? Clear? Now guys, I gave you one concept here. I told you to write one statement. Time taken to complete X% of the reaction. Time taken to complete X% of the first order reaction. That's independent of initial concentration of reactant. What does it mean basically? What does it mean basically? Let's have a look. Let's have a look. For example, I'm giving you one simple question like this. A reaction A gives B. Again the same reaction A gives B. Okay? Rate constant K, rate constant K. Alright? Now, for example, I'm giving a question like this. When the initial concentration of reactant was kept 5 molar, when the initial concentration of reactant was kept 5 molar, let's assume 20% of the reaction was being completed in 73 minutes. Understand the question. Understand the question carefully. I'm telling you, when the initial concentration of reactant was kept 5 molar, at that time, it was observed that 20% of the reaction was completed in 73 minutes. Now you tell me, if I keep the initial concentration of reactant as 10 molar, tell me, how long will it take to complete 20% of the reaction now? And I'm assuming the order of the reaction is 1. Can you let me know in the chats? I want to see exactly whether you will be able to solve this or not. How long will it take for the 20% of the reaction to complete now? Let me see exactly if you can solve this or not. What do you think? Quickly in the chats. Quickly let me know in the chats. What do you think about this one? Exactly, wonderful, good job. I told you time taken to complete X% of the first order reaction, it's independent of initial concentration. So of course, no doubt, you are changing the initial concentration of reactant, but time taken to complete, time taken to complete 20% of the reaction is going to remain the same only, right? Okay. One more point, which is important, please and please take a note of this as well. Take a note of this as well. Let's say I've got a reaction like this, A gives B. This is one shortcut which I'm going to give you. A gives B is one reaction, right? Let's say at time T1, the concentration of reactant was A1. Let's say at time T2, the concentration of reactant was A2. At time T3, the concentration of reactant was A3. At time T4, the concentration of reactant was A4. Okay? So this is time, which I'm plotting here, and this is concentration. This is concentration here. Right? Now, I'm going to write one statement, one simple statement which is going to help you out a lot in solving the questions. For example, if T2 minus T1 is equal to T3 minus T2, which is equal to T4 minus T3. That means I'm talking about the same time interval. If the time interval is same. If the time interval is same. In the same time interval, if the concentration of reactants, if for example A2 minus A1 is equal to A3 minus A2 is equal to A4 minus A3, right? What does it mean? In the same time interval, if the concentration of reactants, if they show the same common difference, that means if the concentration of reactants, if they form arithmetic progression, then do remember this particular reaction at that time is going to be the zero order reaction. Do remember at that point of time, this particular reaction which we have, it's going to be a zero order reaction. Do remember this, it's one important thing, okay? And at the same time, if in the same time interval, A2 divided by A1 is equal to A3 divided by A2 is equal to A4 divided by A3. That means common ratio is same. That means the concentrations of reactants, they are forming the geometric progression. Remember at that time, the reaction at that particular point of time is going to follow the first order kinetics. The reaction at that point of time is going to follow the first order kinetics. Do remember this particular thing as well. Okay? When the concentration of reactants are forming AP, that means at that time, zero order. GP, at that time, it's going to be the first order. Yeah? Now, let's try to do a few questions so that you can understand all these things carefully and properly. Just a second. Just a second, guys. Okay. What do you think about this particular question? Will you be able to solve this? Will you be able to solve this question? What do you think? Quickly. What do you think? You have got a first order reaction, let's say in this format, A gives B. It's mentioned that time taken to complete 75% of the first order reaction is equal to 100 minutes. Time taken to complete 75% of the first order reaction is 100 minutes. Calculate the time taken for 87.5% completion. Calculate the time taken for 87.5% completion. That's something I need to calculate. Time taken to complete 75% of reaction is given. Time taken to complete 87.5% of the reaction. What do you think? What do you think should be the answer? It's simple again. Say, time taken to complete 75% of the first order reaction, that's equal to the 2 times half-life. So 2 times half-life is equal to 100. So I can say half-life of the reaction is basically 50 minutes. Right? This is the half-life of the reaction. Now, few minutes back only I told you, time taken to complete 87.5% of the reaction, it's basically equal to 3 times half-life. So, it's going to be 3 times, half-life is 50, the value comes out to be 150 minutes. So, time taken to complete 87.5% of the reaction is just going to be 150 minutes. Clear to everyone? Quickly in the chats. Everyone in the chats quickly. Everyone in the chats quickly. All right. Now look at one more question. Look at one more question. For an elementary reaction, X gives Y plus Z. This is one elementary reaction. Half-life of this elementary reaction is given. Half-life is 10 minutes. Okay. In what period of time would the concentration of X, be reduced to 10% of original value? First of all, it's not mentioned anywhere that whether the reaction is 0 order or first order, but it's mentioned that the reaction is elementary. And do remember, for elementary reactions, molecularity is equal to order. Molecularity of this reaction is 1, so its order has to be 1 as well. So it's the first order reaction, number 1. Okay. Number 2. Initially, let's assume at time t is equal to 0, or let's just do one thing, just a second. T half is given to us, right? If half-life is given to us, what are we supposed to calculate? In what period of time would the concentration of X be reduced to 10% of its original value? Okay. So, you know, when you talk about the half-life, what just happened? Just a second, guys. Okay, when you talk about the half-life of the first order reaction, that's equal to 0.693 divided by K. Correct? So, from here you can calculate the K value, which is just going to be 0.693 divided by T half. So, it's going to be 0.693 divided by T half. T half is given to us as 10. So, the value is going to be 0.0693. Right? And it's going to be, the units are in minutes, so it's going to be minute inverse. So, we got the rate constant. First part is done. Okay? First part is done. Now, let's assume the initial concentration of reactant is A0. This is 0 and this is 0. The question says in what period of time? Would the concentration of X be reduced to 10%? In what period of time would the concentration of X be reduced to 10%? So, initially, the concentration of reactant was A0. Now, in what period of time would the concentration of X be reduced to 10%? So, let's say at time t, the concentration of X is reduced to 10% of its initial concentration. Let's assume now the concentration of reactant left is 10 by 100 A0, which means 0.1 A0, or you can say A0 by 10. You can just write it as A0 by 10. And the concentration of reactant left at any time is represented by 80. You know it. Okay? You know it. At what time the concentration of reactant left is 10% of its initial concentration. Okay? So, this is the condition which I got. We need to check at what time the concentration of reactant left is A0 by 10. Now, use the integrated rate equation. You can say from the integrated rate equation, T is equal to 2.303 divided by K. It's going to be log of A0 divided by 80. Log of A0 divided by 80. Now, you can say T is equal to 2.303 divided by rate constant is basically 0.0693, and it's going to be log of A0 you are writing as such. 80 value is nothing, that's A0 divided by 10. So, A0 cancel, log 10 is 1, right? A0 cancel, log 10 is 1. Now, it's a matter of calculation, just solve it, get the answer in minutes. That's all, right? Clear to everyone? Is it clear to everyone? Is it clear to everyone? Let's have a look on one more question then. Let's have a look on one more question. Look at this question carefully. An organic compound undergoes a first order decomposition. Time taken for its decomposition to 1/8 and 1/10 of its initial concentration are this and this. Calculate something. Let's have a look. Good question it's. See guys. As far as the question is concerned, let's assume we have got a reaction A gives B, whose rate constant is K. Let's say initially the concentration of reactant is A0, this is 0. Now as per the question, at time t is equal to T1/8, at time t is equal to T1/8, the concentration of reactant left is equal to A0/8. This is something, this is the first condition which is given to me. This is the first condition that's given to me. At time t is equal to T8th, this is the concentration of reactant left. Similarly, at time t is equal to T1/10th, the concentration of reactant left is A0/10. Right? So this is the concentration of reactant left at time t is equal to T1/10th. This is also given to me. Correct? Now, how many conditions I have? 2 conditions. I have 2 conditions, right? I have 2 conditions. What am I supposed to calculate? I am supposed to calculate T1/8 divided by T1/10 into 10. First of all, what is our integrated rate equation? Integrated rate equation is T is equal to 2.303 divided by K. It is a log of A0 divided by AT. Correct? This is our integrated rate equation. Now, if you put the first condition into this equation, instead of T, you will be writing T1/8 is equal to 2.303 divided by K. It's going to be log of A0 divided by AT is just equal to A0 divided by 8. Perfect. So A0 A0 cancel, 8 comes up. It's going to be 2 raised power 3. It's going to be 2 raised power 3. Log of 2 raised power 3, that means 3 log 2 it's going to be. 3 into log 2. So 3 comes here, log 2 value is 0.3. Perfect. Similarly, if you put second condition into the integrated rate equation, instead of T, you will be writing T1/10th is equal to 2.303 divided by K. It's going to be log of A0 divided by AT here is A0 by 10. AT here is A0 by 10. A0 A0 cancel, log 10 is 1, right? A0 A0 cancel, log 10 is 1. Now I got 2 equations basically. This is my first equation and this is my second equation. These 2. Just divide them up. T1/8 whole divided by T1/10. How much will be the value? So this term got cancelled. So 3 into 0.3 is 0.9, right? So I can write T1/10th, sorry. I can write T1/8 divided by T1/10th. If you multiply this term with 10, it's going to be 0.9 multiplied by 10. The value comes out to be 9. So this is something which you are supposed to calculate, right? That's what we calculated. This value came out to be 9. So 9 is going to be the answer of this question, right? Clear? Is it clear to everyone quickly? Is it clear to everyone? It should be, right? It should be clear to everyone. Let's have a look on one more question. Let's have a look on one more question. Look at this question carefully. Look at this question carefully. For a first order reaction, choose the value of half-life. Some graph is given. It's mentioned that the order of reaction is 1. We need to calculate the half-life. You know, T half for the 0 order reaction, that's basically equal to 0.693 divided by K. So in order to calculate half-life, you need to know the value of K. Correct? You need to know the value of rate constant. Now, dear students, a graph is given to you. It's between log AT versus T. Log AT versus T. I have told you already, whenever you plot a graph between log AT versus T, its slope, few minutes back only I told you, its slope is equal to minus K upon 2.303. What is slope? Slope is nothing, it is tan of theta. What is theta? Theta is the angle which the graph makes with the positive x-axis in the anticlockwise direction. So it's tan of 135, which is basically minus 1. So minus K upon 2.303 is equal to minus 1. So K value you got to know as 2.303. And it's, I guess, minute inverse, right? It's minute inverse. So rate constant value you got. Since you got the value of rate constant, if you got the value of rate constant, put it here, it's 0.693 divided by K is 2.303. The answer comes out to be 0.3 minutes. So this is something which you were supposed to calculate, I guess, half-life of the reaction. It came out to be 0.3 minutes. I hope this is clear to everyone. Okay, perfect. Done with this? Done with this quickly? Done with this? One more thing about the first order reactions. That's again important. Do remember this as well. So for example, when you have got the reaction in this format, A gives B. Let's say at time t is equal to 0, the concentration of reactant is A0. Let's say at time t1, the concentration of reactant left is AT1. At time t2, the concentration of reactant left is AT2. Okay. Let's assume when the concentration of reactant left is AT1, at that point of time, rate of this first order reaction is R1. Similarly, when the concentration of reactant left is AT2, at that point of time, let's assume the rate of reaction is R2. Okay. So I can write integrated rate equation in a different format as well. There's a derivation basically, but derivation I'm not going to show you. I'm just going to give the result. K is going to be equal to 2.303 divided by, it's going to be T2 minus T1. Now it's going to be log of AT1 divided by AT2. Or you can write it in different way as well. 2.303 divided by T2 minus T1. It's going to be log of R1 divided by R2. Right? Sometimes a question can be asked from this as well. For example, let me check if we have any question on this equation. Yes, there is a question. There is a question on the same equation. Look at the question carefully. Look at the question carefully. The rate of the first order reaction. The rate of the first order reaction is this at 10 minutes and this at 20 minutes after initiation. Find the half-life. You need to calculate the half-life of the first order reaction, which is going to be 0.693 divided by K. So basically rate constant you have to calculate K. And rate constant K you can calculate in this format. 2.303 divided by T2 minus T1. T2 and T1 are given. Log of, you can write R1 divided by R2. Both the rates are given, both the times are given. So you can calculate rate constant and put it here and get the half-life. Isn't it very simple? When am I going to complete the rest of the portions? On Friday. On Friday, I'll take one more marathon in which all the other chapters will be done. Class 11th Physical Chemistry. Class 11th Physical Chemistry I'll be doing in the Friday's marathon. Okay, in the Friday's marathon. Today it was class 12th now. Perfect, because I had to teach everything in detail. So class 12th part will be done and class 11th will be done on Friday. Okay, is that cool? Surface chemistry, maybe HSP sir will be teaching you the surface chemistry. I'll tell HSP sir to take care of surface chemistry. I'll take care of the other chapters like thermodynamics, equilibrium, solutions, right? Those chapters I'll be taking care of. Perfect. So I'm sure till here it's clear. One more question I would want to share with you, and after that we'll be moving on to the Arrhenius equation. Look at this question carefully. What do you think? Can you solve this one? Can you solve this one? In what time will the molar ratio of ethylene to cyclobutane be 1? What is it? What does it mean? What does it mean? Have a look properly on the question. In what time the molar ratio of ethylene to cyclobutane be 1? So you have got a reaction first of all, right? Let's say at time t is equal to 0, the moles of reactants now at time t is equal to 0 are A, this is 0. For example, initially at time t is equal to 0, the moles of reactant is A, the moles of product is 0, right? Let's say at some time t, out of A moles of reactants, let's say X moles got dissociated into products. So I'll be left with A minus X moles of reactants, right? Now we use the stoichiometry. Since 1 mole gives 2 moles, so from X moles you'll be getting 2X moles, correct? I assumed at time t, at time t, the moles of reactants left are A minus X, the moles of product formed are 2X. I'm assuming this is the time when the molar ratio of ethylene to cyclobutane is equal to 1. I'm assuming this is the time t when the ratio of moles, when 2x divided by A minus X value, is equal to 1. This is the time t. This is the time t which I'm assuming when 2x divided by A minus X value is equal to 1. Correct? So I would say 2x from here comes out to be A minus X. So 3x is equal to A, or you can say x is equal to A divided by 3. So I can say at time t I got the value of x. Okay? At time t I got the value of x. What do I need to calculate? I need to calculate the time in which the molar ratio of ethylene to cyclobutane is 1. So I'll use the integrated equation. 2.303 divided by K is going to be log of A naught by AT. A naught is A here, AT is A minus X, X is A by 3. So you can do a bit of calculation. So it's 2.303 divided by K value is also given, 2.3 into 10 raised power minus 4. It's going to be log of A divided by 2A by 3. 2A by 3. So A cancelled. So it becomes log of 3 by 2, which comes out being log of 3 minus log of 2. Correct? So 2.3, 2.3 almost cancelled. So T is equal 10 raised power minus 4 comes up. So log of 3 is your 0.6. Log of 2 is log of 3 is 0.47, right? 0.47, log 2 is 0.3. When you do a bit of calculation, T from here comes out to be, it will be 1700 seconds. It will be 1700 seconds. So what is meant by the 1700 seconds? It means after the 1700 seconds, the ratio of the moles of product and reactant will become 1 exactly. Okay? Perfectly done? Is it clear? Is it clear to everyone? It should be. Yeah? Now, one more topic which we are going to discuss now, that's going to be your Arrhenius equation. Arrhenius equation. From this equation also, the question comes. Okay? Arrhenius equation. What is Arrhenius equation all about? Basically, Arrhenius equation is going to let you know how rate constant changes on changing the temperature. Arrhenius equation is going to let you know how rate constant of a reaction changes on changing temperature. Okay? Now, dear students, for example, you have got a reaction like this. A gives B. A gives B. Let's assume the rate constant of this reaction is K when the temperature is kept T. When the reaction is carried out at temperature T, its rate constant, for example, is K. Okay? Now, I'll change the temperature and I'll see what will happen to the rate constant. Arrhenius equation says that K is equal to rate constant is equal to A e raised power minus EA by RT. First of all, this A is called as pre-exponential factor. A is called as pre-exponential factor, right? And let me tell you this A and EA combinedly they are called as Arrhenius parameters. They are called as Arrhenius parameters. Combinedly they are called as Arrhenius parameters. Okay. Now let's do simple maths. Let's say I increase the temperature of the reaction. For example, I'm going to do one thing. I'm going to increase the temperature of the reaction. Temperature I'm increasing. If I increase the temperature, what will happen to EA divided by RT value? Will this value increase or decrease? If I increase the temperature, that means I'm increasing the denominator. This whole term will decrease for sure. This whole term will decrease. If this term is decreasing, if this particular term is decreasing, that means minus EA divided by RT term. Minus EA divided by RT term. This whole term will increase. And if this term is increasing, that means E raised power minus EA by RT will be increasing. Right? And if this EA by RT term increases, so I can categorically say that rate constant also increases. Okay? So what can we conclude from here? We can conclude one simple thing. On increasing the temperature, the rate constant of the reaction increases. On increasing the temperature of the reaction, you can say the rate constant of the reaction that increases. Okay? That increases. Now your Arrhenius equation, which can be written in different formats as well. K is equal to A e raised power minus EA by RT. Asha, one more thing I will tell you. On increasing the temperature, let me tell you, on increasing the temperature, rate constant of forward reaction as well as rate constant of backward reaction increases. Okay, do remove this thing as well. On increasing the temperature, rate constant of forward as well as backward reaction increases. Okay. So first of all, let me do one thing. Let me multiply this equation with ln. So it's going to be ln of k is equal to ln of A minus EA by RT. This is one more form of the Arrhenius equation. One more form of the Arrhenius equation, or you can convert it into the logarithmic form as well. So it's going to be log of k is equal to, it's going to be log of A minus EA divided by 2.303 R multiplied by 1 by T. Correct? This is one more format of the same Arrhenius equation. There can be few graphs which can be plotted on this equation as well. Okay, you should know them as well, as far as your NEET examination is concerned. For example, you are going to make a curve, you are going to make a graph between ln of k versus 1 by t. What do you think should be the nature of the curve here? We made one equation right now, ln of k is equal to ln of A minus EA divided by R multiplied by 1 by t. This is the equation which we wrote few minutes back. Now, dear students, ln k you are plotting along y-axis, 1 by t you are plotting along x-axis. This whole term becomes your m, and this is minus, and this becomes c. Y is equal to minus mx plus c. It's going to be a straight line with a negative slope. So slope of this graph over here is equal to basically minus EA divided by R. Okay. Similarly, if you want to plot one more graph like this, it's going to be between ln of k, not ln of k, sorry, it's going to be between log of k versus 1 by t. This graph again will have the same nature, but the slope right now will change. Slope now is going to be minus EA divided by 2.303 R. Okay, minus EA divided by 2.303 R. Okay, perfect. One more thing which I would want to share with you, do remember that as well. You know, there is something called as temperature coefficient. There is something called as temperature coefficient. Temperature coefficient is represented basically by N, and it's defined as the rate constant of the reaction at temperature T plus 10 Kelvin divided by rate constant of the reaction at temperature T Kelvin. So basically we know, you must have heard, that when we increase the temperature of the reaction by 10 Kelvin or by 10 degrees centigrade, rate constant doubles or even becomes more than that. Let me write the statement first. On increasing the temperature by 10 Kelvin, or you can say 10 degrees centigrade, right? Rate constant doubles or even becomes more than that, right? So if I want to define temperature coefficient for the reaction, it's going to be rate constant at temperature T, that's K. When temperature is raised by 10 Kelvin, rate constant, let's assume, now is 2K. So K got cancelled, so N value is 2. Now it's not necessary that rate constant doubles, it can be more than double also. So do remember, N value, temperature coefficient, it's greater than 2, less than 3. Number 1. Number 2, since we know on increasing the temperature by 10 degree or 10 Kelvin, right, rate constant doubles. Even rate of reaction doubles. Okay. So one thing which I would want to tell you like this. Let's say you have got a reaction like this, A gives B. Okay. At temperature T1, rate constant of the reaction is K1. At temperature T2, rate constant of the reaction is K2. For example, I have increased the temperature. Let's say I have increased the temperature. On increasing the temperature, rate of the reaction increases, of course, right? On increasing the temperature, rate of the reaction increases. Now, do remember one thing, R2 divided by R1. R1 is the rate of reaction at temperature T1. R2 is rate of reaction at temperature T2. R2 divided by R1 is always equal. It will be equal to 2 raised power T2 minus T1 divided by 10, right? R2 divided by R1 is equal to 2 raised power T2 minus T1 divided by 10. So this equation is going to let you know how many times the rate has increased. For example, I'll give you a question. On this. Let me give you a question on this. Let's say you've got a reaction like this. A gives B. the initial temperature of this particular reaction was 10 degrees centigrade. Now you are increasing its temperature till 100 degrees centigrade. I need to see how many times rate of reaction has increased. So you'll write simply like this: R2 divided by R1 is equal to 2 raised power T2 minus T1 divided by 10. So R2 is the new rate of reaction, R1 is the earlier rate of reaction, is equal to 2 times 2 raised power. T2 minus T1 is 90, 90 divided by 10 is 9. So R2 is equal to, it has become 2 raised power 9 times R1. So rate of reaction has increased by this particular factor, 2 raised power 9 times. I hope this is clear to everyone. Okay? Right? All clear? All clear, guys? I think, guys, with this we'll be taking a leave here. The rest of the topic, the rest of the chapters, I'll be doing on Friday. Okay? So Friday, 9 a.m. we'll be doing the chapters like thermodynamics, equilibrium, solutions, and the other chapters which are very small chapters like redox and all. So that can be one more 10-hour marathon. That can be one more 10-hour marathon in which we'll be discussing the other chapters. Okay? Perfect? Someone is saying no. Guys, I'm not able to stand now. Whatever I've taught in this chemical kinetics, only this much you will study. That's it. Rest all nothing. Right? So I'll be taking a leave with this. Take care, prepare hard, properly prepare, okay? I mean, these are the some like 10, 11 days which are left. I mean, try to mobilize these 10, 12 days properly, right? And after the NEET examination, it's going to be like a far better life, I'm sure. So try to give as much as possible. And whatever you'll be in need of, just keep on letting me know all the time. I'll be coming up with a similar sort of series and all. By the way, tomorrow it's Shreya sir who will be starting at 9. And after that at 5 p.m. HSP sir will be doing class 11th organic chemistry in one shot. So do follow those sessions as well. And day after tomorrow it's Ambika ma'am. And in between I'll also keep on coming with some strategies, etc., etc. Okay? And these are the chapters like thermodynamics, equilibrium solutions, and like mole, etc., etc. These chapters will be doing on coming Friday. Okay? Chalo guys, with this I'll be taking leave then. Take care. God bless you all. मिलते हैं फिर. Take care. Yes, I'm in Bangalore. I'm right now in Bangalore. Yes. Where will I post the notes? I won't be posting the notes now. I'll post the notes combinedly on Friday. Combinedly on Friday. Okay. Marathon questions I'll be also doing, but I'm thinking to do the marathon questions in the free classes on Unacademy. You know what are the special classes? You know what are the special classes? I'm thinking to do 1000+ question practice in the special classes. After this Friday session, Friday I'll be taking this marathon, right? Maybe on Saturday, Sunday, we'll be doing some top 1000 question practice on the special classes. Cool? Again, so the ones who have not liked the session yet, please do like the session. Do share this channel with everyone, right? I mean, in just 3 to 4 days, we have grown a lot. I mean, we are now the family of almost 14,000 students, 14,000 people. Let's try to grow it even bigger. Let's make it the best channel across the country for all the students who want to learn in English, who have no resources, right? Who want to learn, but they have no resources. So let's make it the best, right? And everything is on you. What is, someone is saying, what is special class? I'll let you know about the special classes also. Just wait for that. Okay, so that 1000 question practice won't be on YouTube. I'll do it on the special class. Chalo guys, with this I'll be taking a leave. You take care. Bye-bye. God bless you all. See you tomorrow.